Students, again, I'll be starting from the basics. First of all, how do we exactly define the term equilibrium in general? In general, how equilibrium is defined? My dear students, let me write its definition. Let me tell you equilibrium. Equilibrium is that state of the system. I'm telling you the general definition of equilibrium. Equilibrium is that state of the system. Equilibrium is that state of the system at which entropy of the system attains its maximum value and gives free energy. Of the system attains its minimum value. This is the definition of the term equilibrium as per thermodynamics. You'll get to know, you'll understand this definition in some time. First thing which I want you guys to remember, what is equilibrium in general? Equilibrium is nothing. It is just a state of the system. Like you would have seen, initial state of the system, final state of the system, intermediate state of the system. So equilibrium is that state of the system at which entropy of the system attains its maximum value, gives free energy of the system attains its minimum value. And my dear students, as per thermodynamics point of view, that state of the system at which entropy attains its maximum value and gives free energy attains its minimum value, that is considered to be the most stable state of the system. So do remember, equilibrium, it is the most stable state of the system. Point number one, which you have to remember, guys. The question can be asked, the theoretical question. At equilibrium, entropy is maximum, gives free energy is minimum. This can be your first theoretical question that can be asked. Okay? Number one. Number two, people, one more thing. I did not make you understand the actual definition of equilibrium yet. I'm just telling you the meaning of equilibrium as per thermodynamics, right? Just try to understand. One more point. My dear students, at equilibrium, delta S is taken to be 0. Delta G is taken to be 0 as well. This is one more point which you are going to remember. At equilibrium, what is equilibrium? It is the state of the system at which entropy attains its maximum value, gives free energy attains its minimum value, right? And that state of the system, as per thermodynamics, at which entropy attains its maximum value, free energy attains its minimum value, that is considered to be the most stable state of the system as per thermodynamics is concerned. As per thermodynamics, delta S and delta G, change in entropy and change in Gibbs free energy, it is taken to be 0. This is the first point which I want you guys to remember for now. Now, you must be thinking, why am I telling you to remember this? Because this definition of equilibrium, we are not going to discuss in detail here. This definition of equilibrium, I'll make you understand in the chapter thermodynamics. So right here, just for your notes, remember these two things. Okay? Remember these two things. Perfect. Remember these two things. Now, my dear students, have you ever heard of what a reversible reaction is? Have you ever heard of what a reversible reaction is? Have you ever heard of what a reversible reaction is? Let me tell you, reversible reaction is that particular reaction which can proceed in both the directions, forward as well as backward. Any such reaction which has got the tendency to move in the forward direction as well as backward direction. Any such reaction which has got the tendency to move in the forward direction as well as backward reaction. That reaction is what you will be calling as a reversible reaction. And my dear students, the equilibrium which we have to discuss today, we have to basically discuss about the equilibrium of reactions. This is basically our chapter. In this chapter, we are going to discuss what? We are going to discuss about the equilibrium of reaction. Right? We are going to discuss about the equilibrium of reaction. And let me tell you the very first point. Let me tell you the very first point. What is that? My dear students, equilibrium, it is possible only in case of a reversible reaction. Any such reaction which can proceed in forward as well as backward direction, that's called as a reversible reaction. And equilibrium is possible only in case of which reaction? In case of a reversible reaction. Equilibrium is not possible in case of irreversible reactions. Next point. Take a note of this. Equilibrium is possible. Equilibrium is possible only in case of what? Only in case of reversible reactions. Equilibrium is possible only in case of a reversible reaction. Now you must be thinking, why every reversible reaction wants to attain equilibrium as soon as possible? You must be thinking, why every reversible reaction wants to attain equilibrium as soon as possible? What is the logic? Because equilibrium, it is the state of the system at which entropy is maximum, Gibbs free energy is minimum. That is the reason equilibrium is considered as the most stable state of the system. That is the reason why all your reversible reactions want to attain equilibrium as soon as possible, right? So if the question is asked like this, why every reversible reaction wants to attain equilibrium as soon as possible? What is the reason? The reason is equilibrium, since that is the most stable state of the system. And every system wants to attain stability. Simple. Yes. Right, people? Okay. So every reversible reaction wants to attain equilibrium as quickly as possible. As quickly as possible. What is the reason? Because equilibrium state is considered to be the most stable state of the system. The most stable state of the system. I hope this particular scenario is clear to everyone. Okay. Now guys, these were the general things which I was talking about. Now we are going to discuss the equilibrium in detail in the reactions. Now we are going to discuss equilibrium in detail in the reactions. But before that, there are some basic points which you need to know. There are some basic points which you need to know, which will make you understand the concept of equilibrium in a better way. Right? Try to understand. Try to understand, guys. First of all, I'm going to write a statement. The statement is, as the reaction proceeds, concentration of reactant decreases and the concentration of product increases with time. This is one of the most important point here. Whenever, my dear students, you will be having a reaction, reactants getting converted into products. As the reaction starts, as the reaction keeps on proceeding, concentration of reactant, it decreases with time. Concentration of product increases with time. Now, you must be thinking what this concentration is. Yeah? You must be thinking what this concentration is. Try to understand. This particular point is very crucial. Try to understand. And it is the basic point. It is the basic point. For example, my dear students, I have got the reaction like this. A gives B. Let's say this is the reaction. Let's assume that this particular reaction has to take place in a container. This particular reaction has to happen. This particular reaction has to take place in a container whose volume is V. Volume of the vessel, imagine it is V liters. V liters is the volume of the vessel, right? Now, my dear students, imagine that initially at time t is equal to 0. Imagine, let's say we have got 10 moles of A. in the container. Initially at time t is equal to 0, when the reaction has not started. Time t is equal to 0 means reaction has not started yet. When the reaction has not started, that means reactants have not got converted into products yet. That means reactants have not got converted into the products yet. I'm talking time t is equal to 0. Initially, when the reaction has not started, there'll be only reactant with you in the container. There'll be 0 moles of product because the reaction has not started. Now, my dear students, when the reaction starts, when the reactant starts getting converted into product, what will happen to the moles of reactants with time? So can I say moles of reactants with time are going to decrease and moles of products with time are going to increase? As the reaction starts, moles of reactants will keep on decreasing and moles of products, they will keep on increasing. As simple as that. Now, my dear students, I'm defining a term concentration. I'm defining a term concentration, which is represented either by square brackets or C. How do you define the term concentration? Concentration is nothing. It is moles per unit volume in liters. It is moles per unit volume in liters. For example, I'm writing concentration of reactant. Concentration of reactant is nothing. It is moles of reactant divided by volume of the reaction vessel, right? Concentration of products, what does that mean? That means moles of product divided by volume of the vessel in liters. Now you tell me, I told you a few minutes back, as the reaction proceeds, number of moles of reactants, they keep on decreasing and number of moles of products will keep on increasing. Now, as the number of moles of reactant decreases with time, as the number of moles of reactant decrease with time, therefore concentration of reactant should also decrease with time because both are directly proportional to each other, right? Similarly, my dear students, as the reaction proceeds, moles of product increases with time. Therefore, concentration of product should increase with time also, right? That is the statement which I wrote over here. As the reaction proceeds, concentration of reactant decreases with time and concentration of product increases with time. Let's quickly have a look how to represent all these things graphically. Just a second, guys. Just a second. Something happened to my mic. Just people. Can you hear me? Can you hear me quickly? Can you hear me quickly? Yes or no? All right. Perfect. The thing which I made you understand over here, I'm just going to represent it in the graphical form. And how do I represent it graphically? It's pretty much simple. I'm going to make a graph over here. The graph is like this. Let's say on this side, I'm plotting the term concentration. And on this side, I'm plotting the term time, right? It is a concentration versus time graph. We know concentration of reactant decrease with time and concentration of product increase with time. So my dear students, if I make the graph like this, concentration decreasing with time, let me know whether this graph is valid for the reactant or product. This particular graph, it is valid for the reactant. Similarly, my dear students, if I need to plot one more curve, again between concentration versus time, we know concentration of product that increase with time. So if I make the graph like this, concentration increasing with time, that means this particular graph, it is valid for what? It is valid for the product. Let me know once in the chats if these two curves clear to you. Yes or no in the chats. Do remember, as the reaction proceeds, as the time goes on, as the reaction proceeds, concentration of reactant, even moles of reactant, they keep on decreasing. Similarly, moles of product, concentration of product, it keeps on increasing. Let me know quickly in the chats if this point is clear to everyone. With the fire symbols, people, everyone in the chats. This is the basic point. This is a very, very, very basic point. Okay, perfect. Now, guys, after understanding this basic point, let me make you understand one more thing. My dear students, In this chapter only, we have to discuss a law, which is called as the law of mass action. Well, the law of mass action, that will be discussed in detail after some time. That will be discussed in detail after some time. But right now, I just need one statement of law of mass action. I just need one statement of law of mass action. Rest, law of mass action will be detailed, will be discussed in detail after some time. But right now, I need one statement from law of mass action. Your law of mass action states that rate of reaction, the speed with which reaction takes place, it is directly proportional to concentration of reactants. It is directly proportional to concentration of reactants. Your law of mass action states that rate of reaction is directly proportional to concentration of reactants, right? Now, my dear students, try to understand. For example, I'm taking a reaction like this. Let's say I'm taking a reaction like this. A gives B. This is a reaction. It is proceeding in both the directions, forward as well as backward, right? If I ask you, look at this reaction carefully and tell me actually how many reactions are these? Is it actually one reaction or these are actually two reactions? Just tell me that. Just tell me that. You'll directly say these are actually two reactions. One is the forward reaction, one is the backward reaction, right? These are actually two reactions. Actually, these are two reactions. One is your forward reaction, A gives B, and one is your backward reaction, B gives A, right? This is your forward reaction and this is your backward reaction. One is forward and one is backward. Now, my dear students, in the forward reaction, which is your reactant? In the forward reaction, A is your reactant. In the backward reaction, which is your reactant? B is your reactant. For the forward reaction, A is the reactant. For the backward reaction, B is the reactant, right? Tell me one thing. Can you write law of mass action for the forward reaction? You should be able to do that. You should be able to write law of mass action for the forward reaction. And as per law of mass action, I can say rate of forward reaction is directly proportional to concentration of reactant. Reactant here is A. So it's concentration of A. Correct? Similarly, rate of backward reaction is directly proportional to concentration of reactant. Reactant here is B. Perfect. Now you tell me one thing. I told you a few minutes back. As the reaction proceeds, concentration of reactant decreases with time and concentration of product increases with time. This is something which we have already discussed. As the reaction proceeds, concentration of A decreases with time, concentration of B increases with time. Now you tell me, if the concentration of A is decreasing with time, can I say rate of forward reaction? Rate of forward reaction will be also decreasing. Similarly, if the concentration of B is increasing with time, can I say rate of backward reaction will be increasing? Do you see, guys? Rate of forward reaction is decreasing with time, and rate of backward reaction is increasing with time. Rate of forward is decreasing with time. Rate of backward is increasing with time. Can I say there will be a scenario when rate of forward and backward reaction becomes equal? Agreed? You got to know the rate of forward reaction that decreases with time. The rate of backward reaction increases with time. So there will be a scenario when the rate of forward and backward reaction becomes equal, and that particular stage in a reaction at which rate of forward and backward reaction becomes equal, you call that state of the system as the equilibrium state. Let me know once in the chats if it's clear. Let me know once in the chats if it is clear. So I'm writing it in the form of statement. The statement is simple. As the reaction proceeds, rate of forward reaction decreases and rate of backward reaction increases. Therefore, a stage reaches at which rate of forward and rate of backward reaction becomes equal, and that stage in a chemical reaction at which rate of forward and backward reaction becomes equal, you call that stage as the equilibrium stage, right? So when do we say equilibrium is established in the reaction? Quickly answer me this. When do we say equilibrium is established in the reaction? Whenever you see rate of forward and backward reaction, both are becoming equal, at that point of time, you will directly say that in the reaction, equilibrium has established. Say yes or no in the chats if this is clear to everyone. Say yes or no in the chats if this particular point is clear to everyone. Everyone means everyone. Everyone means everyone. Let me know once in the chats if you got this particular point. Yes? So as the reaction proceeds, rate of forward reaction decreases, rate of backward reaction increases, a stage comes at which rate of forward and backward reaction becomes equal, and that particular stage is what you call as equilibrium stage. That's what you call as equilibrium stage. I believe this is clear to everyone, yeah? Guys, you have to be involved in the chats. Chat should not stop at all. If basics is getting clear, your equilibrium will be done and dusted. I'm telling you in this session itself. And I'm telling you, after watching this particular session completely, try any sort of book which is related to your NEET or even JEE mains. You should be able to solve each and every question on your own. Mark my words, it's my promise to you. Provided you have your clear eye, your clear focus on the screen for 7 hours complete. Just give me your 7 hours, equilibrium is yours. I'm telling you that. Give me your 7 hours, the equilibrium is yours. Then try to solve each and every question from any book. You should be able to solve that. Okay? Perfect? Perfect, guys. Now, there are a few more points which I would want you guys to remember. What is that? My dear students, equilibrium, it is always dynamic in nature. Have you ever heard of this particular statement? Equilibrium is dynamic in nature. What does it mean? What does it mean? It means once equilibrium is attained in the reaction never stops. Why? Because continuously forward and backward reactions will be going with the same speed. Forward, backward, forward, backward, forward, backward. Continuously it will keep on happening. So once equilibrium is established in the reaction, that means in the reaction that stage has reached where entropy is maximum, Gibbs free energy is minimum. That means the most stable state of the reaction has reached. And every reaction would want to be in the stable condition only, right? That's why we say once equilibrium is established in the reaction, it never stops. Forward reaction keeps on happening, backward keeps on happening. So continuous process it. Okay? Perfect. Apart from this, there is one more statement which I would want you guys to remember. Any such reaction, or let me write it like this. Any reaction, just a second. Any reaction involving a gaseous reactant or product. A gaseous reactant or product. Any reaction involving a gaseous reactant or product can attain equilibrium only in a closed vessel. Only in a closed vessel. This is again one more important point which can be asked in your examination. Now, how do we understand this? My dearest students, imagine that you have got a container. Right? Imagine that you have got a container. Assume that this container is open on one side. It is open on one side. Now, my dear students, in this particular container, let's imagine that in this container, you are keeping calcium carbonate in the solid form. You have kept calcium carbonate in this particular container in solid form. Now, my dear students, you know, when calcium carbonate is heated, you have taken calcium carbonate in the container. Now, you are heating the container. That means you are heating this calcium carbonate. And you should know, when calcium carbonate is heated, it gets converted into calcium oxide solid plus what? Plus carbon dioxide gas. This is the reaction which is going to happen. You have taken calcium carbonate in the container. Now you are heating the container. Means that you are heating calcium carbonate. And when calcium carbonate heats up, you get calcium oxide solid. With that, you get carbon dioxide gas. So during this reaction, can I say a gas is produced? Absolutely, a gas is produced. Now, the container is open on one side. If the container is open on one side, can I say whatever gas is getting formed through this reaction, that gas will escape? Absolutely, that gas will escape. If the gas escapes, there'll be no carbon dioxide in the container. If there'll be no carbon dioxide in the container, is the backward reaction possible then? Is the backward reaction possible? No. If the backward reaction is not possible, should I be calling this as reversible? No. Equilibrium is established only in reversible reactions. So here, equilibrium won't be established. Yeah? Here, equilibrium won't be established. I believe this particular point is clear to you. I believe this particular point is clear to you. Right? I believe this particular point is clear to you. Any reaction involving minimum one gaseous reactant or product can attain equilibrium only when the reaction is taking place in a closed vessel. I hope this is clear to you. Apart from this, look at this particular point. As I told you, as the reaction proceeds, rate of forward reaction decreases, rate of backward reaction increases. There will be a scenario when rate of forward and backward reaction becomes equal. What do you call that as? You call that as equilibrium, right? Can you understand this whole scenario in the form of a graph? Do you want to understand the whole scenario in the form of a graph? Have a look. Have a look. Have a look. Try to understand. Over here, I'm plotting a rate of the reaction, right? Over here, I'm plotting time, rate versus time, rate versus time, rate versus time. We know rate of forward reaction that decrease with time, rate of forward reaction decrease with time, right? Rate of backward reaction that increase with time, that increase with time. And then there comes a scenario. Then there comes a scenario after which rate of forward and rate of backward reaction becomes equal. And that particular point at which the rate of forward and backward reaction becomes equal, you say at that particular point of time, equilibrium is established. The above curve represents rate of forward reaction, which is decreasing with time. The below curve, it represents rate of backward reaction, which is increasing with time. So forward reaction rate decrease with time, backward reaction rate increase with time. There will be a scenario at which, after which, rate of forward and backward reaction becomes equal. And then when this particular point comes, when rate of forward and backward reaction becomes equal, then you say that the equilibrium is established in the reaction. I believe this is again clear to everyone. Yes, I believe this is again clear to everyone. If this is clear, then you should be able to answer me this particular question. You should be able to answer one simple question, which I'll be giving you. You should be able to answer. Try to understand. One question I'm giving you. This is rate versus time. Rate versus time. Rate versus time. This is one curve. This is one curve which I'm giving you. Okay. Similarly, I'm giving you one more curve. Let me see what is your level of understanding. Let me see what is your level of understanding. This is one curve. This is one more curve. Similarly, again, I'm plotting rate versus time. Rate versus time. This is your one curve. This is your one more curve. Let me know, do all these three curves represent equilibrium? Just I want yes or no from you. Do all these three curves represent equilibrium? Yes or no from your sides. Nothing else. Nothing else I need. Do all these three curves represent equilibrium? Quickly. Yes or no from your side. Wonderful. Good. Love you all. Good. Perfect. All these curves, they are not going to represent equilibrium. Why? What is the logic? What is the logic? All these three graphs, they are between rate versus time. And when you define equilibrium in terms of rate, you say equilibrium is that state at which rate of forward and backward reaction becomes equal, becomes equal, becomes equal, becomes equal, becomes equal. Try to understand. Becomes equal. Try to understand. This particular graph, it is for forward reaction because rate of forward decreases, rate of backward increases, right? So there has come a stage at which rate of forward and rate of backward reaction has become equal, right? Now, this particular graph is for forward. This is for backward because rate of forward decreases, rate of backward increases, right? So this particular point over here, it represents rate of forward reaction. Over here, this particular point, it represents rate of backward reaction. So are these rate of forward and backward equal here? No. As you can categorically see, rate of forward reaction is more than that of rate of backward reaction, which is not the criteria for equilibrium. Over here, this particular curve is for backward. This particular curve is for forward. This is a point which represents rate of forward reaction. This is the point which represents rate of backward reaction. So this particular curve is saying that rate of backward reaction is greater than rate of forward reaction, which is not the criteria for equilibrium. So this does not represent equilibrium. Is this point clear? Is this point clear? I'm going to teach you something amazing now. I'm going to teach you something amazing. Tell me whether all the points till now are absolutely clear or not. Quickly, people, everyone in the chats. Yes? Now try to understand one more thing. One very important thing. At equilibrium, all the measurable properties this is one very, very, very important point. At equilibrium, all the measurable properties of the system, like measurable properties means those properties which we can measure, like moles, like concentration, like pressure, like color, right? At equilibrium, all the measurable properties of the system, what do? They attain a fixed value. They attain a fixed value. That means they become constant. That means they become constant. What is meant by this particular point? This is very important. Entire chemical, entire molecular equilibrium revolves around this particular statement, guys. Entire molecular equilibrium revolves around this particular statement. What this statement says, before understanding this particular statement in detail, try to understand the definition. The definition is saying, once equilibrium is established in the reaction, after that, the moles of reactants and products won't change at all. The concentration of reactants and products won't change at all. The pressure of reactant and product won't change at all, right? So all the measurable properties of the system, they attain fixed value. They become constant. They become constant. This is one very important point. Once equilibrium is established in the reaction, guys, understand this. Once equilibrium is established in the reaction, after that, the moles of reactants and products are not going to change. The concentration of reactant product is not going to change. The pressure of reactant product is not going to change. Now, you must be thinking, why? How do we get the detailed explanation of this particular point? Since I told you, your entire molecular equilibrium, that revolves around this particular point. So there should be some logic as well, because this point is very important. So let's try to understand this particular point in depth. Try to understand, people. Try to understand what exactly I'm going to say. Have a look. Have a look, guys. For example, I'm taking a reaction. Try to understand carefully. The reaction is like this. Let me directly write a reactant in equilibrium with product. This is a reaction which is, for example, taking place in a container whose volume is 1 liter. Volume of the reaction vessel is 1 liter. Assume that. Volume of the reaction vessel is 1 liter. Imagine that initially at time t is equal to 0. Initially at time t is equal to 0. When the reaction has not started, assume that we have got 10 moles of reactant in the container. Assume that we have got 10 moles of reactant in the container. Since the reaction has not started yet, therefore the moles of product formed at time t is equal to 0 has to be 0. Right? Initially we had 10 moles of reactants. And moles of product at time t is equal to 0 has to be 0 because the reaction has not started yet. Reactant has not got converted into product yet. Now, my dear students, I am assuming one simple thing. I'm assuming after the completion of 30% of the reaction. I'm assuming after the completion of 30% of the reaction, equilibrium got established. This is something I'm assuming. I'm assuming after the completion of 30% of the reaction, equilibrium got established. Now, what is meant by that 30% of the reaction is completed? What is meant by the term 30% of the reaction is completed? That means 30% of the reactant has got converted into product. How much reactant I had in the beginning? 10 moles. What is 30% of 10? 30% of 10 means 3 moles. So that means at equilibrium. That means at equilibrium. At equilibrium, out of 10 moles of reactants, 3 moles have got converted into products. So can you let me know at equilibrium how many moles of reactant will be left in the container? I started with 10. Out of 10, 3 moles are getting converted into products. So I'll be left with 7 moles of reactants in the container at equilibrium. Right? Tell me how many moles of product have got formed. I would directly say 3 moles of product would have got formed. Yes, I would directly say 3 moles of product would have got formed. So my dear students, I'm assuming once 30% reaction is completed, equilibrium is established. 30% reaction completed means 30% of the reactant has got converted into product. Then only in the reaction equilibrium has established. And when 30% of the reaction is completed, there will be, out of 10 moles of reactant, there will be only 7 moles of reactant left and 3 moles of product would have got formed. Yes? Right? Now guys, try to understand what I'm going to say exactly. Try to understand very carefully what I'm going to say. Try to say. I'm assuming equilibrium is established now. If equilibrium is established, that means now in the reaction, rate of forward and rate of backward reaction has got equal. What does that mean? It means that if 1 mole of reactant now is getting converted into product, at the same time, 1 mole of product will be getting converted into reactant. I hope you're getting it. Right? I'm assuming 30% of the reaction is complete. Equilibrium is established. If equilibrium is established, that means rate of forward and backward reaction has got equal. What does that mean? That means if 1 mole of reactant is getting converted into product, in the same time, 1 mole of product will be getting converted into reactant. Now tell me, will the moles of reactant and product change now? Can the moles of reactant and product change with time now? The moles of reactant and product are not going to change at all because equilibrium is established. The moles of reactants and products are not going to change. If by chance 1 mole of reactant wants to get converted into product, at the same time, 1 mole of product will again get converted into reactant. So the moles of reactants and products are not going to change. Right? Right? That's what you have written over here. At equilibrium, all the measurable properties like moles, they attain a fixed value. They do not change at all. Perfect. Now people, these are the moles of reactants and products at equilibrium, right? So if I ask you, what will be the concentration of a reactant at equilibrium? What is concentration? Concentration means moles per unit volume. Moles per unit volume, right? So concentration of reactant at equilibrium will be equal to moles of reactant at equilibrium, that is 7, divided by volume of container, that's 1. So it comes out to be 7 molar. So this is the concentration of reactant at equilibrium. Similarly, concentration of product at equilibrium will be directly 3 molar, right? Perfect. Right? Now you tell me one simple thing. See, volume of the container is constant. Volume of the container is constant. If moles of reactant and product are not changing with time, once equilibrium is established, I can say concentration of reactant and product also is not going to change with time. I can say concentration of reactant and product is not going to change with time once equilibrium is established in the reaction. Yes? Right, people? Agreed? If this point is clear, I'm asking you what is the concentration of reactant at equilibrium. You will say the concentration of reactant at equilibrium is 7 molar. Concentration of product at equilibrium, that is 3 molar. If I want to show it in the form of a graph, the graph here is going to be concentration versus time. The graph here is going to be concentration versus time. See, what is happening to the concentration of reactants with time? Concentration of reactants with time is decreasing. Concentration of reactant with time was decreasing, and then after some time, it attained a fixed value. It attained a fixed value. It's not changing. Similarly, concentration of product is increasing with time, then is attaining a fixed value. Then is attained a fixed value. Can I say this is the point? This is the point after which after which the concentration of reactants and products, this is the point after which the concentration of reactants and products are not changing at all. So I would say at this particular point, equilibrium has got established in the reaction. So this particular curve, it represents equilibrium. This is concentration versus time. This is not rate versus time. This is not rate versus time. This is concentration versus time. Yes. So after this point, I would say equilibrium is established because the concentration of reactants and products, they have attained the fixed value, right? And this particular point on the curve, it is giving you the concentration of reactant at equilibrium. This particular point on the graph, it is giving you the concentration of product at equilibrium. And as you can see, this is one type of the equilibrium where you see the concentration of reactant is more than that of concentration of product. So this particular curve suggests that the concentration of reactant at equilibrium, the concentration of reactant and product at equilibrium, they have attained a constant value, but concentration of reactant at equilibrium is greater than that of concentration of product at equilibrium. I believe this is clear. I believe this particular point is clear. So let me know once in the chats. Is this particular curve representing equilibrium? Yes or no? Is this particular curve representing equilibrium? Yes or no? Quickly. Absolutely, I would say this particular curve is representing equilibrium. And this particular equilibrium is saying that concentration of reactant at equilibrium is greater than that of concentration of product at equilibrium. Say yes or no in the chats. Then I'm going to give you one more case. Say yes or no in the chats. Then I'm going to give you one more case, which might confuse you afterwards. Which might confuse you afterwards, okay? Which might confuse you afterwards. Have a look. Have a look, guys. Try to understand. For example, I've got the reaction like this. Reactants, and this is product. Again, I'm assuming volume of the container is 1 liter. This is something which I'm assuming. Volume of the container is 1 liter. Volume of the reaction vessel is 1 liter. Now, people, initially, for example, at time t is equal to 0, imagine I've got 10 moles of reactant. So this is going to be 0 because the reaction has not started yet. Now, I'm assuming when 50% of the reaction gets completed, I'm assuming when 50% of the reaction got completed, equilibrium is established. I'm assuming when 50% of the reaction is completed, I'm assuming equilibrium is established in the reaction. Now you tell me, what is meant by 50% completion? That means 50% of the reactant has got converted into products. 50% of the reactant has got converted into products. What is 50% of 10? What is 50% of 10? That's 5. So I would say once 50% reaction is completed, that means 50% of the reactant has got converted into product. That means out of 10 moles of reactant, 5 moles got converted. So I'll be still left with 5 moles of reactants in the container, right? Initially I had 10, now I'm left with 5, right? How many moles of products would have got formed? I would say 5 moles of products would have got formed. Now I'm assuming equilibrium is established. That means rate of forward and backward reaction has got equal. Now people, if 1 mole of reactant is getting converted into product, at the same time, 1 mole of product will be getting converted into reactant, right? Perfect. So equilibrium has established. So tell me, are the moles of reactants and products going to change now? Now the moles of reactants and products are not going to change. Now the moles of reactants and products are not going to change. Yeah? Now the moles of reactants and products are not going to change because equilibrium is established. Tell me, what is the concentration of reactant and product at equilibrium? Can I say the concentration of reactant at equilibrium is 5 molar? The concentration of product at equilibrium is again 5 molar because volume of the container is 1 liter. Yeah? Perfect. Can you express this whole scenario in the form of a graph? You should be able to express this whole scenario in the form of a graph. You should be able to do that. You should be able to do that. This is concentration. This is time. Okay? And we know concentration of reactant decrease with time and then attains a fixed value. Attains a fixed value. Concentration of product increase with time, then attains a fixed value. Attains a fixed value. Attains a fixed value. Attains a fixed value. Right? And this is the equilibrium which is telling you that the concentration of reactant and product at equilibrium, first of all, they are constant, they are not changing, and at the same time they're equal as well. What is the criteria of equilibrium as per concentration? As per concentration, equilibrium, it is that state at which the concentrations of reactants and products, they attain a fixed value. They can be equal as well. They can be equal as well. Criteria is concentrations have to be constant, right? So this particular curve, does it represent equilibrium? Absolutely it does. This curve, it represents equilibrium, right? YK, you can complete your syllabus here on this channel as well, because this is your proper JEE means content which is going on, because NEET level is also going to raise, okay? Please do not spam in the chats or else you can leave, please. Okay? Perfect, guys? Okay, one more case. One more case to understand equilibrium. For example, again, I'm taking the reaction. Reactants getting converted into products. Reactants getting converted into products. Now, my dear students, this particular container, the container in which the reaction takes place, that's again 1 liter. Assume that. Initially, at time t is equal to 0, the moles of reactants are 10, moles of products are 0. Let's assume that again. Now, my dear students, assume one more thing. Assume one more thing. After the 80% completion of the reaction, assume one thing. After the 80% completion of the reaction, equilibrium is established. After the 80% completion of the reaction, equilibrium is established. What is meant by that? 80% completion means 80% of the reactant. 80% completion means 80% of the reactant has got converted into product. What is 80% of 10? 8. That means out of 10 moles of reactants, I would say 8 moles would have got converted into products. So I'll be left with 2 moles of reactants. And I'll say 8 moles of products would have got formed because 80% reaction is completed. Right? Now I'm assuming equilibrium is established. That means rate of forward and backward reaction now is equal. So if 1 mole of reactant is getting converted into product, at the same time, 1 mole of product is getting converted into reactant. Right? Right? If 1 mole of reactant is getting converted into product, at the same time, 1 mole of product is getting converted into reactant. Can I say moles have become constant now? Because equilibrium is established. Moles have become constant. Okay, moles have become constant. Tell me, what about the concentration? Concentration of reactant at equilibrium is 2 molar. This is 8 molar. Will these concentrations of reactant and product change with time? They are not going to change with time. These concentrations of reactants and products, they are not going to change with time because equilibrium is established. Moles of reactants and products, they have attained the fixed value. They are not going to change, right? And my dear students, can I say this is that case of equilibrium which is telling you the concentration of product at equilibrium can be greater than the concentration of reactant at equilibrium as well. So if you want to understand this whole scenario in the form of a graph, you can do that. Concentration versus time. Concentration of reactant is decreasing and is attaining a fixed value. This for reactants, right? Concentration of product is increasing and is attaining a fixed value. And is attaining a fixed value. Can I say this is a point? This is the point after which concentration of products and reactants, they have become fixed. They are not changing at all, right? So this is the point which represents your equilibrium. This is the time which is going to tell you that equilibrium is established in the reaction. And my dear students, this is that case of equilibrium which is making you understand that at equilibrium, concentration of product can be greater than that of concentration of reactant. Let me tell you, if the idea about equilibrium is done and dusted with the fire emojis. Quickly. Quickly, people. Quickly. One more thing I would want to add here. These are not only concentration versus time. Same thing happens with moles versus time curve too. If you want to draw the moles versus time, you can draw. Moles versus time curve, they can be same. Similarly, pressure versus time curve, they can be same. Pressure versus time curve in all these cases will be same. So this curve is valid for concentration versus time, moles versus time, pressure versus time, right? So tell me how many total graphs do represent equilibrium till now? These are the 3 graphs which represent equilibrium. Concentration versus time, moles versus time, pressure versus time. Similarly, 3 more, 9 graphs. And when it comes to rate versus time, there is only one graph which represents equilibrium. So do remember one simple thing from now onwards. Concentration versus time. 3 graphs are there. which I showed you, representing equilibrium, right? Moles versus time. 3 graphs represent equilibrium. Pressure versus time. 3 graphs are there which represents equilibrium, which I showed you. But when it comes to rate versus time, are there 3 curves? No, there is only one graph which correctly represents your equilibrium. Yes? Right, people, quickly in the chats if every damn thing is clear till here. Quickly in the chats, everyone. Everyone means everyone, guys, yeah? Don't be slow. Nonsense. Don't be slow. Don't be slow, guys. Someone is saying, sir, your voice is low. Guys, I'm shouting. What are you telling me? There is something wrong with your phone, and I'm not going to buy you a new phone. Yeah? You're supposed to be very active, guys. Very active. Yes, everyone means everyone. Of course. Jasima is saying, sir, why rate versus time only one graph? Because when it comes to rate, we define equilibrium in one simple statement. Rate of forward and backward reaction should be equal. We don't use the term constant there. We use the term equal. Yeah? Perfect, guys. Now, I believe the basics of equilibrium is absolutely clear to you. Now, let's move on. Let's move on. Let's move on. Let's move on to something called as the law of mass action. Guys, it might look strange to you for 5 to 10 minutes, but after 5 to 10 minutes, you would love it. Okay? Yeah? So for 5 to 10 minutes, it might look strange to you, but it's not. Okay? After some time, after 5 to 10 minutes, you'll be familiar with this properly. So what this law of mass action is all about? First of all, before making you understand its definition, let me tell you, this law of mass action, it is a theoretical concept. It is a theoretical concept. This particular law of mass action was given by 2 scientists. One is called as Goldberg, another one is called as Vage. These were the 2 scientists which gave this particular statement, which is your law of mass action. Now, what this law of mass action says? As per law of mass action is concerned, rate of reaction is directly proportional to the product of active masses of reactants raised to the powers of their respective stoichiometric coefficients. What is meant by that? Have a look. For example, people, let's say I've got the reaction like this: N1A plus N2B. It gives products. This is one reaction which I have. Imagine this is one balanced chemical equation which we have. Now, first of all, this A and B over here, I'll be calling them as the reactant. Absolutely. Your A and B is your reactant. Okay? Now, guys, as per law of mass action is concerned, rate of reaction is directly proportional to the product of active masses of reactants. What are active masses? You'll get the idea in some time. Active masses, what is meant by term active mass? You'll get the idea in some time. But remember one thing. Rate of reaction is directly proportional to the product of active mass of reactants. So it's going to be active mass of A multiplied by active mass of B raised to the powers of their stoichiometric coefficients. So what is the stoichiometric coefficient of A? It's N1. So it's raised par N1. Active mass of B raised par its stoichiometric coefficient. That's N2. So if I elaborate this a bit, if I remove this proportionality sign, there'll be a constant K, and it's going to be active mass of A raised par N1. It's going to be active mass of B raised par N2. Perfect. This is how you write the law of mass action. This is how you write exactly the law of mass action. Now, what this K over here says that, before talking about K, this R stands for the rate of reaction. Or if you want to be more precise, it gives you the theoretical rate of the reaction. What is this K? K is something which you call as a rate constant of the reaction. K is called as the rate constant of the reaction. Now, you must be thinking what these active masses are. Active mass is nothing. It is just the fancy term. It is just a fancy term. Like sometimes we use volume percentage, volume fraction, right? Okay, mole percentage. Those are all fancy terminologies. Correct? In the similar way, this ectomass, it is nothing, it is a fancy terminology, nothing else. See, what you have to remember. In general, what you have to remember. Whenever you see any reactant or product, whenever you see any reactant or product in aqueous state, in the brackets if AQ is mentioned, in the brackets if AQ is mentioned, any reactant or product, right, which is followed by AQ at the end. Let me tell you, for that reactant or product, ectomass is nothing. It is the concentration of that reactant or product. Any reactant or product which will be in aqueous state, in bracket if there is AQ mentioned, that means its ectomass is nothing, it is its concentration. Similarly, whenever you see any reactant or product in gaseous state, for gases, ectomasses are expressed in terms of concentration or in terms of pressure. So ectomass of gas can be either its concentration or you can take its pressure. Any solid or liquid in general, their ectomasses are constant. And in order to reduce the calculation, the value of this constant is taken as unity. It's taken as 1. These are the 3 things which you have to remember, nothing else. Okay? These are the 3 things which you have to remember, nothing else. Right? Any reactant or product which will be in aqueous state, its ectomass is its concentration. Gaseous state, its ectomass can be its concentration as well as pressure. Right? In pure solid or pure liquid form, its ectomass is generally constant, which is taken as 1. Okay? Yeah? Now guys, try to understand. Ashwin, you can ask him. Okay, not here. You can ask him. Why are you asking me? All right. So people, now let's try to elaborate this particular part. Try to understand what exactly I'm going to show you. Imagine that I've got a reaction. N1A plus N2B. This is N3C plus N4D. This is a reaction. First of all, tell me whether it is one reaction or these are actually 2 reactions. I'm asking you. You tell me. I'm asking you. Whether this is a single reaction or these are actually 2 reactions. I've used the term reversible here. These are 2 reactions. Forward, backward. How many? 2 reactions. Perfect. These are 2 reactions. Now, if I want to write these 2 reactions separately, you can do that. I can say N1A plus N2B. It gives N3C plus N4D. This is the first reaction. This is the forward reaction. Now, what about the backward reaction? Backward reaction is like this. N3C plus N4D. It gives N1A plus N2B. Right? So this is your forward reaction and this is your backward reaction. Perfect. Now tell me one thing. If you understood this is forward, this is backward, can I say these are the reactants, this A and B, these are the reactants of forward reaction and these are the reactants of backward reaction. I can say that. Yes, I can say that. Now people, one simple thing. If I want to use the law of mass action here as well as here, can we do that? We are in a position to do that. I can say rate of forward reaction is directly proportional to product of ectomasses of reactants. So ectomass of A multiplied by ectomass of B raised by their stoichiometric coefficient. This is N1, this is N2, right? Similarly, rate of backward reaction is directly proportional to. Here you will write ectomass of C raised by N3 and it's going to be ectomass of D raised by N4. Correct? Simple, I'm using law of mass action. Now guys, if you remove the proportionality sign, you'll get a constant here as Kf. Rest everything is same. Ectomass of A raised by N1, ectomass of B raised by N2. And here you will write rate of backward reaction. Put the constant Kb here. This is ectomass of C raised by N3, ectomass of D raised by N4. Correct? Now people, first of all, I got these terminologies here, Kf and Kb. What is meant by these terminologies? Let me tell you, this Rf stands for the rate of forward reaction. Rf stands for the rate of forward reaction. This Kf stands for rate constant of forward reaction. This is the rate constant of forward reaction. This is rate constant of forward reaction. This RB, it stands for rate of backward reaction. It stands for rate of backward reaction. And this KB, it stands for rate constant of backward reaction. It stands for rate constant of backward reaction. Now, my dear students, you tell me, when equilibrium is established, in the reaction at that point of the time, what happens? I'll say at equilibrium. When equilibrium is established in the reaction, you know, rate of forward and rate of backward reaction, they become equal. Yes, this is the criteria for equilibrium. At equilibrium, rate of forward and backward reaction, they become equal. Now, if rate of forward and backward reaction is becoming equal, what is the value of RF? RF is this. What is the value of RB? RB is this. So I can write RF is equal to nothing. It is KF multiplied by active mass of A raised power N1 multiplied by active mass of B raised power N2. It has to be equal. It has to be equal to RB. RB is nothing. It is KB multiplied by active mass of C raised power N3, active mass of D raised power N4. Correct? Correct, guys? Now this KF I'm writing as such, right? Put this KB in the denominator here, right? Is equal. This term I'm writing as such, active mass of C multiplied by active mass of D. This is raised power N1, sorry. This is raised power N3. This is raised power N4 whole divided by. This will be active mass of A raised power N1, active mass of B raised power N2. I just reshuffled this equation. Nothing else I've done. I just reshuffled this equation. KF divided by KB is equal to this term divided by this term. Now what is KF? KF is the rate constant of forward reaction. What is KB? Rate constant of backward reaction. Rate constant of forward reaction divided by rate constant of backward reaction. This is something which you call as equilibrium constant. Rate constant of forward reaction divided by the rate constant of backward reaction. Rate constant of forward reaction divided by rate constant of backward reaction. This is something which you call as equilibrium constant. And how do you write its expression? Product of active masses of product raised power stoichiometric coefficient divided by product of active masses of reactants raised power their stoichiometric coefficients. Is that clear? Say yes or no once. Say yes or no once. Say yes or no once. Right? Say yes or no once quickly. Quickly, my dear students. Quickly. So what is, if somebody asks you what is equilibrium constant, you will say equilibrium constant. It's a constant which is defined as the ratio of rate constant of forward to that of rate constant of backward reaction. Now, if I ask you, how do you write its equilibrium? How do you write its expression? How do you write the expression of equilibrium constant? You will say it's nothing. In the numerator, you will have to write the active masses of reactants raised by their stoichiometric coefficients. In the numerator, you have to write active masses of products raised by their stoichiometric coefficients. In the denominator, you have to write active masses of reactants raised by their stoichiometric coefficients. Nothing else. Nothing else. Yes? Now, try to understand this a bit more in the detailed version, detailed format. So first of all, your equilibrium constant. You got to know how to write its expression. How do we write its expression? Product of active mass of products. So active mass of C multiplied by active mass of D. This is power N3. This is power N4 divided by active mass of A power N1, active mass of B power N2. This is how you write the expression of equilibrium constant. Now, my dear students, we classify this equilibrium constant into many types. We classify this equilibrium constant into many types, right? Into many types. One is what you call as KC. One is what you call as KP. One is what you call as KX. One is what you call as KPC. But I don't use that here. We just have to study KP and KC in detail. Equilibrium constant is further classified. I'm telling you, equilibrium constant is further classified into three types: KP, KC, and KX. There is one more as well, KP, KPC, but leave that. We just have to do these two in detail. Now, I'm telling you, equilibrium constant is classified into these types. My dear students, whenever in the expression of equilibrium constants, active masses are replaced by their concentrations. For example, if I write concentration of C, concentration of D, A, B, at that point of time, your equilibrium constant, KEQ, it is replaced by Kc. Kc is nothing, it is just the equilibrium constant. Kc is nothing, it is the equilibrium constant. When active masses are taken as concentrations in the expression. As simple as that. Similarly, equilibrium constant, it becomes Kp. It becomes Kp when active masses, it becomes Kp when active masses are replaced by the term pressures. If in the expression I use pressure of C raised power n3, pressure of D raised power this, divided by pressure, right? Then Keq will be called as Kp. Then Keq will be called as Kp. Similarly, when do we use the term Kx? If instead of these active masses, I use the term. If instead of these active masses, I use the term mole fractions. Now guys, you should be in a position to write the expressions of each. If I want to write the expression of Kc, what is Kc? It is the equilibrium constant. Kc is equilibrium constant when active masses are replaced by concentrations. So how do I write this expression? I'll write concentration of C at equilibrium raised power n3 multiplied by concentration of D at equilibrium raised power n4 divided by concentration of A at equilibrium raised power n1, concentration of B at equilibrium raised power n2. Isn't this your expression for Kc? Simple? Yes. This is your expression for Kc. Similarly, if you want to write the expression for Kp, you can do that. What do you have to do? Instead of Keq, you'll write Kp is equal to active mass of C means partial pressure of C at equilibrium raised power stoichiometric coefficient. Partial pressure of D at equilibrium raised power stoichiometric coefficient divided by pressure of A at equilibrium raised power stoichiometric coefficient. Pressure of B at equilibrium raised power stoichiometric coefficient. This is your expression for Kp, nothing else. Nothing else. Similarly, if you ask me, how do you write Kx expression? Again, you should be in a position. So Kx will be nothing. Kx will be nothing. Instead of active mass of C, I'll write mole fraction of C at equilibrium raised power stoichiometric coefficient, that's N3. Similarly, mole fraction of D at equilibrium raised power stoichiometric coefficient N4 divided by mole fraction of A at equilibrium raised power stoichiometric coefficient N1, mole fraction of B at equilibrium raised power stoichiometric coefficient N2. This is how you exactly are going to write the expression for Kx. Let me know in the chats whether you can write the Kp, Kc, Kx expression for any sort of reaction. Yes or no in the chats. Everyone, don't sleep, please. Don't sleep, please. I want the chats to light up. Quickly. Quickly, people. Everyone means everyone. Everyone means everyone. Everyone means everyone. Quickly in the chats, everyone, light up. Light up the chats, people. Yes, I can see a lot of students have not liked the session yet. Guys, I want to break your fingers. Yeah, I want to break your fingers. Okay. So I believe you should be in a position to write Kp, Kc expression from now on. So if you are in a position to write Kp, Kc expression for now on, Kp, Kc expression from now on, then write the Kp, Kc expression for these. See, this is one of the reaction which is given to us. This is one more reaction which is given to us, right? First of all, gas. For gases, active mass can be concentration as well as pressure. For gases, active mass can be concentration as well as pressure. So that means you can write the expression for Kc as well as you can write the expression for Kp. Because for gases, active mass can be concentration or pressure. You're done, you're sorted. Kc is going to be, start with the product. Concentration of H2 at equilibrium raised power stoichiometric coefficient concentration of I2 at equilibrium raised power stoichiometric coefficient divided by concentration of HI at equilibrium raised power its stoichiometric coefficient. This is Kc expression. Write the Kp expression. Write the Kp expression. It is going to be partial pressure of H2 at equilibrium raised power stoichiometric coefficient, partial pressure of I2 at equilibrium raised power stoichiometric coefficient divided by partial pressure of HI at equilibrium raised to the power its stoichiometric coefficient. Right? 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 Now, my dear students, if I ask you one thing, can you calculate delta Ng for this reaction? Now, you must be thinking what this delta Ng is. It's a great term. It's a tough term. Delta Ng is nothing. It is the number of moles of gaseous products minus number of moles of gaseous reactants. Delta Ng is nothing. It is number of moles of gaseous products minus number of moles of gaseous reactants. So basically, in order to calculate delta Ng for the reaction, you will have to take that reactant and product into consideration. You will have to take that reactant and product into consideration, which will be in gaseous state. Lucifer is writing, Ahmed sir, chemistry is the GOAT. Absolutely. He is one of my very good friends. He's a wonderful teacher. You can tell him my name, okay? He's a wonderful teacher, right? He's an elder brother who you are talking about, yeah? Ask him about me. He'll tell you who you are talking to. Okay, so number of moles of gaseous products. See, this particular product, number of moles of gaseous products. So look at the products first, right? Stoichiometric coefficient 1 and 1. So 1 plus 1 is 2. So number of moles of gaseous products is 2 minus number of moles of gaseous reactant. This is gaseous reactant, so its moles are 2. So 2 minus 2 comes out to be 0. So delta Ng for this reaction comes out to be 0. Yeah? Right? Now people, look at this particular expression. This is aqueous, this is aqueous, this is aqueous, right? For aqueous, active mass is concentration, right? Active mass is concentration. Yeah? So write the expression for Kc. You cannot write the expression for Kp because these are aqueous. These are aqueous. You cannot write the expression for Kp. You can write the expression for Kc though. So Kc is going to be, Kc, it's going to be concentration of NH4 positive at equilibrium raised power stoichiometric coefficient, concentration of OH negative at equilibrium raised power stoichiometric coefficient divided by concentration of NH4OH at equilibrium raised power stoichiometric coefficient. This is how you are going to write the expression of Kc. Agreed? 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 Agreed, people? Okay. Take few more examples so that everything looks damn clear to you. Okay. See, this is gaseous, this is gaseous, this is gaseous, right? So you can write the expression for Kc as well as Kp, right? Now people, write the expression for Kc first of all. Kc is going to be concentration of Hi at equilibrium raised power stoichiometric coefficient divided by concentration of H2 at equilibrium raised power stoichiometric coefficient, concentration of I2 at equilibrium raised power stoichiometric coefficient. Done, understood? Try to write the expression for Kp. It's going to be partial pressure of Hi at equilibrium raised power coefficient divided by partial pressure of H2 at equilibrium raised power coefficient, partial pressure of I2 at equilibrium raised power coefficient. Yes? Tell me the delta Ng. What is delta Ng for this particular reaction? Number of moles of gaseous products, that is 2, minus number of moles of gaseous reactants, which is 1 plus 1, 2, which makes it 0. Done, understood? Right? Look at the next reaction. You should be in a position to write all these things again. So first of all, write the expression for Kc. It's going to be concentration of PCl3 at equilibrium raised power coefficient, concentration of Cl2 at equilibrium raised power stoichiometric coefficient, concentration of PCl5 at equilibrium raised power stoichiometric coefficient. Write the expression for Kp. It's going to be partial pressure of PCl3 at equilibrium raised power stoichiometric coefficient, partial pressure of Cl2 at equilibrium raised power coefficient divided by partial pressure of PCl5 at equilibrium raised power coefficient. Yes? Simple? Simple. Tell me one thing. What about delta Ng for this particular reaction? Delta Ng, number of moles of gaseous products. These two are gaseous products. So 1 plus 1 makes it 2 minus moles of gaseous reactants. That's 1. So this value will come out to be 1. Yes? Simple and basic. Simple and basic, people. I believe you should be in a position to do all these things from now on. Quickly, guys, quickly. Everyone. All right, look at this particular reaction. Now here, this is solid, this is solid. For solids, their ectomass is unity. They're constant. Ectomass are constant. So I have got nothing to do with these solids. I've got nothing to do with these solids. I've got something to do with gas. So write Kc. Kc is going to be simply concentration of carbon dioxide at equilibrium raised by stoichiometric coefficient. Similarly, write the expression for Kp. Kp is going to be partial pressure of carbon dioxide at equilibrium raised by stoichiometric coefficient. Okay, delta Ng for this reaction, it is going to be number of moles of gaseous products. This is not gaseous. This is gaseous. Its coefficient is 1 minus number of moles of gaseous reactant. There is no gaseous reactant. So delta Ng for this reaction is 1. Okay, correct? Look at this particular reaction. This is solid. Nothing to do with this gas. This is gas. This is gas. So consider them. So write Kc expression first of all. Kc is going to be concentration of SO3 at equilibrium raised by coefficient divided by concentration of O2 at equilibrium raised by coefficient. Nothing else. Okay. Kp expression is going to be partial pressure of SO3 at equilibrium raised by coefficient divided by partial pressure of O2 at equilibrium raised by coefficient. Nothing else. Okay. So tell me, what about the value of delta Ng for the reaction? It has to be number of moles of gaseous products, that's 1, minus number of moles of gaseous reactant, that is 3 divided by 2. The value comes out to be minus 1 by 2. This is the delta Ng for the reaction. This is the delta Ng for the reaction. Right? This is the delta Ng for the reaction, people. I believe you can easily write Kp and Kc expressions from now onwards for anything. Okay? Now comes a main topic. Before doing this particular topic, tell me once in the chats if all the things are very, very, very much clear to you. Very much clear to you. Yes? Guys, till now, whatever I was teaching you, that was complete basics. Now we are going to scale up the level. Someone is asking why you are calculating delta Ng. Now you'll get to know why I was calculating delta Ng. Okay? Now you'll get to know why I was calculating delta Ng. And I think electricity will go off and we have to introduce the night mode soon. And one important thing, please and please do not ask for the break till 8. Do not ask for the break till 8. Okay? Ramesh is asking all naming reactions. I have told you that we'll cover everything. Today it's day 18, 17 chapters are done. We have a lot more to do. Okay? We are not stopping yet. Perfect. Perfect, guys. I have not covered thermodynamics yet. Thermodynamics will be the next chapter after this. Okay, perfect. What is the relation between Kp and Kc? This is one important topic, so try to understand very, very, very carefully. Here I have to teach you some concepts as well. Have a look, guys. For example, imagine I have got a gaseous phase reaction like this. N1A gas, it's in equilibrium with N2B gas. Imagine this is your gaseous phase reaction. The first thing which I want you to do to calculate the value of delta Ng. Delta Ng means number of moles of gaseous products, that's N2, minus number of moles of gaseous reactants, that's N1. Basically, I had a balanced chemical equation in which N1 and N2 were the stoichiometric coefficients, so delta Ng came out to be N2 minus N1. Very simple. Now, If I would want to write the expression for Kc, I can do that. Expression for Kc is going to be concentration of B at equilibrium raised power n2 divided by concentration of A at equilibrium raised to the power n1. Okay. Write the expression for Kp. Kp expression is going to be partial pressure of B at equilibrium raised power n2 divided by partial pressure of A at equilibrium raised power n1. Now, the first thing which I want to make you understand, what is meant by the term partial pressure of B and partial pressure of A. What is partial pressure of B at equilibrium? What is partial pressure of A at equilibrium? Guys, try to understand. Try to understand. First of all, imagine this particular reaction is taking place in a closed container. Imagine this particular reaction is taking place in a closed container. At time t is equal to 0, initially, when the reaction has not started, tell me how many gases will be there in this container. When the reaction has not started, initially at time t is equal to 0, tell me how many gases will be there in the container. There'll be only a reactant. There'll be only gas A present in the container. There'll be only one gas. There'll be only one gas in the container. That is gas A at time t is equal to 0, right? Because reaction has not started yet. Now you tell me, when the reaction starts, moles of reactants will keep on decreasing. Moles of products will keep on increasing. So tell me, when equilibrium will be established in the reaction, how many gases will be there? Will there be only A, only B, or both? Tell me that. Can I say, when equilibrium is set in the reaction, there'll be two gases. There'll be some moles of gas A left. There'll be some moles of gas B, which would have got formed. So these are the two gases present in this container at equilibrium, right? Perfect. So tell me one thing. Can I say at equilibrium, there is not one gas? At equilibrium, there is a gaseous mixture in the container. At equilibrium, there is a gaseous mixture in the container. At equilibrium, what do we have? There is a gaseous mixture in the container. If there is a gaseous mixture in the container, as per Dalton's law, the total pressure of the mixture at equilibrium, can I say the total pressure of this mixture, is it going to be due to only A, due to B, or I would say both will contribute towards total pressure? Can I say both these gases at equilibrium will contribute towards the total pressure of the mixture at equilibrium, right? Both will contribute towards the total pressure, okay? Which will be equal to, I'll say total pressure of the mixture at equilibrium is equal to contribution made by gas A towards the total pressure, plus contribution made by gas B towards the total pressure. So basically, I'm taking the sum of the contributions. I'm taking the sum of contributions made by each gas. This is what your Dalton's law is all about. And this PA, the contribution made by gas A towards the total mixture, is what you call as partial pressure of A. This is something which you will be calling as partial pressure of B. And both are right here at equilibrium. So partial pressure of A at equilibrium, partial pressure of B at equilibrium. Now, I need not to tell you all this. I just need to tell you one thing. I just wanted to make you understand what is partial pressure. Partial pressure is nothing. It is a contribution made by gas towards the total pressure of the mixture, right? So partial pressure of gas A will be equal to, as per formula, it is equal to total pressure of the mixture at equilibrium. Total pressure of the mixture at equilibrium. Partial pressure of gas A at equilibrium is equal to total pressure of the mixture at equilibrium multiplied by mole fraction of A at equilibrium. This is the result. Similarly, partial pressure of B at equilibrium will be equal to total pressure of the mixture at equilibrium multiplied by mole fraction of B at equilibrium. So partial pressure is nothing else. Total pressure multiplied by mole fraction. Nothing else. Okay. So again, I'm repeating one thing. Initially, at time t is equal to 0, there will be one gas in the container. At equilibrium, there are two gases. So there is a mixture at equilibrium. The total pressure of that mixture is PT equilibrium. And that PT equilibrium will be due to A as well as B, right? Contribution made by A towards the total pressure of the mixture at equilibrium is called as partial pressure of A. contribution made by gas B towards the total pressure of the mixture is called as partial pressure of B. As simple as that. Now guys, now try to understand one more thing. I am pretty much sure you would have studied ideal gas equation somewhere. PV is equal to nRT. PV is equal to nRT. Can I write P is equal to N divided by VRT? I can do that. Can I say P is equal to N by V, moles per unit volume, concentration, multiplied by R, multiplied by T? I can say it, right? I can say it, right? So, if I write PA, partial pressure of A is going to be concentration of A, RT. Partial pressure of B is going to be concentration of B and RT. Right? Simple? Simple? Now people, can I write something like this now? KP. KP is equal to, KP is equal to, KP is equal to, instead of partial pressure of B, instead of partial pressure of B, can I write concentration of B multiplied by R multiplied by T? So instead of partial pressure of B, I'm using concentration of B at equilibrium multiplied by R multiplied by T, whole raised power stoichiometric coefficient, that's N2, divided by. Instead of partial pressure of A, I'm using concentration of A at equilibrium. This is R, this is T, raised power stoichiometric coefficient, that's N1. Correct? Now people, try to understand. I'm going to reshuffle this equation like this. I'll be writing concentration of B at equilibrium, raised power N2, separately I'm writing, divided by concentration of A at equilibrium, raised power N1, separately I'm writing. This is the RT raised power N2, this is RT raised power N1. So it is going to be RT raised power N2 minus N1. Bases are same, powers are subtracted in division. So I'll say your Kp is nothing, it is equal to this particular term, concentration of B raised power N2, concentration of B raised power N2, concentration of A raised power N1, concentration of A raised power N1. So this particular term I'll be calling as Kc, right? This is going to be RT and raised to the power. What is this N2 minus N1? N2 minus N1 is something which you call as delta Ng here. So I got one very important result for a gaseous phase reaction. For a gaseous phase reaction, Kp is equal to Kc RT raised power delta Ng. Yes? Right guys? Right guys? So I took a reaction like this, N1A gas in equilibrium with N2B gas. Right? N2B gas. What is going to be the relation between its Kp and its Kc? We got to know your Kp is equal to Kc RT raised to the power delta Ng for this particular reaction. Is it clear? Is it clear? Now, if this is clear, there is something which is important. I'm not sure whether you would have studied that or not. Look at this particular result. Relation between Kp and Kc. Try to understand one simple thing. What is the value of R? What is the value of R? R value, you must be knowing, it is 0.0821, or you can write it as 1 by 12. 1 by 12 atm liter per Kelvin per mole. Correct? This is the value of your R. 1 by 12 atm liter per Kelvin per mole. Over here in the bracket, do we have R or we have RT? We have RT. Okay, we have RT. Try to understand carefully what I say. If by chance this particular reaction is taking place at temperature 12 Kelvin. Imagine this particular reaction is taking place at temperature 12 Kelvin. Is taking place at temperature 12 Kelvin. What is the value of R? R is 1 by 12. What is the value of? My Siri is talking here from the phone. Okay. See guys, try to understand. If this reaction takes place at temperature 12 Kelvin, okay, what will be the value of RT? R value is 1 by 12. So 1 by 12 multiplied by 12, temperature is 12. This value comes out to be 1. So RT is 1. RT is 1. 1 raised per anything is always 1. 1 raised per anything is always 1. Therefore, Kp and Kc will be always equal. So that reaction which will be carried out at temperature 12 Kelvin. That reaction which will be carried out at temperature 12 Kelvin. Do remember its Kp and Kc will be always equal. Irrespective of delta Ng. Whatever delta Ng is, leave that, nothing to do with that. If the reaction is carried out at 12 Kelvin, its Kp and Kc will be equal. Its Kp and Kc will be equal. Number one. Number two. If the reaction is carried out at temperature greater than 12 Kelvin, if the reaction is carried out at temperature greater than 12 Kelvin, so R value you know, it's 1 by 12. Temperature right now, it's greater than 12. Keep it as 13. So R multiplied by T, this value will be greater than 1. R multiplied by T value will be greater than 1, right? So if temperature is greater than 12 Kelvin, so RT value will be definitely greater than 1. RT value will be greater than 1. Now, my dear students, if RT value, if this is greater than 1, if this is greater than 1 now this particular term is greater than 1, it can be 2, 3, whatever, right? Now, few cases arise here. First case is if delta Ng will be greater than 0. If delta Ng will be greater than 0, this is already greater than 1. Now, this is greater than 0. That means at that point of time, mathematically, your Kp will be greater than Kc. As simple as that. If delta Ng will be less than 0, this particular term, this is greater than 1. This is less than 0. Greater than 1, less than 0. So at that point of time, I can say Kp will be less than Kc. And if by chance, delta Ng for the reaction will be 0. If delta Ng for the reaction is 0, this is greater than 1. Anything raised power 0 is 1. So at that point of time, your Kp and Kc will be equal. Your Kp and Kc will be equal. But do remember, this is the criteria which is only valid when temperature is greater than 12 Kelvin. Now. What is the case 3? What is the case 3? Tell me the case 3, people. What has to be the case 3 here? Case 3. If by chance this particular reaction is carried out at temperature less than 12 Kelvin, at that point of time, R multiplied by T will be less than 1. Agreed? At that point of time, R multiplied by T will be less than 1. Now, here also few cases arise. First case, if delta Ng is greater than 0. See, now this term is less than 1. This term is less than 1. This term is greater than 0. So at that point of time, mathematically, what you'll observe? You'll observe Kp will be less than Kc. Similarly, if delta Ng for such a reaction is less than 0, accordingly, you'll find Kp greater than Kc. And one thing is already clear. If delta Ng is equal to 0, at that point of time, whatever the temperatures are kept, Kp and Kc will be equal. So do remember, this is something I'm not sure whether you have studied before or not. Okay, so do remember these things. Do remember these things. Is it clear? Is it clear, people? Quickly in the chats, everyone. Yeah? This is one very important point. One very important point. You do not get to see all these things frequently when it comes to your NEET examination. In JEE, it is much needed. Okay? Now, guys, there is one more thing. Since we are discussing Kp-Kc relation, right? Since we are discussing Kp-Kc relation, you got to know your Kp is equal to Kc RT raised power delta Ng for a gaseous phase reaction, right? Okay? Now, people, if I multiply this equation by the term log, and I say it becomes log of Kp will be equal to, this becomes log of Kc multiplied by RT raised power delta Ng for a gaseous phase reaction. Absolutely. So I can say your log of Kp is equal to log of m into n. Log of m into n means log of m plus log of n. Plus log of n. Correct? Now, slightly I'll modify this equation. Log of Kp is equal to log of Kc plus, this is log of m raised power n, which is going to be n log m. So it is delta Ng, and it's going to be log of what? It's going to be log of RT. Now, my dear students, why did I show you the logarithmic form here? Imagine you have to plot a graph between log of K versus the log of RT. Imagine you have to plot a curve between log of Kp versus log of RT. You should be able to draw it. If this is Y, this is X, this I'll be calling as M, and this whole term I'll be calling as C. In between the sign is plus. Here is equal to, Y is equal to mx plus C. Y is equal to mx plus C. Tell me the nature of the curve. This is your Y, and this is your X, and Y is equal to mx plus C. It's going to be a straight line, absolutely, with some intercept. Okay. If you ask me, what is the slope of this particular curve? Slope means m. M here is delta Ng. M here is delta Ng. If you ask me, what is the intercept? Intercept is represented by C, and C here is equal to log of Kc. It is the log of Kc, right? And over y-axis, what did I plot? It is basically the graph between log of Kp versus log of Rt. It is basically the graph between log of Kp versus log of Rt. You should know this as well. Is it clear, people? Is it clear? Sometimes there will be a graph given, and from the graph you will have to calculate delta Ng. So whatever is the slope of this graph, that's going to be the delta Ng of the reaction. Nothing else. Done and dusted. Yes? Is it clear? Is it clear, people? Is it clear? By the way, did you see tomorrow's thumbnail? I laughed when I saw that. Did you see the tomorrow's thumbnail? Yes, Tiger, we'll be doing that. The session which I'm going to take tomorrow. Did you see that thumbnail? I actually laughed. It's cute, right? I hope you can see it. Yeah. Well, this is completely AI thumbnail. I did not wear this dress. I did not wear this dress, okay? If this is visible to you, somehow, let me tell you, I did not wear this dress. This is completely AI generated thumbnail, okay? I was shocked when I saw it. Like, when did I wear it? Yeah, and it's going to be a good surprise for all of you tomorrow. Join that session tomorrow at 8 p.m. Okay? Yes, I wanted... See, I was not supposed to change my beard color. If they wanted, they could have changed it on their own. It is AI nowadays, yeah. They should have kept white beard. Even I asked them, change it, keep white. But I don't know why they did not do that. Okay, so let's move on. So this was your relation between Kp and Kc, right? Which is very important. I hope all the parameters which I told you, all are perfectly clear. Now, that's not it. That's not it. There is one more thing. If you ask me what is the relation between Kp and Kx, right? There must be some relation between Kp and Kx as well. See, Kp-Kc relation we generated. What about Kp and Kx? That's again important. That's again important. Till now, you were never asked questions from this particular topic, but they might now because the level has increased. Level has increased. It's not going to be same anymore. Okay? So see guys, for example, you have got a gaseous phase reaction like this. N1A gas, it is in equilibrium with N2B gas. This is my reaction, a gaseous phase reaction. So first of all, my dear students, tell me the value of delta Ng for this reaction. It is the number of moles of gaseous products, which is N2 minus the number of moles of gaseous reactant, that's N1. So this is the delta Ng for the reaction. This is the delta Ng for the reaction. Now people, I would want you to write the expression for Kp as well as Kx. And you are in a position to write these expressions. Kp will be equal to, it's going to be partial pressure of B at equilibrium raised par stoichiometric coefficient divided by, it's going to be partial pressure of A at equilibrium raised par stoichiometric coefficient, right? Kx expression is going to be mole fraction of B at equilibrium raised par stoichiometric coefficient divided by mole fraction of A at equilibrium raised par stoichiometric coefficient, right? This is something which we have discussed already. Okay. Now guys, again I'm asking you one simple question. Tell me, when equilibrium is established in the reaction, at that point of time, will you see only one gas in the container or there'll be two gases? Quickly, everyone, quickly. When equilibrium is established in the reaction, will there be only one gas in the container or two gases? There will be. Flood the chats. There will be two gas in the container. So can I say at equilibrium there'll be a mixture of gas? At equilibrium there'll be a mixture of gas, right? That mixture of gas will be containing some moles of A left and some moles of B which had got formed. So at equilibrium, we have got a mixture. Let's assume total pressure of that mixture is Pt. This is the total pressure of the mixture. This is the total pressure of what? Of the mixture, of the gaseous mixture at equilibrium. Is this total pressure going to be only due to A, only due to B, or both will contribute? Both will contribute. A as well as B would have contributed. Contribution made by A towards the total pressure of the mixture is called as partial pressure of A. Contribution made by B towards the total pressure of the mixture is partial pressure of B. right? Now, what about partial pressure of A at equilibrium? Partial pressure of A will be equal to total pressure of the mixture at equilibrium multiplied what? Multiplied the mole fraction of A at equilibrium, right? Similarly, partial pressure of B at equilibrium, you can write that. You can do that. Now, tell me one thing. Kp is equal to partial pressure of B at equilibrium can be written as total pressure at equilibrium multiplied by mole fraction of B at equilibrium raised to the power stoichiometric coefficient, that is N2, divided by partial pressure of A at equilibrium is nothing. It is total pressure of the mixture at equilibrium, mole fraction of A at equilibrium raised to the power the stoichiometric coefficient, that's N1. That's N1. Yes, that's N1. That's N1. That's N1. Now try to simplify this a bit. See, PT. I'll be writing something like this. This I'm writing separately. Mole fraction of B at equilibrium raised to the power N2 divided by. This I'm writing separately. This is going to be mole fraction of A at equilibrium raised power stoichiometric coefficient N1. Correct? This is PT raised power N2. This is PT raised power N2. Sorry, this is PT raised power N1. So bases are same, powers are subtracted in division. So PT at equilibrium raised power N2 minus N1. Right? Simple maths I'm using, nothing else. Nothing else. So I'll be writing it further here. Kp is equal to. This particular term is what you call as Kx. Right? Kp is equal to Kx. And this is total pressure of the mixture at equilibrium raised to the power N2 minus N1 is nothing. That's delta Ng. So you got one more important result. Right? Which is the relation between Kp and Kx. This is the relation between Kp and Kx. Kp is equal to Kx, Pt raised power delta Ng. Right? So I can say something like this. Kp is equal to Kx, total pressure at equilibrium raised power delta Ng. This is the relation between Kp and Kx for a gaseous phase reaction. Now guys, here are certain things. What are certain things? See, look at its logarithmic form. If I multiply throughout with log, it becomes log of Kp is equal to log of m into n is going to be log of m plus log of n. Log of m plus log of n. Now further, if you want to reduce it, log of Kp is equal to, it's going to be log of Kx plus log of m raised power n. It's n log m. So delta Ng comes to the front, then it's going to be log of Pt. This is your logarithmic form. And if this is your logarithmic form, if you would want to plot a graph, and the graph is between log of Kp versus log of Pt, you again should be in a position to make this graph. You should be in a position to make this graph, people. Have a look. Log P, you are plotting along y-axis. Right? Log Pt, you are plotting along x-axis. This is going to be your m. And this whole term is going to be your c. In between sign is plus. This is equal to y is equal to mx plus c. Right? If you ask me, sir, what about the slope of the curve? Slope is nothing m. M is nothing, that's delta Ng. Now at the same time, if you ask me what about the intercept means c, and c here is nothing, it's the log of kx. Right? So this is your one more graph. Sir, who will take hydrocarbon? I have no idea who will take hydrocarbon. Let's see. We have not discussed yet. Me and HSP, sir, we have not discussed yet. Let's see who wants to take hydrocarbon. First of all, we discuss. Whatever chapter is my favorite, I take that. Whatever chapter is his favorite, he takes that. Because it's better. We both take our favorite chapters so that we give you the best content. Right? If I do not take my favorite content, maybe I'll just skip certain things. If he does not take his favorite chapter, maybe he'll skip certain things. Yeah? So understand in those parameters. Okay? Yeah? Am I logical? What do we want here? We want the best content, right? Best content on YouTube. So for the best content on YouTube, definitely both the teachers, whosoever, 2 physics teachers are there, 2 bio teachers are there, 2 chemistry teachers are there. Like in every subject, favorite chapters are taken by the teachers. I hope I'm clear. Now you cannot say a single word after this, right? Because the explanation which I gave you, I mean, there is no second thought to this explanation. You cannot say a single thing after this. Even I liked this explanation. HSP Baba is OP. Everyone in the chats, Baba HSP OP. Baba HSP OP. Do you want to talk to him? Do you want to talk to Baba HSP? Say yes or no. Maybe I can call him if he picks my call up. He's a super senior teacher. Yeah? Do you want to talk to your Baba HSP? Should I be calling him? Let me see if he picks up. I don't know where he will be. Maybe he'll be celebrating Christmas somewhere. सर जी क्या हाल चाल? सर जी क्लास में हूँ, लाइव सेशन में हूँ, यूट्यूब पे हूँ, तो बच्चे बोल रहे हैं HSP सर से बात करनी है. स्पीकर पे मैंने फोन रखा है. क्या हाल चाल? कुछ बोल दो बच्चों को यार.
Hey everyone, hi dear students.
अरे आप यूट्यूब पे नहीं हो, मतलब ऐसे ही बात कर रहे हो जैसे फोन पे बात कर रहे हो.
अच्छा.
नहीं बच्चे सुन रहे हैं, बट बच्चे सुन रहे हैं.
नहीं तो यूट्यूब पे हो, कहाँ पे हो?
मैं अभी यूट्यूब सेशन ले रहा हूँ.
हाँ
ठीक है. और मैंने आपका फोन स्पीकर पे रखा हुआ है.
ओके.
बच्चे सुन रहे हैं. ठीक है. तो आप जरा कुछ बताइए अपनी लैंग्वेज में, कुछ शायरी वायरी सुनाइए इनको.
चलो सुनाता हूँ. देखो बच्चा लोग रियली बहुत हार्ड वर्क कर रहे हैं. these kids are really doing hard work. तो इन समय इनको कंफर्ट नहीं मिल रहा होगा. तो हिंदी में कहते हैं, कभी किसी को मुकम्मल जहां नहीं मिलता, कभी जमी तो कभी आसमां नहीं मिलता.
Wow. Guys, I cannot translate this in English. सर आप नेक्स्ट चैप्टर कौन सा उठा रहे हैं?
कोऑर्डिनेशन केमिस्ट्री.
So sir's next chapter is going to be coordination chemistry, okay? Sir told one of the shairi, but I'll be unable to translate it. I'm not so good in the English. Maybe somebody can do it in the chats.
केमिकल इक्विलिब्रियम बता दो ना कि लिक्विड वाटर is not having freedom, but gaseous H2O is having freedom, but not that stability.
Oh wow. See, he gave you one concept as well. I told you he's Baba of chemistry, right? He is our Baba of chemistry. चलो यार सर जी मिलते हैं, ठीक है.
हैप्पी क्रिसमस, मैरी क्रिसमस बोलना मेरी तरफ से.
हाँ, मैरी क्रिसमस. सर इज सेइंग मैरी क्रिसमस. Yes. Thank you so much, sir. You carry on, no? Tata. Bye. See you. Baba is always up for a call. Okay, perfect. So guys, this was the graph between log Kp and log Pt, right? Now guys, one thing is there. See, I gave you two relations. One was the relation between Kp, Kc. One is the relation between Kp, Kx, right? The first relation was your Kp is equal to Kc RT raised to the power delta Ng for a gaseous phase reaction. Similarly, one more relation was Kp is equal to Kx. Kp is equal to Kx, total pressure at equilibrium raised to the power delta Ng. Correct? Let's call this as equation number 1. Let's call this as equation number 2. Now. Kp is this. So I can equate both. And when you equate both, what do we get? We get something like this. Kc, this is RT raised to the power delta Ng. It has to be equal to Kx, this is Pt raised to the power delta Ng. Perfect. Now guys, try to understand what exactly I'm going to say. I'll write Kc is equal to, or let me write it like this. I can write Kx is equal to Kc. RT I'm writing as such. Pt I'm taking the denominator, and delta Ng I'm taking common. You can remember this relation in this format, or if you don't want to remember it in this format, then remember it in one more format. You can write Kc is equal to Kx. Now Pt in the numerator, RT in the denominator, whole raised power what? Whole raised power delta mg. So this is going to be your relation between Kc and Kx as well. This is the relation between your Kc and Kx as well. Yeah? This is your relation between Kc and Kx as well. Now, the logarithmic form. If I multiply with the log throughout, what do I get? I get a log of Kc is equal to log of m multiplied by n. Log of m into n is nothing. That is log of m plus log of n. So log of Kx plus log of Pt divided by RT whole raised power delta mg. Right? If you further want to elaborate a bit, it's going to be log of Kc is equal to, this is going to be log of Kx plus log of m raised power n is n log m. So delta ng comes to the front. Then it's going to be log of Pt divided by RT. Pt divided by RT. So this is your logarithmic form. This is your logarithmic form, people. This is your logarithmic form. If this is your logarithmic form, then you can plot a graph. And I want you guys to let me know the nature of the graph. So log of Kc versus log of Pt divided by RT. So tell me, what will be the nature of this particular curve? What will be the nature of this particular curve? Log of Kc versus log of P by RT. Quickly. This is your y. You are plotting it along y-axis. This term, you are plotting along x-axis. This is going to be your m. This is going to be c. Y is equal to mx plus c. Y is equal to mx plus c. Straight line with the positive slope and some intercept. So the curve is like this. Now, if you ask me what is the slope exactly, slope is nothing, that's delta ng. And the intercept is denoted by c. And this was your value of c, which is log of kx. Correct? So my dear students, these were three graphs which can be asked. These were three graphs which can be asked from your KP-KC relations and their logarithmic relations. Is every single thing clear till here? Is every single thing clear till here? Then I can move on to few questions, few basic questions. Few basic questions. I told you, slowly we'll cover up everything, right? Slowly in detail. Write the KP expression for the following in terms of Kc. For every reaction, you have to write Kp in terms of Kc. You have to write Kp in terms of Kc. Look at the first reaction. For the first reaction, if I ask you what is delta Ng, delta Ng is equal to number of moles of gaseous products minus number of moles of gaseous reactants. So 1 plus 1 is 2. 2 minus 2 is 0. So delta Ng is 0, right? For any reaction whose delta Ng is 0, its Kp and Kc will be always equal. For any reaction whose delta Ng is 0, its Kp, Kc will be equal. Question number 1 done. Look at the second one. Calculate delta Ng for the second reaction. Delta Ng is equal to number of moles of gaseous products, which is 1 plus 1, that is 2, minus number of moles of gaseous reactant, that's 1. So 2 minus 1 comes out to be 1. So Kp-Kc relation, I'll say Kp is equal to Kc RT raised to the power delta Ng, that's 1. Right? This is your one more answer. This is your one more answer. Right? Look at the third question, people. Look at the third question. Calculate delta Ng for this reaction. Delta Ng is equal to number of moles of gaseous products, which is 2, minus number of moles of gaseous reactants, which is 1 plus 3, that is 4. So the value is minus 2. So delta Ng is minus 2. So Kp is equal to Kc RT raised by delta Ng, which is minus 2. So this is the relation between Kp, Kc here. Similarly, the fourth case. First of all, calculate delta Ng for the fourth reaction, which is number of moles of gaseous products, which is 1, because this is solid, this is solid. So delta Ng is 1. If delta Ng is 1, your Kp is equal to Kc RT raised by delta Ng, that's 1. My dear students, do you know, 2 years back, one direct question was asked from this. Let me show you that direct question. But that direct question was asked in JEE mains, and you laugh at that. I'm pretty much sure you'll laugh at that question. I have noted that question somewhere. I've noted that question. Yes. This was your JEE mains question. Look. Integer type question this was. Reaction was given. Kp is equal to Kc RT raised by x. Calculate x. Solve it. Tell me the value of x quickly. Tell me the value of x quickly. Everyone. Everyone means everyone, okay? Everyone means everyone. You know it. Everyone means everyone. You know it. Yeah? Quickly, guys, everyone. Everyone means sab log. What is the value of x? What is the value of x? Guys, just give me a second. Hello? Okay. Perfect. The value of x is? See guys, I just need to calculate what? I just need to calculate delta Ng, right? So delta Ng for this reaction will be number of moles of gaseous products, which is 1, minus number of moles of gaseous reactant, which is 1 plus 1 by 2, makes it 3 by 2. So this is equal to minus 1 by 2. Now you know, as per your relation, Kp is equal to Kc. This is RT raised by delta Ng. Delta Ng is coming out to be minus 1 by 2. Now as per the equation, Kp is equal to Kc, RT raised by x. Now compare these two equations. Compare these two equations, get the value of x. X value is nothing, that's minus 1 by 2. Right? One simple and basic equation this was. One simple and basic equation this was. Let's go back to our things again. I hope till here everything is clear. Now guys, you must be thinking, what are going to be the units of Kp, Kc? Till now, I'm not solving many questions yet. Questions are yet to come. First, I want your basics to be very, very, very strong, right? So that you can kill the questions afterwards. Units of Kp and Kc. What are going to be the units of Kp, Kc? This is again a very simple and basic topic. See guys, try to understand. For example, you have got a reaction like this. N1A gas in equilibrium with N2B gas. This is a gaseous phase reaction, for example. This is, for example, a gaseous phase reaction. If I ask you what about the delta Ng value, you'll directly say it is N2 minus N1, delta Ng, right? If I ask you what is the expression for Kc, you'll directly write concentration of B at equilibrium raised by N2 divided by concentration of A at equilibrium raised by N1. Yes? Similarly, if I ask you what is the expression of Kp, you will say partial pressure of B at equilibrium raised by N2 divided by partial pressure of A at equilibrium raised by N1. This is how you are going to write. This is how you are going to write Kp, Kc expression. Now guys, it's pretty much simple. Kc is equal. In the numerator, you have got a term concentration. What is concentration? Moles per unit volume. So what is the unit of this particular term? Unit of the numerator is moles per liter. Raised by what? Raised by N2. In the denominator, again it's going to be what? Moles per liter. Raised by what? Raised by N1. Yes? Now guys, you are done. So it's going to be moles per liter raised to the power N2 minus N1. N2 minus N1 is nothing. That's your delta Ng, right? So this is the unit of your Kc for a gaseous phase reaction. This is the unit of your Kc for a gaseous phase reaction. Now, what is going to be the unit of Kp for a gaseous phase reaction? Pressure, pressure. Let's assume pressure is in atm. So this is atm raised by N2. In the denominator, it is atm raised by N1. So it is going to be atm raised to the power N2 minus N1. Or you can say Kp units are nothing. If pressure is in atm, it's going to be atm raised by delta Ng. Done and dusted for a gaseous phase reaction. Yes? Right, people? I hope every single thing is clear till here. Let me know once in the chats. I hope you got the relation. I mean, you got the Kp, Kc units as well. I hope you got the Kp, Kc units as well. Is every single thing clear? Then only I can move on to something important from which basic questions are asked, and you will love those questions. You will love those questions, people. Try to have a look. Characteristics of equilibrium constant. Characteristics of equilibrium constant. The first and the most important characteristic. Equilibrium constant, it is independent of the initial concentration of reactants. Equilibrium constant, it is independent of initial concentration of reactants. Why is that? Why equilibrium constant is independent of initial concentration of reactants? Why is that? Guys, it's pretty much simple. When you write the expression for equilibrium constant, for example Kc, how do you write it? Concentration of product at equilibrium raised by stoichiometric coefficient divided by concentration of reactant at equilibrium raised by stoichiometric coefficient. This is how you write equilibrium constant expression. Now you see, in this equilibrium constant expression, whatever concentrations we take, these are the concentrations of reactants and products at equilibrium. These are not the initial concentrations of reactants. Right? Right? Whenever we calculate equilibrium constant, we need concentration of reactants and products at equilibrium. We do not need the initial concentration of reactants. So I would say your equilibrium constant, it does not depend on the initial concentration of reactants. It depends on what? Concentration of reactant and product at equilibrium, basically. Yes? Point number one. Point number two. Catalyst. I'm talking about the positive catalyst, which speeds up the reaction. What does a catalyst do? What does a positive catalyst do? Positive catalyst speeds up the reaction. And let me tell you, positive catalyst, it speeds up forward as well as backward reaction. Positive catalyst speeds up forward as well as backward reaction. Due to which, if forward reaction and backward reaction is speeded up, if it is speed up, what will happen? I'll say equilibrium will be established in the reaction quickly. Right? Imagine it like this. In absence of catalyst, let's say equilibrium was coming in the reaction after 20 seconds. In presence of catalyst, imagine equilibrium is coming in just 5 seconds. So what is catalyst doing? What is catalyst doing? It is just speeding up the forward and backward reaction, due to which equilibrium is established in the reaction quickly. Whether the equilibrium comes in a reaction late or comes quickly, will it change the equilibrium concentrations? It will not change the equilibrium concentrations. If equilibrium concentrations are not changed, I would say catalyst does not do anything to the equilibrium constant. Right? Catalyst does not do anything to the equilibrium constant. Catalyst just speeds up the reactions, forward as well as backward, due to which equilibrium comes early. But nothing happens to the equilibrium concentrations. They are still the same. Right? Remember this particular point. Even this point. Your equilibrium constant, it depends on temperature. Equilibrium constant, this is important. It depends on temperature. But right now, I won't be explaining this. I'll be explaining this after some time when I'll be teaching you Lee-Chatelier's principle. Right? Equilibrium constant, it depends on temperature. Equilibrium constant changes on changing the temperature. How it changes, that is something which I'll be teaching you in Lee-Chatelier principle when I'll be teaching you the Van 't Hoff's equation. Okay, after some time. Now guys, equilibrium constant depends on the stoichiometric coefficient, stoichiometric representations of the reaction. Equilibrium constant depends on the stoichiometric representation of a reaction. And when a reaction is reversed, its equilibrium constant is inversed. 3 points you have to remember, and all the basic questions you can solve. The first point. For example, you have got the reaction like this. A in equilibrium with B. Let's say its equilibrium constant is K1. Now, my dear students, if you reverse the same reaction, now its equilibrium constant won't be K1. It'll be inversed. It'll be 1 by K1. Remember, when the reaction is reversed, its equilibrium constant is inversed. When the reaction is reversed, its equilibrium constant is inversed. Point number one. Point number two. For example, you have got a reaction like this. A in equilibrium with B, whose equilibrium constant is K1. Right? Now, for example, you are multiplying this reaction by some number. You are multiplying this reaction with some number. Let's say the reaction now becomes Na in equilibrium with N times B. Okay? You had a reaction A gives B, whose equilibrium constant was K1. Now you are multiplying this reaction by some number. Do remember that number goes to the power of the equilibrium constant. Now the equilibrium constant of this reaction won't be K1. It is going to be K1 raised to the power of that number. Simple? Correct? Simple? Do remember them directly. They have got proofs as well, but that's going to take a lot of time. Leave that. Remember them directly so that we can solve the questions easily. Nothing else. At the same time, for example, you have got the reaction like this. A in equilibrium with B, whose equilibrium constant is K1. For example, C in equilibrium with D, whose equilibrium constant is K2. These are the two reactions. Now imagine I'm adding them. When I add these two reactions, what do I get? I get A plus C in equilibrium with B plus D. Since I added these reactions, when you add the reactions, equilibrium constants are multiplied. I would say equilibrium constant for this reaction now will be K1 multiplied by K2. It will now be K1 multiplied by K2. Okay, these are the three things which you have to remember, nothing else. Just these three things. Number one. What is the first thing? When you reverse the reaction, equilibrium constant is inversed. Number 2, when you multiply a reaction by some number, that number goes to the power of equilibrium constant. Number 3, what is number 3? When you add the reactions, their equilibrium constants are not added, they are multiplied. If this is clear, tell me the answer of a lot of questions, guys. A lot of questions. I'm starting with the first question. These are the questions you should kill. And these sort of questions are frequently asked. And these are very basic questions. What should be the answer of this question? See, one question I'll show you. The other ones you will have to do. Other ones you will have to do. My dear students, I'm giving you the reaction. The reaction is N2 gas plus 3 times H2 gas. It is in equilibrium with 2 times NH3 gas. 2 times NH3 gas. The equilibrium constant for this reaction is given to me as 49. Equilibrium constant for this reaction is given to me as 49. Now, I'm given with one more reaction whose equilibrium constant is to be calculated. I'm supposed to calculate the equilibrium constant for this reaction. I'm supposed to calculate equilibrium constant for this reaction. Do remember, that reaction whose equilibrium constant is to be calculated. That reaction whose equilibrium constant is to be calculated. Try to make that reaction out of the reaction whose equilibrium constant is given. Again, I'm repeating the same thing. That reaction whose equilibrium constant needs to be calculated. You will have to make that reaction out of the given reaction whose K is given. Understand? Now, how will I make this reaction from this particular reaction? What do I need to do? I'll just reverse the reaction first. When I reverse the reaction, it is going to be 2 times NH3. It gives N2 plus 3 times H2. Now, since I have reversed this reaction, its equilibrium constant will be inversed. Now it's 1 by 49. Now look, is this reaction and this reaction same? No, they are not same. Here the coefficient is 2. Here the coefficient is 1. So what I'll be doing? I'll be multiplying this reaction by the number 1 by 2. When I multiply this by number 1 by 2, it becomes NH3 in equilibrium with 1 by 2 N2 plus 3 by 2 H2. Correct? Since I multiplied this reaction by 1 by 2, that 1 by 2 goes to the power of its equilibrium constant. So it's 1 by 49 raised power 1 by 2. The value comes out to be 1 by 7. So 1 by 7 is the equilibrium constant of this reaction. Right? So the answer of this particular question is just going to be 1 by 7. Is it simple? Is it simple, people? Is it simple? Yes. Quickly. 3 reactions I'm given with. Their equilibrium constants are K1, K2, K3. We have to calculate equilibrium constant for this particular reaction. You will have to make this reaction out of these 3 reactions. Will you be able to solve this? Will you be able to solve this? Will you be able to solve this, people? Look here. The reaction whose equilibrium constant needs to be calculated, in that reaction, NH3 is on left side. Look at all these reactions. In all the reactions, I can see NH3 is there in only one reaction, and that's on right hand side. So what should my first step? My first step should be to reverse the first reaction. When I reverse the first reaction, it is going to be 2 times NH3 gives what? N2 plus 3 times H2. Since I reversed this reaction, so its equilibrium constant now is going to be 1 by K1. Right? It's going to be 1 by K1. Now guys, the second reaction, let me write it as such. N2 plus O2 gives 2 times NO. Its equilibrium constant is K2. Okay? Perfect. Now the reaction which I have to make, I would need 5 by 2 O2 here. Here I've got 1 O2. So what I'll be doing, let me just do one thing. If I multiply this reaction by number 3, see what will happen. If I multiply this reaction by number 3, it becomes like this. I multiplied this particular reaction by number 3. That number 3 goes to the power of its equilibrium constant. So it's K3 raised power 3. Right? This is the operation which I did till now. Now people, if you add them up, see what all things will get cancelled out. See, first thing, if you add them up, left hand side on one side, right hand side on one side. So 3 times H2, 3 times H2 cancel. N2, N2 cancel. Right? N2, N2 cancel. What I'm left with? 2 times NH3. 2 times NH3 plus O2 plus 3 by 2 O2 makes it 5 by 2 O2. Makes it 5 by 2 O2, right? On this side, what is left? 2 times NO plus 3 times H2O. Perfect. Look at this particular reaction. Is this reaction same as that of this one? Absolutely. So we made this reaction. How? When I added them up. since you're adding these reactions, so their equilibrium constants, they need to be multiplied, right? So equilibrium constant of this reaction will be 1 upon K1 multiplied by K2 multiplied by K3 raised power 3. So this is the equilibrium constant of the reaction which we were supposed to calculate. Now find the option. Find the option. K2, K3 raised power 3 divided by K1. K2, K3 raised power 3 divided by K1. Yes, I believe these sort of questions you can easily kill, right? Done, guys? Is it clear? What should be the answer of this question? What should be the answer of this question? Write out quickly. Till then I can have some water, because this is one basic question. Basic, semi-basic. What is the relation between K1 and K2? K1 and K2 are the equilibrium constants of these two reactions. You have to get the relation between them. You can easily get it. So electricity is over. That's okay. Board has to be visible. Is board visible? Night mode is on. Is board visible? Yeah. Welcome to the world of the night mode. Yeah, let me make the bass a little high. Welcome to the world of the night mode. All right, look at this question, guys. As per the question, we are given with two reactions. Reaction number 1, reaction number 2. Consult any one reaction. Let's say I'm consulting this reaction. So first thing, what I'll be doing? I'll be reversing this reaction. When I reverse the reaction, I'll be getting something like this. 3 times A2 plus 3 times B2, it gives 6 times AB. Since I have reversed this reaction, so its equilibrium constant is inverse. So it's 1 by K2. Do you think this particular reaction and this particular reaction is same? No, they are not same yet. We have to make them same. How? I'll be multiplying this reaction by the number 1 by 3. When you multiply it by the number 1 by 3, what do I get? I get something like this. 1 by 3, 3 cancel, 1 by 3, 3 cancel, 1 by 3 into 6 is 2, right? Since I multiplied this reaction by 1 by 3, so that 1 by 3 goes to the power of equilibrium constant. Perfect. Now look at this particular reaction and this particular reaction. Are they same? Yes, they are same. Yes, they are same. So I would say your K1 is equal to 1 upon K2 raised power 1 by 3. 1 upon K2 raised power 1 by 3. Right? Right, people? Or you can say, you can write it like this. K2 raised power minus 3 is equal to K1. K2 raised power minus 3 is equal to K1. Right? Sorry, I did a mistake. K2 raised power minus. K2 raised power 3 is equal to K1. Or if you take cube root on both the sides, you say K2 is equal to K1 raised power 1 by 3. Right? K2 is equal to K1 raised power 1 by 3. So option C is the one which is correct. Right, guys? Right. I mean, these sort of questions are pretty much simple and you should be able to solve them. See, do you believe this can be a question asked in your NEET examination? Do you believe that? You are given with a reaction. The concentrations of reactants and products at equilibrium are given and we are supposed to calculate Kc. How exactly? The reaction is 2 times A in equilibrium with B and C. Perfect. As per the question is concerned, concentration of A at equilibrium is given as 10 raised power minus 3 molar. Concentration of B at equilibrium is given as 2 into 10 raised power minus 3 molar. Concentration of C at equilibrium is also given as 3 into 10 raised power minus 3 molar. Right? These are the concentrations of A, B and C which are given to me. What do you have to calculate? I have to calculate Kc. What is Kc? How do you write the expression for Kc? It is going to be concentration of B at equilibrium raised power coefficient, concentration of C at equilibrium raised power coefficient divided by concentration of A at equilibrium raised power stoichiometric coefficient. Now put the values, that's it. Concentration of B at equilibrium, that is 2 into 10 raised power minus 3. C at equilibrium, that is 3 into 10 raised power minus 3. Divided by A at equilibrium, that is 10 raised power minus 3. But this is 10 raised power minus 3 ka square. So this term gone. The value just comes out to be 6. So 6 is going to be the answer of the question. This was your NEET question, guys, by the way. By the way. Right? Perfect. I believe easily you can solve this question. Even this is your asked question, guys. This is your asked question. You should be again in a position to solve this. Quickly. In which of the following Kp and Kc are not equal? Kp and Kc are not equal. First of all, you should know when Kp and Kc are equal. Kp and Kc are equal, well, delta Ng is equal to 0. So Kp and Kc won't be equal when delta Ng will be non-zero. This is the criteria. Done? Now look at all the options. Where do you see delta Ng non-zero? If you look at the last case, in the last reaction, calculate delta Ng is equal to number of moles of gaseous products minus number of moles of gaseous reactant, right? This is solid, leave it. So 2 minus 1 comes out to be 1, which is non-zero. If delta Ng is non-zero, Kp won't be equal to Kc. So D is the answer of the equation. Simple. Simple. Physics wala motivation is saying, sir, you have not posted notes on Telegram. Which chapter notes you are saying? Are you talking about GOC? GOC notes, I told you in the Telegram itself. GOC notes I was unable to save. Now, if by chance the ones who are watching me, if by chance you have made the notes of GOC, please post in the Telegram somewhere, right? Okay, so that others can also have them. All right. So people, what about this question? What about this question? Values of Kp in the reaction. Isn't simple again? Value of Kp in this reaction. Value of Kp in this reaction. See, this is gaseous. Nothing to do with this solid. Nothing to do with this solid. So Kp is nothing. It's going to be initial pressure of carbon dioxide at equilibrium. Raised for stoichiometric coefficient. That's 1. So again, this is done and dusted. Option A is the one which is correct. Yeah? Is it perfect, guys? Is it perfect? Are all the things clear? Now comes the most important topic of the chapter, that is Kp Kc calculation. But so guys, whatever basics was required to do some amazing questions, I think we have almost covered 90% of the basics which is required to solve the questions. Okay. Now we are going to enter into one more phase of this particular chapter. This is considered to be comparatively difficult, but if your basics is strong, this part will be very easy again. Okay, so till now, I'm sure you did not find anything difficult, right? Because everything was discussed in detail, right from the basics. Okay, so right after this also, whatever I'll be discussing, I'll be starting from the scratch only. Okay, perfect. So now comes one important topic, that is calculation of Kp and Kc. This is the topic from which the questions are asked majority of the times from the chapter equilibrium. Okay. Calculation of Kp and Kc. Well, my dear students, for the calculation of Kp and Kc, we have to discuss two methods. One is going to be your mole method, and one is going to be your degree of dissociation method. So one by one, we shall be discussing these two methods in detail. In detail, right? So first, we shall be starting with the mole method. Calculation of Kp and Kc with the help of mole method. This is something which is important. With the help of mole method. So my dear students, over here, the first thing which I'm going to discuss with you. What is that? That is the most important, which is the calculation of moles. Calculation of moles of reactants and products at equilibrium. How exactly do we calculate the moles of reactants and products at equilibrium? This is something which is really, really very important. If you understood this topic, that means you can understand everything in detail. Okay. Now guys, try to understand how do we exactly calculate the moles of reactants and products at equilibrium. For that, I'm going to take one simple reaction like this. Understand step by step. Let's say I've got a reaction A gives B plus C. Imagine this is a balanced chemical equation. Imagine this is a balanced chemical equation. Now, if this is a balanced chemical equation, let's assume that initially at time t is equal to 0, we have got A moles of reactant. First of all, this particular reaction will be taking place in some container, right? I'm assuming initially at time t is equal to 0, we have got A moles of reactant. Since the reaction has not started yet, that means moles of B and C formed will be 0 because the reaction has not started yet. A has not got converted into B and C yet, right? Now, my dear students, I'm assuming at equilibrium, out of A moles of reactant, let's assume X moles of reactant got converted into products. I'm assuming out of A moles of reactants, X moles got converted into product. So let me know how many moles of reactant will be left in the container at equilibrium. It's absolutely going to be A minus X. I had A moles. Out of A moles, X moles got converted into products. So I'll be left with A minus X. These are the moles of reactants which are left in the container at equilibrium. Now people, after this, what do we have to do? We have to use the stoichiometry. See, 1 mole gives 1 mole. 1 mole of A gives 1 mole of B. Therefore, X moles of A will give us X moles of B. 1 mole of A gives 1 mole of C. Therefore, X moles of A will give us X moles of C. So what did we calculate here? We calculated one simple thing. These are the moles of reactant present in the container at equilibrium, right? These are the moles of C and these are the moles of B in the container at equilibrium. So this is one very important step which you should know how to calculate in all the reactions. For example, let me change the reaction. Let's say you have got the reaction like this. A in equilibrium with 2 times B plus 3 times C. Let's say this is the reaction. Okay. Assume that initially at time t is equal to 0, we have got A moles of reactant in the container. So this has to be 0, this has to be 0 because the reaction has not started yet. Now imagine at equilibrium, out of A moles of reactant, X moles got converted into product. So I'll be left with A minus X moles of reactant, right? Now after this, you have to use the stoichiometry. 1 mole of A gives 2 moles of B. Therefore, X moles will give 2X moles of B. 1 mole of A gives 3 moles of C. Therefore, X moles will give 3X moles of C. So what did I calculate? These are the moles of all the reactants and products present in the container at equilibrium, right? Right, people? For example, let me change the reaction again. Let's say you have got the reaction like this. 2 times A in equilibrium with 3 times B plus 5 times C. Let's say this is the reaction now. Try to understand. For example, initially at time t is equal to 0, we have got A moles of reactant. So this has to be 0. Now, imagine out of A moles of reactant, X moles got converted. X moles got converted into product. So I'll be left with A minus X moles of reactant. Now try to understand. Use the stoichiometry. 2 moles of A gives 3 moles of B. 2 moles of A gives 3 moles of B. So 1 mole of A gives 3 by 2 moles of B. So X moles of A gives 3 by 2 multiplied by X moles of B. I hope this is clear. Simple stoichiometry. Similarly, 2 moles of A gives 5 moles of C. 1 mole of A gives 5 by 2 moles of C. So X moles of A gives 5 by 2 X moles of C. So these are the moles of reactants and products in the container at equilibrium. I believe this is clear. Similarly, my dear students, let me take few more reactions so that it becomes very much clear to you. Assume that you have got the reaction like this. A in equilibrium with B plus C. Assume that this is the reaction, right? For example, initially in the container, there were A moles of reactant. In the container initially. And before the start of the reaction itself, in the same container, imagine there were moles of product as well. Before the start of the reaction, imagine there were few moles of product. There were few moles of B already in the container. There were few moles of C already in the container before the start of the reaction itself. Now, at equilibrium, let's assume out of A moles of reactants, X moles got converted. So I'll be left with A minus X. These are the moles of reactant in the container. Already in the container, there were B moles. Now, some extra moles of B would have got formed. How exactly? 1 mole of A gives 1 mole of B. X moles would have given X. So, the moles of this B in the container at equilibrium will be B plus X. Similarly, this has to be C plus X. Right? So, these are your moles of reactant and product in the container at equilibrium. Right? These are the moles of your reactant and product in the container at equilibrium. I believe this is clear. For example, I've got the reaction like this. Understand. The reaction is 2 times A in equilibrium with 3 times B plus 7 times C. Let's say this is the reaction. Assume that initially at time t is equal to 0, before the start of the reaction, imagine we have got some A moles of reactant in the container. We have got B moles also. There are C moles of this product as well. Before the start of the reaction itself, there are some moles of B, there are some moles of C. Before the start of the reaction itself. Now, when the reaction will start, what will happen? I'll say at equilibrium, assume that out of A moles of reactant, X moles got converted into products. So I'll be left with A minus X moles, right? Now we use the stoichiometry. Before the usage of stoichiometry, how many moles of B were there in the container initially? There were B moles. Now, due to the reaction, few extra moles of B would have got formed. Now, how many? Use the stoichiometry. 2 moles gives 3 moles, right? 2 moles of A gives 3 moles of B. 1 mole of A gives 3 by 2 moles of B. So, X moles of A gives 3 by 2 X moles of B, right? Can I say similarly, this is going to be C plus 7 by 2X. So these are the moles of all the reactants and products in the container at equilibrium. Yes? Perfect, guys. Similarly. For example, imagine you have got a reaction like this. N2 plus 3 times H2. It is in equilibrium with 2 times NH3. This is the reaction which I'm taking, for example. Okay, this is the reaction, for example, which I'm taking. Imagine that initially at time t is equal to 0, we have got A moles of N2 in the container. There are, for example, B moles of H2 in the container. This is, for example, 0. Now, at equilibrium, how do we get the moles of all the reactants products? Now, my dear students, among these two reactants, I will be taking one as the reference. I'll be taking one of the reactant as a reference. And generally, that reactant is taken as reference whose stoichiometric coefficient is less. So I'll be taking N2 as the reference. Now understand. First of all, N2 has to react with H2. Perfect. How many moles of N2 we had? A. Let's assume that out of A moles of N2, X moles reacted with H2. Assume that out of A moles of N2, X moles reacted with H2. So I'll be left with A minus X moles. Correct? Understand now. 1 mole of N2 reacts with 3 moles of H2. 1 mole of N2 reacts with 3 moles of H2. So X moles of N2 would have reacted with 3X moles of H2. X moles of N2 would have reacted with 3X moles of H2. I had taken B. Out of B, 3X are reacting. So I'll be left with B minus 3X moles of H2. Correct? Similarly, 1 mole of N2 gives 2 moles of NH3. So X moles of N2 will give us 2X moles of NH3. Will you be able to do this? Honestly, will you be able to do this to every reaction? If that is the case, if you can do, then you should answer this question. For example, I've got the reaction N2 plus 3 times H2 in equilibrium with 2 times NH3. This is the reaction, for example. Before the start of the reaction itself, we have got A moles of N2 we have got B moles of H2, and there are already, for example, C moles of NH3 in the container. Now you need to tell me how many moles of reactant and product are present in the container at equilibrium. How do you do that? So first of all, among these two reactants, take one as the reference. I'm taking N2 as the reference. Yeah, the one which has got less stoichiometric coefficient. Imagine that out of A moles of N2, X moles have reacted. So I'll be left with A minus X moles of N2 in the container at equilibrium. Now you have to use the stoichiometry. 1 mole of N2 reacts with 3 moles of H2. So X moles would have reacted with 3X. I had taken B. Out of B, 3X are reacting. I'll be left with B minus 3X. These are the moles of H2 in the container. Already in the container, there were C moles of NH3. Now, due to the reaction, some new moles of NH3 would have got formed, right? See, 1 mole gives 2 moles. So, X moles are going to give us 2X moles. So, these are the moles of this NH3 in the container. Yes? Right, people? Is it clear? Is it clear? Is it clear? If this part is clear, if you are able to find the moles of reactants and products at equilibrium, you are fit to do the Kp and Kc calculation. You are fit to do the Kp and Kc calculation. But before doing Kp Kc calculation, I would want honest answers from you. Tell me whether you can calculate the moles of each reactant and product at equilibrium. Tell me in the chats with yes or no quickly. Tell me in the chat with a yes or no. Then I'll be moving on to Kp Kc calculation. Yeah? Perfect, guys. Now, it is time to discuss the mole method then. It's time to discuss the mole method, by means of which we can calculate Kp and Kc of different reactions. Try to understand how exactly I'm going to do it. Step-by-step process. Step-by-step process. Understand one by one. This is very important. Case 1. I'm taking, for example, the reaction. Let's say I'm taking the reaction A gas in equilibrium with B gas plus C gas. Let's say this is the reaction which I have. Okay. The first and the most important thing. Tell me the delta Ng for this particular reaction. Imagine this is a balanced chemical equation. So delta Ng is moles of gaseous products minus moles of gaseous reactants. So delta Ng is 1. Okay. Perfect. The first thing which I need to calculate the value of Kc. I need to get the value of Kc. How do I get the value of Kc? By writing Kc expression. How do I write the Kc expression? It is going to be concentration of B at equilibrium raised by stoichiometric coefficient. Concentration of C at equilibrium raised by stoichiometric coefficient. Concentration of A at equilibrium raised by stoichiometric coefficient. Correct? So can I say in order to get the value of Kc, I would need the concentrations of all reactants and products at equilibrium? I need this term as well as this term. What are these terms? These are the concentrations of reactants and products at equilibrium. So in order to get Kc, I need the concentrations of reactants and products at equilibrium. I'm assuming one more thing. I'm assuming the reaction is taking place in a container whose volume is V liters. The reaction is taking place in a container whose volume is V liters. Now, my dear students, try to understand one simple thing. Imagine at time t is equal to 0, we have got A moles of reactants. Imagine this is 0, this is 0. Now at equilibrium, how many moles of reactants will be left? A minus X. 1 mole gives 1, so X gives X and X gives X. So I got the moles of all the reactants and products in the container at equilibrium. But do I need the moles or I need the concentration? I need the concentration of all the reactants products at equilibrium. How do we convert moles into concentration? Concentration is moles per unit volume, right? So I'll be dividing these terms by the volume of the reaction vessel. So A minus X divided by V liters, X divided by V liters, X divided by V liters. What do I call these terms as? Can I say this is the concentration of reactant at equilibrium? This is the concentration of B at equilibrium. This is the concentration of C at equilibrium. Once you get the concentrations of reactants and products at equilibrium, you are done, you are sorted. Yes, you are done. Now you can easily write the expression for Kc. So Kc expression for this reaction is going to be concentration of B at equilibrium, that's X divided by V raised power 1. Concentration of C at equilibrium, that's again x divided by V raised power 1 whole divided by concentration of A at equilibrium, that is A minus x divided by V. So what will happen? This V and V will get cancelled out. So you got the final result as x square divided by V multiplied by A minus x. So this is the expression for Kc, for the reaction which was given to you. This is how you get the expression for Kc, right? This is how you get the expression for Kc. Now, how do we exactly get the expression for Kp? How do we write the expression for Kp? Try to write the Kp expression first. Guys, understand and remember this procedure. This is important, very much important. How do we write the expression for Kp? It's going to be partial pressure of B at equilibrium raised power stoichiometric coefficient multiplied by partial pressure of C at equilibrium raised power stoichiometric coefficient divided by partial pressure of A at equilibrium raised power stoichiometric coefficient. So basically, in order to calculate Kp, do we need concentrations or partial pressures? We need partial pressures of reactants and products in the container at equilibrium, right? Now guys, try to understand very carefully, very carefully. Try to understand very carefully. If I ask you, initially there was only one gas in the container, right? At equilibrium, there are three gases in the container. There are A minus X moles of reactant in the container. There are X moles of B in the container. There are X moles of C in the container. So at equilibrium, how many gases are there? There are three gases. So can I say at equilibrium we have got a gaseous mixture? Absolutely. At equilibrium we have got a gaseous mixture. Assume that total pressure of the gaseous mixture is represented by PT. PT equilibrium. This is basically what I call as total pressure. This is basically what I call as total pressure of the gaseous mixture at what? At equilibrium. This is total pressure of the mixture at equilibrium, right? This is total pressure of gaseous mixture at equilibrium. Now try to understand. First thing, if I ask you how many total moles are there in the container at equilibrium? How many total moles are there in the container at equilibrium? You will say it's A minus X plus X plus X. So it is A minus X plus X plus X, right? So which came out to be A plus X. So these are the total moles present in the container at equilibrium. How many gases are there? There are three gases in the container at equilibrium. Total moles present in the mixture at equilibrium, A plus X. Out of these total moles present at equilibrium, how many moles of reactant are there? A minus X. How many moles of B are there? X. How many moles of C are there? X. Now guys, just tell me one thing. If I divide this A minus X, by the total moles present in the mixture, if I divide this X by the total moles present in the mixture, if I divide this X by the total moles present in the mixture, what do I call these terms as? What do I call these? In the mixture, what do we have? We have got three gases. We have got a gaseous mixture. That gaseous mixture contains three gases. Moles of first gas divided by total moles. Moles of second gas divided by total moles. Moles of third gas divided by total moles. Should I be calling these terms as mole fractions of the individual gases at equilibrium? Absolutely. These are the mole fractions of the individual gases. This is the mole fraction of reactant at equilibrium, mole fraction of B at equilibrium, mole fraction of C at equilibrium, right? But do I need mole fractions or partial pressures? I need partial pressures. How do you convert mole fraction into partial pressure? How do you convert mole fraction into partial pressure? Multiply the mole fraction by the total pressure of the mixture at equilibrium. So it is A minus X divided by A plus X multiplied by PT. This will give you partial pressure of reactant at equilibrium. X divided by A plus X multiplied by PT. This will give you partial pressure of B at equilibrium. X divided by A plus X multiplied by PT. This will give you the partial pressure of C at equilibrium. If you got the partial pressures of reactants and products at equilibrium, can't you put these values into this expression? Absolutely. Can't you put these values into this expression? You can do that, right? So I'll be getting the exact value of Kp. partial pressure of B at equilibrium is X divided by A plus X multiplied by PT. Partial pressure of C at equilibrium is same, so it becomes square, divided by partial pressure of A at equilibrium is nothing, it is A minus X divided by A plus X multiplied by PT, right? So this gives you the value of Kp for the reaction. I believe the process is clear. The procedure is clear. I'll be taking one more example so that you can understand it properly. So in order to write the Kc, I need concentrations. Simple, moles divided by total volume. In order to write Kp, first I'll be calculating moles, divide them with total moles at equilibrium. I'll be getting mole fraction, and mole fraction is to be multiplied by the total pressure of the mixture at equilibrium. I'll be getting the partial pressure. Once I get the partial pressures, I'll put it here in the expression. Done and dusted. Say yes or no in the chats. Its process is very simple. Process is very simple, and every question will be solving with the help of this particular approach. Majority of the questions, I mean. Let me take one more example. With that, all the things will be clear, and then we'll be fit enough to do the questions. Try to understand. For example, I've got the reaction like this. Let's say the reaction is 2 times A gas. It gives B gas plus C gas. Okay, B gas plus C gas. The first thing which I'm asking you, what is delta Ng for the reaction? Let me know in the chats. What is delta Ng for this reaction? Quickly. I would first of all say delta Ng for the reaction is 0. Number of moles of gaseous products minus number of moles of gaseous reactants. It is 0. And you already know for those reactions whose delta Ng is 0, is their Kp and Kc always equal? Absolutely, their Kp and Kc is always equal. So if I get the Kc, automatically that will be Kp also. Right? Automatically that will be Kp also. Now we'll justify whether for this reaction Kp and Kc will be equal or not. Try to understand how exactly. First thing. Imagine people, initially at time t is equal to 0, we have got A moles of reactant. This will be 0, this will be 0. At equilibrium, understand, out of A moles of reactants, X moles got converted. So this is A minus X, right? Now, 2 moles of A are giving 1 mole of B. So 1 mole of A gives 1 by 2 moles of B. X moles will give X by 2. This will be also X by 2, right? This will be also X by 2, correct? So I got the moles of each reactant and product at equilibrium. Now, in order to get the Kc, what do I need? I need to get the concentrations. The concentration of each reactant and product at equilibrium will be equal to moles of reactant divided by total volume. X by 2 divided by total volume. X by 2 divided by total volume, right? So these terms, what do we call these terms as? These are the concentrations of what? Concentrations of reactants and products at equilibrium, correct? If you got the concentrations of all reactants and products at equilibrium, what do I need to write now? I need to write the expression for Kc. Kc expression will be equal. Concentration of B at equilibrium, that's X by 2V. Raised power stoichiometric coefficient, that's 1. Concentration of C at equilibrium, that's again X by 2V. Raised power stoichiometric coefficient, that's 1. Divided by concentration of A at equilibrium, that's A minus X divided by V, right? Raised power stoichiometric coefficient, that's 2. That's 2. Now see all the cancellation part. I'll say V square and V square gets cancelled. So what do I get at the end? What do I get at the end? Try to understand. What do I get at the end? It's going to be X square. It's going to be X square divided by 4 multiplied by A minus X ka square. This is the value of Kc for the reaction. This is the value of Kc for the reaction. Now, let's try to calculate Kp as well. How do you write the Kp expression first of all? Kp expression is written as partial pressure of B at equilibrium raised power 1, partial pressure of C raised power 1 divided by partial pressure of A raised power 2, which is the stoichiometric coefficient. Now people, try to understand. First of all, if I ask you how many total moles are there in the container at equilibrium, total moles in the container at equilibrium, which is A minus X plus X by 2 plus X by 2. That will come out to be A, right? Total moles in the container at equilibrium. Let me write it over here. Total moles in the container at equilibrium is equal to A minus X plus X by 2 plus X by 2. The value comes out to be A. If I divide this A minus X by total moles, if I divide this X by 2 by total moles, if I divide this X by 2 by total moles, what did I get? I got the mole fraction of reactant product at equilibrium. But do I need mole fraction to write Kp? No. What do I need? I need partial pressures. How do I get the partial pressure of reactant product at equilibrium? I'll assume that at equilibrium, the mixture, at equilibrium, the gaseous mixture which we have, assume its total pressure is Pt. So A minus X divided by A multiplied by Pt. Similarly, this term, X divided by 2A multiplied by Pt. This term, X divided by 2A multiplied by Pt. So these terms are what we call as partial pressures of reactants and products. Partial pressures of reactants and products in the container at equilibrium. At equilibrium. Once you got the partial pressures, you are fit to write the expression for Kp. Kp expression will be equal to partial pressure of B at equilibrium, X divided by 2A multiplied by Pt, right? This is partial pressure of B at equilibrium raised by stoichiometric option 1. Partial pressure of C at equilibrium, again X divided by 2A multiplied by Pt, whole raised by stoichiometric option, that's 1, divided by partial pressure of A at equilibrium, that is A minus X multiplied by Pt divided by A, whole raised by stoichiometric option, that is 2, right? See what all terms will get cancelled out. This is P square, P multiplied by P is P square, P square cancel. A यहाँ पे A square cancel. So what do I get? Finally, I get something like this. X square divided by 4 multiplied by A minus X ka whole square. This is the exact value of Kp, which we already knew that for the reaction whose delta Ng is 0, its Kp as well as Kc are always equal, and hence you proved it. Yeah? Yes, Abdul, yes. I was just showing you how come Kp, Kc are coming out to be equal. We already knew it. Kp and Kc will be equal for the reaction because delta Ng is 0, right? But here I just wanted to show you whether actually they come out to be equal or not. Got it? So if this is clear, now you are, my dear students, you are, I think, fit to solve different types of questions in equilibrium. A lot of questions which are already typed there, and a lot of questions I have come up with in the handwritten format. Okay? So one by one, we shall be discussing the question. This is our first question. For the reaction A plus B gives 2C, 2 moles of A, 1 mole of B, and 1 mole of C are placed in a 10-liter vessel and allowed to reach equilibrium. Allowed to reach equilibrium. If the final concentration of C is 0.2 molar, calculate Kc. How you are going to solve it? Simple procedure. The same procedure which we already know. First thing, the reaction is like this. A gas plus B gas, it is in equilibrium with 2 times C gas. This is the reaction. This reaction is carried out in a vessel whose volume is 10 liters. Perfect. Now, as per the equation, initially, we have got 2 moles of A, 1 mole of B, and 1 mole of C in the container. This is something which we have as per the equation. As per the equation, the final concentration of C. What is meant by final concentration of C? Final concentration of C means concentration of C at equilibrium. Because we know once equilibrium is established, concentrations of all reactants and products, they are fixed. They do not change after that. So final concentration of C. Concentration of C at equilibrium is equal to 0.2 mole. This is something which is given. Okay. Now use the same procedure which I told you. Imagine at equilibrium, out of 2 moles of reactant, X moles have reacted, so I'll be left with 2 minus X moles of reactant. 1 mole of A reacts with 1 mole of B, so X moles would have reacted with X moles. 1 mole reacts with 1 mole, so X moles with X moles. I had taken 1, out of 1 X moles are reacting, so I'll be left with 1 minus X. Already in the container there was 1 mole of C. Now some new moles of C would have got formed. 1 mole of A gives 2 moles of C, so X moles would have given 2 X moles because stoichiometry is 2 here. Correct? Right, people? So what are these terms here? These are basically the moles of reactants and products. These are the moles of reactants and products in the container at equilibrium. These are the moles of reactant and product. Just guys, give me a second. Done. My job is done. Look at this. A lot of spammers do come in between, right? They don't know I have got the option of blocking as well. Yeah? They don't know I have got the option of blocking as well. Nonsense. Blocked forever. Let him come with one more account. Let him come with one more account. It'll be fun. I hope he comes. Okay. Perfect. So these are the moles of reactants and products in the container at equilibrium. Yeah. Now, guys, we have to calculate the value of Kc. To calculate value of Kc, what do we need? Do we need concentrations? Absolutely, we need concentrations. So, concentration, how do you convert moles into concentration? Moles divided by volume. So, 2 minus x divided by total volume of the vessel is 10 liters. 1 minus x divided by 10, right? 1 plus 2x divided by total volume 10 liters. What did I get? I got the concentrations of all the reactants and products at equilibrium. These are the concentrations of reactants and products at equilibrium, right? Now, people, already we know one thing. What is that? Concentration of C at equilibrium is given. And we know concentration of C at equilibrium. We got to know it is 1 plus 2x divided by 10. This is the concentration of C at equilibrium, right? And this is something which is given to me as 0.2, which means 2 by 10. 10 cancelled. So x value will come out to be 0.5. X value will come out to be 0.5. Since you got the value of x, put this value of x here everywhere. You'll be exactly getting the concentrations. 2 minus 0.5 is 1.5. 1.5 divided by 10 is 0.15 molar, right? 1 minus 0.5 is 0.5. 0.5 divided by 10 is 0.05. So 0.05 molar. And this term already we know, as per the equation, it's 0.2 molar. So you exactly got the concentrations of all the reactants and products at equilibrium. Since you got the concentrations, write the expression for Kc, right? Write the expression for Kc. It is going to be concentration of C at equilibrium raised power 2 divided by concentration of A at equilibrium raised power coefficient 1, concentration of B at equilibrium raised power stoichiometric coefficient 1. Look at all the values. Concentration of C at equilibrium 0.2 raised to the power 2 divided by concentration of A at equilibrium 0.15 molar raised power stoichiometric coefficient 1. Similarly, this is 0.05 raised power 1. It's a matter of calculation. Solve it and get the value of Kc, which you were supposed to calculate. And as I can see, a lot of students are saying Kc value is coming out to be 5.3. Chalo, I trust you. It is 5.3. It is 5.3, right? If I ask you what are going to be the units of Kc, if you remember Kc units, moles per liter raised per delta Ng. What is delta Ng for the reaction? 2 minus 2 is 0. Anything raised per 0 is 1. So it is going to be unitless, right? 5.3 is the value of Kc. Done and dusted? Done and dusted? Absolutely, this is done and dusted. Look at one more question, guys. Look at one more question. Now it's a question game. For a reaction, x plus y gives 2 times z. 1 mole of A, 1.5 moles of y, and 0.5 moles of z were taken in a 1 liter vessel, allowed to react. At equilibrium, the concentration of z was this much. The equilibrium constant of the reaction is x by 15. Find x. See, the same procedure, x plus y, as per the equation, x plus y in equilibrium with 2 times z. This is the reaction which we have. Now, the same procedure which we have been following throughout. So initially at time t is equal to 0, how many moles of x are given? 1. How many moles of y are given? 1.5. How many moles of z are there? 0.5. So these are the moles of reactants and products in the container. These are the moles of reactants and products in the container at equilibrium. Now, my dear students, as per this particular question, at equilibrium, the concentration of Z is given. The concentration of Z is given. Tell me, at equilibrium, the concentration of Z is given. How much? The concentration of Z at equilibrium, it is given to me as 1 mole per liter, or you can say 1 molar. What do we have to do? We have to get the value of Kc. We have to get the value of Kc. You are going to use the same approach. At equilibrium, assume that out of 1 mole of this reactant, X moles have reacted. So I'll be left with 1 minus X moles of reactant. Now, 1 mole of X, 1 mole of this reacts with 1 mole of this. So X moles would have reacted the X moles. So I'll be left with 1.5 minus X. The same procedure which we have seen already. Already there were 0.5 moles of Z in the container. Some new moles would have got formed. 1 mole of this gives 2 moles. So X moles will give 2X. So you got to know the moles of each reactant and product in the container at equilibrium, right? Since you got the moles of each reactant product at equilibrium, do we need moles or do we need concentration? We need concentration. Do you know how do we convert moles into concentration? Yes. Moles divided by volume. Moles divided by volume. So divide all these terms by the total volume of the vessel. Total volume of the vessel is 1 liter. Total volume of the vessel is 1 liter. So you got the concentrations. These are your concentrations, right? And as per the equation, concentration of Z at equilibrium is given. We know concentration of Z at equilibrium is 0.5 plus 2x. It is equal to 1, right? So 2x will come out to be 0.5 and x will come out to be 0.25. So this is the x. Since you got the x, put the value of x in all the expressions. So 1 minus 0.25 comes out to be 0.75. So this is 0.75 molar. This will be 1.5 minus 0.25 will come out to be 1.25 molar. This is given as per the equation. It is 1 molar, right? So you got the concentrations of all the reactants and products in the container at equilibrium. Now, my dear students, since you are done till here, write the Kc expression. Kc is going to be concentration of Z at equilibrium, that's 1, raised power stoichiometric coefficient, that's 2, divided by concentration of X at equilibrium, that is 0.75, raised power stoichiometric coefficient 1, concentration of Y at equilibrium, that's 1.25, raised power stoichiometric coefficient, that's 1. Okay. Now, my dear students, is the value of Kc given? Yes, the value of Kc is given as X divided by 15. The value of Kc is given as X by 15. So X by 15 is equal to 1 divided by 0.75 multiplied by 1.25. Isn't it a matter of calculation now? One equation, one unknown. Get the value of X. You are done. You are done. Yes, you are done, people. You are done, people. Is it clear? Is it clear? Everyone in the chats, is it clear? Is this question done? Is this question done? Let me show you one more question which was asked last year in your JEE mains examination, and I believe you can easily kill this. You can easily kill this. You can easily kill this. Will you be able to solve this quickly? Quickly, guys. Basit, yes, Altaf sir, chemistry. He's a wonderful teacher. I love him. He's my elder brother. Okay? Just call him and ask. Call him and ask about me, okay? Give it a try. Give it a try, people. I'm serious. You call him and ask him about me. Tell him that you were spamming in my chats. Call him. Or I can provide you his number. Quickly. Anyone? Anyone? Okay, look at this particular question. See what the question says. Guys, you should be able to solve this question as well. For the reaction given below, Kc is something. If the initial concentration of all the species was 1 molar, calculate the concentration of D at equilibrium. Okay, have a look. Initially at time t is equal to 0, the initial concentration of all the reactants is given. Initial concentration of all the reactants as well as products. Initial concentration of all the species is 1 molar. Now here I'm directly starting with concentration, right? Now at equilibrium, what will be left? 1 minus x, here 1 minus x, here 1 plus x, here 1 plus x. I don't think there is any need to explain this. Since I started with the concentration directly, so what are these terms? What are these terms? These are concentrations of your reactants and products. These are concentrations of your reactants and products at equilibrium. Because I started with the concentration. I'm not supposed to divide with volume here. Okay? Anyways, concentration of D at equilibrium I need to calculate. Kc is given to us. Kc is given to us. Can you write the Kc expression once? Kc expression is going to be concentration of C at equilibrium multiplied by concentration of D at equilibrium. So which will be 1 plus x square divided by, it's going to be 1 minus x square. So I'll write it like this, 1 plus x divided by 1 minus x whole square. And this Kc value is equal to 100. This Kc value is equal to 100. Okay. Now, it is 1 plus x divided by 1 minus x is equal to 10. Or you can say 1 plus x is equal to 10 minus 10x. Or you can say 11x is equal to 9. Or you'll be getting the value of x as 9 by 11. This is the value of x which you got. What were you supposed to calculate? What were you supposed to calculate? Try to understand. You were supposed to calculate the concentration of D at equilibrium. And concentration of D at equilibrium is nothing, it's 1 plus x. So concentration of D at equilibrium is 1 plus x. You have already gotten the value of x. It is going to be 1 plus 9 by 11. So the value comes out to be 20 divided by 11 molar. This is the concentration of D which you were supposed to calculate at equilibrium. Done and dusted, right? Isn't it simple? Isn't it simple, people? Isn't it simple? Quickly in the chats. Look at one more similar question. One more similar question. You should be able to solve this as well. 8 moles of AB3 are introduced in 1 decimeter cube. 1 decimeter cube means 1 liter. At equilibrium, 2 moles of A2 are present. Calculate Kc. Again the similar sort. Again the similar sort. As per the question, initially at time t is equal to 0, we have got 8 moles of AB3. So this has to be 0. This has to be 0. Right? Now at equilibrium, assume that out of 8 moles of reactant, x moles got converted. So I'll be left with 8 minus x moles. Now 2 moles gives 1 mole. 2 mole of AB3 gives 1 mole of A2. So 1 mole of AB3 gives 1 by 2. X gives x by 2. Similarly, this is going to be 3 by 2x. Right? Volume of the container is 1 liter. So I can call them directly as the concentrations. I can call them directly as the concentrations. Now, my dear students, as per the question, it is mentioned 2 moles of A2 are present at equilibrium. 2 moles of A2 are present at equilibrium. Number of moles of A2 at equilibrium is basically x by 2. So x by 2 is equal to 2. Right? 2 moles of A2 are present at equilibrium. Perfect. Number of moles of A2 at equilibrium is x by 2. That's given to us 2. So x value will come out to be directly as 4. If x is 4, 8 minus 4 comes out to be 4. This is 4 by 2 is 2. This is 3 4s are 12. 12 by 2 is 6. Right? So this is directly molar. These are the concentrations. Right? Because the volume of the vessel is 1 liter. If you got the concentrations of each reactant product, you can get the value of Kc. It is going to be concentration of A2 at equilibrium. That's 2 raised power 1. Concentration of B2 at equilibrium. That is 6 raised power stoichiometric coefficient. That's 3. Right? Divided by concentration of AB3 at equilibrium, that is 4 raised power stoichiometric coefficient, that's 2. Solve it and get the value of Kc, which you were supposed to calculate. Done? Done, people? You should be in a position to solve these sort of questions from now on. Let's have a look on different types of questions now. Let's have a look on different types of questions now. Let's have a look on different types of questions now. Look at this particular question. Look at this particular question. On starting with 1 mole of HI in a 2 liter container, calculate the concentration of each species at equilibrium if Kp for the decomposition of HI is something. First of all, decomposition of HI. Write the decomposition reaction of HI. It is going to be 2 times HI gas in equilibrium with H2 gas plus I2 gas. This is going to be your reaction. Yes, this is your reaction. Now, as per the question is concerned, Kp value is given. Kp value for the reaction is given to us as 16. What are we supposed to calculate? Calculate the concentration of each species at equilibrium. Okay. On starting with 1 mole of HI. So initially, you are starting with 1 mole of HI. This is 0. This is 0. Right? Same procedure. Now you tell me first of all one thing. Tell me one thing. What is the value of delta Ng for this reaction? Delta Ng for the reaction. Delta Ng for the reaction. Number of moles of gaseous products 1 plus 1 2 minus number of moles of gaseous reactants 2. So 2 minus 2 is 0. So I would say first of all delta Ng for the reaction is 0. If delta Ng for the reaction is 0, can't I say Kp has to be equal to Kc? Right? Kp is given. That means it is the value of Kc as well. That means it is the value of Kc as well. Agreed? It is the value of Kc as well. Now after this, use the general procedure at equilibrium. Assume that out of 1 mole of reactant, X moles got converted into product. So I'll be left with 1 minus X moles of reactant. Now we use the stoichiometry. 2 moles gives 1 mole. 1 mole gives 1 by 2. X gives X by 2. Right? Even this is going to be X by 2. So these are the moles of reactants and products in the container at equilibrium. Correct? So if you ask me what is the concentration of each reactant and product at equilibrium, divide these moles by the total volume. 1 minus X divided by total volume of the vessel is 2 liters, right? So this is X divided by 2, 2s are 4. This is X divided by 4. So these are the concentrations of each reactants and products in the container at equilibrium, right? Now, my dear students, just try to write the expression of Kc expression. Concentration of H2 at equilibrium, that's X by 4 raised power 1. Concentration of this at equilibrium, X by 4 raised power 1. So it comes out to be X square divided by 16 whole divided by. Concentration of Hi at equilibrium 1 minus X divided by 2 whole raised power stoichiometric coefficient 2. Perfect. Now it's just a matter of calculation. It is just a matter of calculation now. Try to understand how. See guys, Kc value is given as 16. So I would say 16 is equal. It is going to be X square divided by 4 multiplied by 1 minus X square. Just a bit of calculation is needed, nothing else. Now after this, what you'll be doing? See, 16 I'm writing as such is equal to, I'll write it like this, X divided by 2 multiplied by 1 minus X whole raised power 2. Will it make a difference? No way. Take the root on both the sides. This is 4 is equal to X divided by 2 minus 2X. So it's going to be 8 minus 8X is equal to X. So you got to know as 9X is equal to 8. And from there, you got the value of X. So X value came out to be 8 divided by 9. You got the value of X. If you got the value of X, what was I supposed to calculate? I was supposed to calculate the concentration of each species at equilibrium. What is the concentration of H2 at equilibrium? Concentration of H2 at equilibrium is same as that of concentration of I2 at equilibrium. And both are equal to how much? Both are equal to X by 2. So X by 2. X is your 8 by 9. So 8 divided by 9 2s are 18. So this is your concentration of H2 at equilibrium and I2 at equilibrium. Similarly, concentration of Hi at equilibrium is equal to 1 minus X divided by 2. Just a second. Sorry guys. There is a mistake. This has to be concentration of H2 and I2 at equilibrium is X by 4. Sorry. This is X by 4. So 8 divided by 36 will come as the answer. 8 divided by 36. It is 8 divided by 36 molar. Similarly, this is 1 minus X divided by 2. So it's going to be 1 minus X is 8 by 9 whole divided by 2. This will come out to be 9 minus 8 is 1. 1 divided by 18 molar is basically going to be the concentration of Hi in the container at equilibrium. Is it clear? Will you be able to solve these sort of questions as well? I would need the genuine answer from here. Is it clear? Look at one more type of the question, guys. Look at one more type of the question. For the reaction N2 plus 3 times H2 gives NH3. the partial pressure of N2 and H2 are this and this at equilibrium, the total pressure of the system at equilibrium is 2.8. Calculate Kp for the reaction. Look at this particular equation. Again, this is simple only. It is just your concept should be strong enough to interpret the question, guys. See, as far as this particular equation is concerned, I'm writing a reaction. N2 gas plus 3 times H2 gas. It is in equilibrium with 2 times NH3 gas. This is my reaction which is given to me. Now tell me one thing. At equilibrium, when equilibrium will be established in the reaction, how many gases will be there in the container? Just tell me that. When equilibrium will be established, there will be some moles of this left, some moles of this left, and some moles of NH3 which would have got formed. So at equilibrium, how many gases will be there? 2 or 3. There will be 3 gases in the container. Right? So the equilibrium mixture, the mixture contains how many gases? The mixture contains 3 gases. Which all? Which all? Some moles of N2 will be there, some moles of H2 will be there, and some moles of NH3 would have got formed. Correct? As per the question is concerned, total pressure of the mixture at equilibrium is given as 2.8 atm. This is the total pressure of the mixture at equilibrium. This is the total pressure of the mixture at equilibrium. I'll use the Dalton's law. Total pressure of the mixture will be the sum of their partial pressures. I'll say total pressure of the mixture at equilibrium will be equal to partial pressure of N2 at equilibrium plus contribution made by H2, which is what you call as partial pressure of H2 at equilibrium plus partial pressure of NH3 at equilibrium. Correct? I used simply the Dalton's law, and this value is equal to 2.8 atm. Partial pressure of N2 as per the equation is 0.8. H2 is 0.4. 0.8 plus 0.4 is 1.2. So from here, you can calculate the partial pressure of NH3 at equilibrium. How much that will be? 2.8 minus 1.2, which will come out to be 1.6 atm. So this is the partial pressure of NH3 at equilibrium. Since you have partial pressure of each reactant and product at equilibrium, you can easily calculate the value of Kp. So Kp expression has to be equal. It is partial pressure of NH3 at equilibrium raised by stoichiometric coefficient divided by partial pressure of N2 at equilibrium raised by stoichiometric coefficient, partial pressure of H2 at equilibrium raised by stoichiometric coefficient. So Kp has to be equal. Partial pressure of NH3 at equilibrium is how much? 1.6 plus square. Partial pressure of N2 at equilibrium is given to us as how much? 0.8. Partial pressure of H2 at equilibrium is how much? 0.4. 0.4, but this is 0.4 raised by 3. When you solve this, the value comes out to be 50. Now, if I ask you what are going to be its units, units will be atm raised by delta Ng. Delta Ng is number of moles of gaseous products minus number of moles of gaseous reactants. So 2 minus 4 comes out to be minus 2, right? So this is the value of Kp which we were supposed to calculate. I believe you can easily solve these sort of questions from now on. Is that people? Is that people quickly? Is everything clear? Now there is one more type of the question. We have got one more type of the question here. Let's see what the question says. We have got one more type of the question. If the total pressure at equilibrium for the following reaction is 2 atm, then calculate the volume fraction of Cl2 at equilibrium. Kp is given. Okay. Guys, before solving this question, let me tell you one simple concept. Let me give you one simple concept. Then we'll solve this question. Let me solve this simple question. Imagine this is the container. Imagine in this container, there is a mixture of gas, A, B, and C. Mixture of 3 gases are there in the container, right? Mixture of 3 gases are there in the container. Perfect. We have got gas A, gas B, gas C. So first of all, I can say I have got a mixture of gas. I've got a gaseous mixture in the container. I'm assuming that this gaseous mixture is kept at constant pressure and temperature. Its pressure and temperature are kept constant. The pressure and temperature of the mixture is fixed. It's constant. It's constant. Remember, whenever you will be having a gaseous mixture, whose pressure and temperature will be constant. At that point of time, you can say the mole fraction of gas A in the container, you can call it as the volume fraction of A as well. Similarly, mole fraction of B, you can call it as the volume fraction of B. Similarly, mole fraction of C, you can call it as the volume fraction of C. But when? Is it valid every time? No, it's not valid every time. It is valid only when the gaseous mixture is present at constant fixed pressure and temperature. Fixed pressure and temperature. Right? Fixed pressure and temperature. Now guys, try to understand how to deal with this particular question. As per the question, we are given with the reaction. The reaction is simple. PCl5 gas. It is in equilibrium with PCl3 gas plus Cl2 gas. This is the reaction that's given. Okay. What are we supposed to calculate? We are supposed to calculate the volume fraction of Cl2 at equilibrium. Volume fraction of Cl2 at equilibrium, we are supposed to calculate. Kp is given. Kp is given. My dear students, imagine that we have got A moles of reactant in the beginning. So this has to be 0. This has to be 0. Now, at equilibrium, this has to be what? A minus x. This has to be x. This has to be x. Correct? Right? This has to be x. Now guys, if I ask you how many total moles are there in the container at equilibrium, you will say A minus x plus x plus x, which makes it A plus x. So I'm dividing this term with A plus x. I'm dividing this term with A plus x. I'm dividing this term with A plus x. What did I get? I got the mole fraction of each. I got the mole fraction of each reactant and product in the container at equilibrium, right? Now, you know, when equilibrium is established in the reaction, all the measurable properties are constant. Pressure is constant. Temperature is constant. So can I say when equilibrium will be established in the reaction, the total pressure of the mixture is constant. The temperature of the mixture is constant. So at equilibrium, I would say pressure and temperature of the mixture is kept constant. At equilibrium, these terms are constant, right? Now, if these terms are constant, can I say, as per the concept which I told you, can I say, at equilibrium, since the pressure and temperature is constant, can I say the mole fraction of Cl2 will be called as volume fraction of Cl2, right? What are we supposed to calculate? Volume fraction of Cl2 at equilibrium. But we got to know volume fraction of Cl2 is nothing. That's the mole fraction of Cl2 at equilibrium. So basically, whose value we have to calculate? We have to calculate this value. X divided by A plus X value is to be calculated. X divided by A plus X value is to be calculated. Now the point is, how do you get the value of X divided by A plus X? For that, I need some space. Try to understand how exactly we'll be doing it. My dear students, what is the total pressure of the mixture at equilibrium? Total pressure of the mixture at equilibrium is 2, right? So if I multiply this term by 2, this term by 2, this term by 2, what should I be calling these as? I'll be calling them as the partial pressures of reactants products. I shall be calling them as partial pressures of reactants products. If I write the expression for Kp, Kp expression is going to be this term multiplied with this term, which will come out to be 4x square divided by A plus x whole square, right? Whole divided by partial pressure of PCl5 at equilibrium, which is 2 multiplied by A minus x whole divided by A plus x. So 1A plus x, 1A plus x cancel. So Kp value will come out to be finally 2122. This is 2x square divided by A plus x into A minus x will come out to be A square minus x square, right? And this Kp as per the question is given to me as 0.2. 0.2 means 2 by 10. So 2 got cancelled. So you got x square divided by, or let me just ignore certain steps. Since 2 got cancelled, you got 10x square is equal to A square minus x square. From here you got 11x square is equal to A square. So x you got to know as A divided by root 11. So x you got to know as A by root 11. If x is A by root 11, put it here. So x is A by root 11 whole divided by A I am writing as such plus x is A divided by root 11. So A everywhere cancelled. So it's going to be 1 divided by root 11 divided by 1 plus 1 by root 11. Correct? Cross multiplication is needed. So finally, I'll be getting the final answer like this. Final answer I'll be getting as 1 divided by root of 11 plus 1. Right? This is the final answer which I got. So this multiplied by this multiplied by this, root 11 cancel. So 1 divided by root 11 plus 1. This is something which I'll be calling as the volume fraction of Cl2 at equilibrium. That is something which I was supposed to calculate, right? Volume fraction of Cl2 at equilibrium came out to be 1 divided by root 11 plus 1. Is this clear? Will you be able to solve these sort of questions? Will you be able to solve these sort of questions? Everyone. Everyone. Alina Ashfaq, I think you are new to the channel, right? We have started the session just 4 hours back and we take 10-hour classes. I think you are new here. Okay. I hope all the things are absolutely clear till here. So let's move on to one more type of the question. Before solving one more type of the question, there is something which we need to know. There is something which you need to know. Usage of pressure instead of moles. Usage of pressure instead of moles. My dear students, one thing which I would want to share with you. Ideal gas equation everyone would have studied. PV is equal to nRT. PV is equal to nRT. This is your ideal gas equation. Okay. My dear students, imagine that if volume and temperature is kept constant, R is already constant, I can say pressure is directly proportional to moles. At constant volume and temperature, I can say pressure is directly proportional to moles. What does that mean? That means if moles are increasing, pressure will be increasing. Moles are decreasing, pressure will be decreasing. Correct? At constant volume temperature, if you increase the moles, pressure will increase. If you decrease the moles, pressure will decrease. What does that mean? And how exactly you are going to use this? Understand what exactly I'm going to say. For example, I've got the reaction like this. A gas in equilibrium with B gas plus C gas. A gas in equilibrium with B gas plus C gas. Imagine this particular reaction has to take place in a container which is closed. It is a closed container. It is a closed container, right? It is a closed container. For example, what exactly I'm doing? I'm keeping volume and temperature constant here. I'm keeping volume and temperature constant. And we know at constant volume temperature, pressure is directly proportional to moles. Decrease the moles, pressure will decrease. Increase the moles, pressure will increase. Now, the point is very simple. Initially at time t is equal to 0. Initially at time t is equal to 0. There will be only moles of reactant in the container. There will be only moles of A in the container. So whatever pressure will be there in the container, that will be only due to A. Because the reaction has not started. B and C has not got formed yet. Whatever is the pressure of the container at time t is equal to 0, that is due to A. Let's call that pressure as P0. Let's call that pressure as P0. For example, P0 ATM. Pressure due to B will be 0. Pressure due to C will be 0. Why? Because B and C, they have not got formed yet. Now tell me one thing. As the reaction proceeds, the moles of reactant will keep on decreasing. My dear students, if moles of reactant decrease with time, when you decrease the moles, pressure will decrease. If moles of reactant decrease with time, can I say pressure due to reactant will decrease too? Pressure due to reactant will decrease too. So at equilibrium, pressure due to reactant will be less. For example, here it was P0. Here it's going to be P0 minus X. P0 minus X ATM. Directly, I'll be calling this as pressure of A at equilibrium. Correct? Now, my point is pretty much simple. The way you were treating the moles, in the similar way, treat the pressure. The way you were treating the moles, in the similar way, treat the pressure. In short, no need to remember anything. The way you were treating the moles, in the similar way, treat the pressure. Imagine this was P0 moles. This is P0 minus X. Now, 1 mole gives 1 mole. From X, you get X. 1 mole gives 1 mole. From X, you get X. But you have no doubt treated them like moles, but these are actually the pressures. So what are these terms here? These are the partial pressures. Directly, these are the partial pressures of reactants and products at equilibrium. You got it? You got it? The way you were treating the moles, in the similar way, treat the pressure. Nothing else. Take one more example and solve the equation then. For example, the reaction is like this. A gas in equilibrium with 2B gas plus 3 times C gas. Imagine this is your reaction. Imagine this is your reaction, which is happening at constant volume temperature. At time t is equal to 0, there'll be only reactant in the container. So whatever is the pressure at time t is equal to 0, that's P naught. So this is 0, this is 0. Now treat the pressure in the similar way as you used to treat moles. Call this as P naught minus X. 1 mole gives 2 moles, X gives 2X, 1 gives 3, X gives 3X. Now these are the pressures basically. These are the partial pressures of reactants and products at equilibrium, nothing else. Got it? So my point is pretty much simple. At constant volume and temperature, treat the moles in the similar way as you treat pressure. I told you reverse. Treat the pressure in the similar way as you used to treat moles. Okay? Perfect. Say yes or no in the chats once. Say yes or no in the chats once, if it is clear. Say yes or no in the chats once, if it is clear. See how it's going to solve a lot of problems. It's going to solve everything. Look at this question. As far as the question is concerned, we have got the reaction AB3 gas, which is in equilibrium with AB2 gas, plus what? Plus half of B2 gas. This is the reaction which we have, correct? This is the reaction which we have. As per the question is concerned, if the initial pressure of AB3 is 900 torr, if the initial pressure of AB3 is 900 torr, and the total pressure at equilibrium is 1000 torr. So this is 0, this is 0. Now at equilibrium, what will be pressure due to AB3? Can't I say it is 900 minus X torr? Use the stoichiometry. 1 mole gives 1 mole, X gives X. 1 gives 1 by 2, X gives X by 2. Right? So what are these terms? What are these terms? What are these terms? These are the partial pressures of reactants and products at equilibrium. Right? Now, can I say total pressure of the mixture at equilibrium will be the sum of these partial pressures? Of course. So it is 900 minus X plus X by 2. So X cancel. Total pressure of the mixture at equilibrium is given as 1000 torr. So 1000 is equal to 900 plus X by 2. So the value of X will come out to be 200 torr. Value of X will come out to be 200 torr. If you got the X value, put the value of X here. 900 minus 200 is 700 torr, right? This will be X, which is 200 torr, X by 2. 200 by 2 is 100 torr. Since these are the partial pressures of reactants and products at equilibrium, if these are the partial pressures, you can easily calculate the Kp expression. Kp, partial pressure of AB2 at equilibrium, which is 200, raised for stoichiometric coefficient. Partial pressure of B2 at equilibrium, which is 100, raised for stoichiometric coefficient. Partial pressure of AB3 at equilibrium, which is 700, raised for stoichiometric coefficient. So Kp will come out to be 200 divided by 7. Right? Sorry, 20 by 7 it will come. Kp will come out to be 20 divided by 7. If I ask you the units is torr raised by delta Ng. Delta Ng for the reaction is 1 plus 1 by 2 is 3 by 2. 3 by 2 minus 1 is 1 by 2. So torr raised for 1 by 2 is the final answer. Do you agree with this? Is it clear? Say yes or no quickly. Say yes or no quickly. You cannot take this much of time. Look at one more. Look at one more, guys. The question is saying something. I don't know what it is saying. The total pressure at equilibrium is 30 atm and the partial pressure of HNO3 at equilibrium is 2 atm. Calculate Kp for the reaction. How you are going to solve this? How you guys are going to solve this? The procedure which I gave you a few minutes back, use the same procedure. Try to understand. The reaction that's given to us is 4 times HNO3 gas. It is in equilibrium with 4 times NO2 gas plus 2 times H2O gas plus O2 gas. This is the reaction that is given to us. This is the reaction that's given to us. As per the question is concerned, the total pressure of the mixture at equilibrium is given. Partial pressure of HNO3 at equilibrium is given. Calculate Kp. Okay. But dear students, let's assume that the pressure due to HNO3 initially is P naught. This will be 0, this will be 0, this will be 0. Now, treat the pressure in the similar way as we were treating the moles. This is going to be P naught minus X, right? 4 moles are giving 4 moles. 1 mole will give 1 mole. So X will give X, right? 4 moles are giving 2 moles. 1 mole will give 2 by 4. 2 by 4 means 1 by 2. So X will give X by 2. right? 4 moles are giving 1 moles. So 1 mole will give 1 by 4. X will give X by 4. No doubt, I treated these pressures like moles, but these are not moles. I treated them like moles. I treated them like moles. Yeah? I treated them like moles. Now you tell me. P naught minus X. P naught minus X. Units are in ATM. This is the partial pressure of HNO3 at equilibrium. Partial pressure of NO2 at equilibrium. Partial pressure of H2 at equilibrium. Partial pressure of O2 at equilibrium. Now, my dear students, try to understand very carefully what exactly I'm going to do. As per the question, the partial pressure of HNO3 at equilibrium is 2 atm. Partial pressure of HNO3 at equilibrium. Partial pressure of HNO3 at equilibrium, basically that is P naught minus X. This is given to me as 2 atm. As per the question. This term is given to me as 2. And the total pressure of the mixture is also given to me as 30 atm. Total pressure of the mixture. Total pressure of the mixture at equilibrium will be the sum of these partial pressures. So P naught minus X plus X by 2 plus X by 4. This is the total pressure of the mixture at equilibrium, which is the sum of partial pressures. As per the question, there is 30. Now, as per this scenario, P naught minus X value is given us as 2. So instead of this P naught minus X, I'll write 2. This 2 will go on this side. 30 minus 2 is 28, right? So it's X plus X by 2 plus X by 4. It is equal to 28. Take the LCM, that's 4. This is going to be 4X plus 2X plus X is equal to 28. So it's going to be 7X divided by 4 is equal to 28. So from here, X value will come out to be 16 atm. So you got the value of X. If you got the value of X, you're sorted. What do we have to calculate? We have to calculate Kp. How do you write the Kp expression? Partial pressure of NO2 at equilibrium, that is X atm, raised power stoichiometric coefficient 4. Partial pressure of H2 at equilibrium, that's X by 2, raised power stoichiometric coefficient, that's 2. Partial pressure of O2 at equilibrium, that's X by 4, raised power stoichiometric coefficient 1, divided by partial pressure of HNO3 at equilibrium, that is P naught minus X, raised power stoichiometric coefficient, that's 4. Now, my dear students, all these terms we already have. X is 16, so this is 16 raised power 4. X by 2 is 8, so it is 8 raised power 2. X by 4 is 4, 4 raised power 1. Divided by P naught minus X is 2, so this 2 raised power 4. Matter of calculation, solve it and get it killed. Yes? Is it clear? Is it clear, people? I hope you can solve these sort of questions from now on easily. I believe that you can do it. Is everything clear till here? Say yes or no in the chats. Quickly. I want answers from everyone, guys. And you know, my everyone means everyone, yeah? Correct? Correct, people? Perfect. Now comes one more topic, that is degree of dissociation. If you remember in the beginning, I told you Kp, Kc calculation is done either with the help of mole method or with the help of degree of dissociation method. So first of all, let's try to understand what degree of dissociation is all about. And once we understand what degree of dissociation is all about, then we can get to know we can get to know the Kp, Kc expression with the help of degree of dissociation. Yeah? Right? So people, try to understand what this degree of dissociation means. Degree of dissociation, first of all, it is represented by alpha. It is represented by alpha. It looks like infinity, but it's alpha, okay? The degree of dissociation is represented by alpha. How do you define this degree of dissociation? My dear students, it is defined as the fraction of reactant which gets dissociated into product. In the reaction, you would have seen till now, in the reaction, reactants basically, they break, they get converted into products. Reactants break, they dissociate. Dissociate means break, right? Reactants break into products. Now, that fraction of reactant which gets converted into product, that's what you call as degree of dissociation. For example, let's say again I've got the reaction like this. Okay, before writing the reaction, let me write its definition in this format. Alpha, degree of dissociation. Degree of dissociation. It is always equal. It is always equal to number of moles of reactants dissociated. Number of moles of reactants dissociated divided by initial moles of reactants taken. Number of moles of reactants dissociated divided by initial moles of reactants taken. So first of all, what is degree of dissociation? First of all, it is that fraction of reactant which gets converted into product. Mathematically, how do we write it? Alpha is equal to those moles of reactants which get dissociated into products divided by initial moles of reactants. Now try to understand how exactly I'm going to use it. Or you can, in short, you can write it like this. ND, number of moles of reactant dissociated divided by initial moles of reactant. You can write it like this as well. No issues at all. Divided by Ni. Now try to understand, people, how exactly I'm going to utilize this particular thing. First of all, if alpha is equal to ND divided by Ni, can I write ND will be equal to Ni multiplied by alpha, or leave this part aside? Let me write the reaction first. For example, you have got the reaction like this. A gas, it is in equilibrium with B gas plus C gas. Let's say this is the reaction. I'm assuming its degree of dissociation is X. Degree of dissociation is X. Imagine initially at time t is equal to 0. Imagine initially at time t is equal to 0. We have got A moles of reactant. So this has to be 0. This has to be 0. Right? This has to be 0. This has to be 0. Now, degree of dissociation here is X. Initial moles of reactant is A. If I use this particular result, we know alpha is equal to those moles of reactant which get dissociated divided by initial moles of reactant. Initial moles of reactant here are A. So can I get a term ND from here? ND will be equal to A times alpha. What is ND? ND represents, these are those moles of reactants which are getting converted into product. Till now, in mole method, I used to call this term as X. Till now, in mole method, I used to call this term as X. Now here, in place of X, I'm calling it as A alpha. I'm calling it as A alpha. So what is A alpha? These are the number of moles of reactants dissociated. These are the moles of reactants which have got converted into products. Right? Now try to understand. Initially, I had A moles at equilibrium. Let's assume out of A moles of reactants, how many are getting dissociated? How many are getting converted into products? Out of A moles of reactant, I'll say A alpha are getting converted. So I'll be left with A minus A alpha. These are the moles of reactants left in the container at equilibrium. Till now, this A alpha was called as X, right? A minus X. Now, process is very simple. 1 mole gives 1 mole. From A alpha, you get A alpha. 1 mole gives 1 mole. From A alpha, you get A alpha. Now these are what you call as, these are your moles of reactants and products in the container at equilibrium in terms of alpha. In terms of alpha. Correct? In terms of alpha. For example, there is a reaction like this. Let's say the reaction is simple. A gas, this is 2B gas, this is 5 times C gas. Imagine this is your reaction. Imagine this is your reaction. If the degree of dissociation is alpha, assume that initially you have got A moles of reactant. A moles of reactant. So this has to be 0, this has to be 0. Now, at equilibrium, out of A moles of reactant, how many got dissociated? Out of A, I'll say A alpha got dissociated. If A alpha got dissociated, how many will be left? A minus A alpha will be left. Correct? Now use stoichiometry. 1 mole gives 2 moles. From A alpha, you get 2 times A alpha. 1 mole gives 5 moles. From A alpha, you get 5 times A alpha. Now these are the moles of reactants and products in the container at equilibrium. Correct? Yes. So like this, you can easily calculate the moles of reactants and products in terms of what? In terms of alpha. In terms of alpha. Correct? In terms of alpha. Perfect, guys? In terms of alpha. Correct? For example, you have got the reaction like this. Let's say I'm writing a reaction. N2O4 gas in equilibrium with 2 times NO2 gas. Imagine this is your reaction. Degree of dissociation is alpha. Initially, you are starting with A moles of reactants. So this is 0. I want to write the Kp and Kc expression in terms of alpha. I want to write the Kp and Kc expression in terms of alpha. How am I going to do that? Same procedure. At equilibrium, we will be left with, out of A moles, A alpha would have got dissociated, so I'll be left with A minus A alpha. This is going to be 2 times A alpha because stoichiometric coefficient is 2, right? Let's assume the volume of the vessel is V liters. So if these are the moles of reactant product at equilibrium, so concentration of reactant and product at equilibrium will be moles divided by volume. These are the moles at equilibrium divided by total volume in liters. Now you can write the Kc expression. Kc expression will be concentration of NO2 at equilibrium raised power 2. So it will come out to be 2 2s are 4 A square alpha square divided by V square, whole divided by concentration of NO2 at equilibrium, which is A minus A alpha divided by V. So V and V got cancelled, right? So you got something 4A square alpha square divided by V multiplied by A minus A alpha. Now what you can do here is, this is 4A square alpha square divided by V as such. A you can take common. This is 1 minus alpha. So A and A got cancelled out. So from here you can get the Kc expression as 4A alpha square divided by V multiplied by 1 minus alpha. So this is your Kc for this particular reaction in terms of alpha. Can you get Kp as well? Can you get Kp as well? You should be able to do. First of all, in order to get the Kp, what do I need? I need the mole fraction of reactant product at equilibrium. To get the mole fraction, I would need the total moles at equilibrium. Total moles at equilibrium will be A minus A alpha plus 2 times A alpha, which is A plus A alpha. So divide this term with A plus A alpha. Even divide this term with A plus A alpha. So what did you get? You got the mole fractions. Now to get the partial pressure of reactant product at equilibrium, I need to multiply these mole fractions with total pressure of the mixture at equilibrium. So this is going to be A minus A alpha divided by A plus A alpha multiplied by total pressure of the mixture at equilibrium. Similarly, this is 2 times A alpha divided by A plus A alpha multiplied by total pressure of the mixture at equilibrium. You got the partial pressures. Now, since you got the partial pressures, now we can easily write the expression for Kp. Kp is going to be partial pressure of NO2 raised power 2, which will come out to be 2A alpha divided by A plus A alpha multiplied by Pt whole raised power 2, right? Divided by. Just a second, guys. Right. Divided by N2 for partial pressure is how much? N2 for partial pressure. This is A minus AX, A alpha multiplied by Pt divided by A plus AX. Perfect. Right? So I think you're done. You just have to put the values and you'll be getting the value of Kp. Correct, people? Correct? So this is how you get Kp, Kc expressions in terms of what? In terms of degree of dissociation. And do remember one simple thing, take a note of this as well. Sometimes in the questions, they won't directly give you the degree of dissociation. Do remember, they'll give you percentage dissociation. Percentage dissociation, it is nothing, it is degree of dissociation multiplied by 100. Percentage dissociation is nothing, it is degree of dissociation multiplied by 100. So sometimes in the question, they'll give you percentage dissociation. So percentage dissociation divided by 100 will give you alpha. Right? It will give you alpha. It will give you degree of dissociation. Let's try to solve few questions based on the same concept so that you can understand properly. One basic question I'm giving you. One basic. Straight basic question. Straight basic question. Yes, Abdul. Both actually mole method, degree of dissociation method, both are same. It is just names are different, nothing else. Nothing else. You can solve every question with the help of mole method. Every question you can solve with the help of mole method. Yeah? Okay. Now look at this. Calculate Kp for the dissociation of 1 mole of PCl5, which is 20% dissociated with the total pressure at equilibrium of 1 atm. Right? Right? Now people, as per the question is concerned, PCl5 gas is being dissociated. It is being dissociated into what? It will get dissociated into PCl3 gas plus Cl2 gas. First of all, check whether the reaction is balanced or not. Yes, the reaction is balanced. Okay. Now, initially at time t is equal to 0, how do we start? We start with A moles of reactant. This is 0, this is 0. Calling it this as alpha. Now, same procedure at equilibrium. This has to be A minus A alpha. Even this will be A alpha. Even this will be A alpha. Correct? Calculate the total moles at equilibrium. This, which will be A plus A alpha. So, dividing every term with A plus A alpha. Dividing every term with A plus A alpha. I got the partial pressures, right? Multiplying every term with total pressure of the mixture at equilibrium. Multiplying every term with the total pressure of the mixture at equilibrium. Now I got the partial pressures. Now I got the partial pressures. Now, get the exact partial pressures because I can see some terms will get cancelled. If you take A common here, A will get cancelled. So it will be 1 minus alpha multiplied by total pressure of the mixture at equilibrium. Total pressure of the mixture at equilibrium is 1 atm. So PT is 1 divided by 1 plus alpha, right? Similarly, A cancel. So this is alpha divided by 1 plus alpha. PT value is 1. A cancel. So this is alpha divided by 1 plus alpha. PT values cancel. Correct? PT values cancel. Now, my dear students, do we know the alpha value? We know the percentage dissociation, 20. If percentage dissociation is 20, that means alpha will be 0.2. Correct? 2 minutes back I told you, alpha will be 0.2. Now get the KP expression. KP expression, partial pressure of PCl3. Alpha divided by 1 plus alpha. So 0.2 divided by 1.2. 0.2 divided by 1.2. This is the partial pressure of PCl3 at equilibrium multiplied by partial pressure of Cl3 at equilibrium. It is again 0.2 divided by 1.2 raised for stoichiometric coefficient divided by partial pressure of PCl5. 1 minus 0.2 is 0.8. 0.8 divided by 1.2. 0.8 divided by 1.2 whole raised per stoichiometric coefficient 1. Solve this, get the value of Kp. Done, understood? I hope you can easily solve these sort of questions from now on. I hope you can do that. I hope you can do that. I hope you can do that. Yeah? Right, guys? It's completely your choice. It's completely your choice. Which method do you want to choose? If you want to go for mole, you can go for mole. If you want to go for volume, degree of dissociation, you can go for that. Okay? Right, guys? Can you solve this question? Pretty much simple. 50% HI is dissociated into H2 and I2 at equilibrium. Calculate Kc. Do I need to solve this? Do I need to solve this question? Tell me that. Whatever method you want to use, you do that. Whatever method you want to use, you do that. Start with A00. If you want to use alpha method, A minus alpha, A minus A alpha, this will be A alpha, this will be A alpha. Sorry, not A alpha. This will be A alpha by 2, this will be A alpha by 2. Correct? You have to calculate Kc. Assume that total volume is V. Divide by total volume, you will get the concentration. Some terms will get cancelled out. And Kc expression you can easily get. Because alpha is given as 1 by 2. 50 by 100, that's 1 by 2. Alpha is given as 1 by 2. This can be solved. Do let me know the answer of this particular question in the comment section of the video. Okay? Comment section of the video I want. Okay. Let's try to see one more thing. Let's try to see one more question. This is again a similar type of question. Let's give it a try. Let me show you the procedure again. This is N2O4 gas. It is in equilibrium with 2 times NO2 gas. Perfect. The degree of dissociation of N2O4 at 1.5 atm. At 1.5 atm and 25 degrees centigrade is 0.25. Degree of dissociation is 0.25. Right? Calculate Kp. Again, guys, this is same. I don't want to solve this. This is A, this alpha, this is 0. Now at equilibrium, this is A minus A alpha. This is 2 times A alpha. Divide with total moles. Total moles will be A minus A alpha plus 2 times A alpha. This is going to be A plus A alpha. Divide this with A plus A alpha. A gets cancelled, right? So this is 1 minus alpha. Divide by 1 plus alpha. This is 2 times alpha. Divide by 1 plus alpha. So these are the mole fractions. Multiply with total pressure. Total pressure is 1.5. Here the total pressure is 1.5. These are the partial pressures, right? Even alpha value you know. Even alpha value you know, that is 0.25. Put the value of alpha, you'll be getting the exact partial pressures. Once you get the exact partial pressures, you can easily calculate Kp, right? You just have to write Kp expression. I'm not solving this. I'm not solving. I have solved this already, but further you do it. I'm not doing it. Look at this. Look at this. Look at this, guys. The question says if 1:3 mixture, if 1:3 mixture of N2 and H2 yields NH3, 20% by volume at 30 atm. Calculate Kp. Try to understand what is given in the question. Let me make the language of the question comparatively easy. As per the question is concerned, volume percentage of NH3 at equilibrium is given. Let me tell you first of all, volume percentage. It is again a fancy terminology. It is basically volume percentage is nothing. It is volume fraction multiplied by 100. Right? Volume fraction multiplied by 100. As per the question, volume percentage of NH3 is given. How much? Volume percentage of NH3 at equilibrium is given 20. So 20 divided by this 100 will be the volume fraction of Cl2. Right? Since at equilibrium, all the measurable properties like pressure, temperature constant, and at constant pressure and temperature, volume fraction is nothing, that is mole fraction. So basically, indirectly, you got the mole fraction of Cl2 at equilibrium. I hope you are trying to understand this. Indirectly, you got the mole fraction of Cl2 at equilibrium, right? Perfect. What do we have to calculate? Kp. As per the question is concerned, we had 1:3 mixture. So it is 1:3 mixture of N2 and H2 yields NH3, right? At 30 atm. Total pressure of the mixture is given as 30 atm. Total pressure of the mixture is given as 30 atm, right? Now the same approach which we have been using. So at equilibrium, let's assume that out of 1 mole, X moles have reacted. So I'm left with 1 minus 6. 1 mole reacts with 3 moles, X will react with 3X. So this will be 3 minus 3X. And at the end, this will be 2X. These are the moles of reactants and products in the container at equilibrium. If these are the moles of reactants and products at equilibrium, tell me how many total moles are there in the container at equilibrium? Total moles will be there. 1 minus X plus 3 minus 3X plus 2X. 3 plus 1 is 4, right? It will be 4 minus 2X. These are the total moles present in the container at equilibrium, correct? These are the total moles present in the container at equilibrium. If you got the total moles, I'm dividing this 1 minus X by the total moles. Total moles is 4 minus 2X. Even this I'm dividing by 4 minus 2X. Even this I'm dividing by 4 minus 2X. What did I get? I got the mole fraction. I got the mole fraction of each reactant and product at equilibrium. But in order to get the Kp, do I need mole fraction? No, I do not need that. What do I need? I need partial pressures. But before doing the partial pressure, before calculating the partial pressures, we know mole fraction of Cl2 at equilibrium is 0.2. And as per this scenario, just a second guys, this is not Cl2. What is it? Why am I writing Cl2 here? Why am I writing Cl2 here? This is NH3, right? This is NH3. This is NH3. Mole fraction of NH3, already we know that is nothing but 2x divided by 4 minus 2x. And this value is equal to 0.2. 0.2 makes it 2 by 10, right? So 2 and 2 gets cancelled. So this is 10x is equal to 4 minus 2x. So I can say this is 12x is equal to 4. X is equal to 1 by 3. X value is equal to 1 by 3. If x is 1 by 3, put the value of x here. You'll be getting the exact mole fractions of each reactants products at equilibrium, right? You'll be getting the exact mole fractions of reactants products at equilibrium. Whatever values you get, multiply this value by total pressure 30. This is partial pressure. Multiply this value, whatever value you get after putting the value of x, right? Multiply it with total pressure. Similarly, multiply this with total pressure. What do we get? We got the partial pressures of each reactants products. Once you get the partial pressures, you can easily write the expression for Kp. Guys, is this solvable question? Is this solvable question? Will you be able to solve this sort of a question again from now on? Quickly. Quickly. Let me know once in the chats if this is super clear to everyone. Let me know once in the chats, people, if it is super duper clear to everyone. You got the process. The process is important here. Again, I'm telling you, the process is important. Have you solved the equation? That's important. Have you solved the equation? That is important. Okay. So, can you do this sort of a question? Can you do this sort of a question? Here, no need to use any formula. You can solve this question in like 2 seconds. No need to use any formula here. You have got a solid which is undergoing decomposition to form a mixture of gases. The total pressure at equilibrium is 10 bar. Total pressure at equilibrium is 10 bar. Calculate Kp. See guys, solid. Does solid contribute towards the total pressure? Does solid contribute towards pressure? No. Gases contribute. So basically, once equilibrium is established in the reaction, there will be some moles of this solid left. There will be some moles of this formed. There will be some moles of this formed. So at equilibrium, can you let me know how many gases will be there? At equilibrium, there will be two gases. This X and this Y. Stoichiometry is 1:1. Stoichiometry is 1:1. So let's assume at equilibrium pressure due to this is X ATM. Pressure due to this will be also X ATM because stoichiometry is 1:1. If the stoichiometry here was 1:2, then if it was X, this should have been 2X. If the stoichiometry was 1:3, if this was X, then this should have been 3X. Done? This one is not going to contribute. This one is not going to contribute towards the pressures. Right? As per the question, the total pressure at equilibrium is 10 atm. Total pressure at equilibrium will be X plus X, which makes it 2X. So 2X is 10, which means that X is 5 atm. If you got X, calculate Kp. Kp is nothing. Partial pressure of this raised power 1. Partial pressure of this raised power 1. So X into X is X square. X square is 25. This is atm. And this is going to be square as per the units. Done? I hope you got it. Solid is decomposing. So at equilibrium, there will be some moles of solid left. There will be some moles of this gas form, some moles of this gas form. So at equilibrium, there will be two gas in the container. Right? At equilibrium, there will be two gas in the container. Perfect. One is going to be this, one is going to be this. This is not going to contribute towards anything. So if pressure due to this X is X, so this has to be X as well. Why? Because stoichiometry is 1:1. If it was 1:2, then if this is X, this should have been 2X. 1:3, X 3X. 1:4, X 4X. So total pressure of the mixture at equilibrium will be this plus this. This is not going to contribute. X plus X makes it 2X. So 2X is equal to 10 as per the question. From there, X is equal to 5. If X is equal to 5, Kp is going to be X square. Done and dusted. Right? Done and dusted. Okay? So, one more topic to be killed. Have you studied this particular topic before? Have you studied this particular topic before? Calculation of degree of dissociation using vapor density measurement. Quickly. Have you studied this? This is again one important topic, guys, by the way. This is again one important topic. Okay, so let's see what exactly it means. Let's see what exactly it means. Try to understand what exactly I'm going to say. Okay, step by step, I'm going to tell you the things. So here, we are going to do the calculation of degree of dissociation using vapor density measurement. Using vapor density measurement. We have to calculate degree of dissociation basically. My dear students, I'm going to use the first case, which I'm calling as the case of dissociation. The case of dissociation. So basically, I'm going to show you how to calculate degree of dissociation with the help of vapor density measurement. So for that purpose, what exactly I'm planning to do? I'm planning to take a reaction like this. A gas in equilibrium with N times B gas. This is the reaction I have planned to take. Okay. Let's assume degree of dissociation here is alpha. Right? And I'm assuming at the same time, imagine N value is greater than 1. N value is greater than 1. Here the stoichiometric coefficient is 1. Here the stoichiometric coefficient is N. And this N, it is greater than 1. So it can be 2, it can be 3, it can be 4, whatever. Right? So can I say 1 mole of A is giving us more than 1 mole of B? Since N is greater than 1. N can be 2, it can be 3, it can be 4, whatever. Can I say 1 mole of A is giving us more than 1 mole of B? if 1 mole of if 1 mole of reactant is giving us more than 1 mole of product, if 1 mole of reactant is giving us more than 1 mole of product, can I say this is the case of dissociation? So A is breaking into more than 1. This is the case of dissociation. So this alpha I'll be calling as degree of dissociation. This alpha here I'll be calling as degree of dissociation. Correct? So this is the case of dissociation, this understood. Now, imagine at time t is equal to 0. We have got A moles of this reactant. So this has to be 0. Correct? Now at equilibrium, out of A moles of reactant, how many moles would have got dissociated? Out of A moles, I'll say A alpha would have got dissociated. So how many will be left? A minus A alpha will be left. Right? Now, 1 mole gives n moles. So A alpha moles are going to give us n A alpha moles. So these are the moles of reactants and products. These are the moles of reactants and products present in the container at equilibrium. Tell me one thing. How many initial moles of reactants were there in the container? How many initial moles? This plus this. So A. These were the initial moles of reactants in the container. How many moles are present in the container at equilibrium? How many moles are present in the container at equilibrium? That's going to be this term plus this term. So it is A minus A alpha plus N A alpha. Correct? So I'll say total moles present in the container at equilibrium will be equal to A. I'm writing as such. Among these two, I'll be taking A alpha as common. So if I take A alpha as common, right? If I take A alpha as common here, it is going to be N minus 1. It's going to be N minus 1. Correct? I hope this particular thing is clear. These are the initial moles. These are the total moles present in the container at equilibrium. I've taken A alpha common among the two. So A alpha is common. So it has to be N minus 1. Why did I do it? There is a logic behind that. First of all, whatever I told you till now, just keep it as such. Keep it as such. My dear students, I hope you remember. One topic which we have discussed in the mole concept. I had given you one result, if you remember. That was molar mass is equal to 2 times the vapor density. Do you remember this? Molar mass is equal to what? 2 times the vapor density. I hope you remember. Molar mass is equal to 2 times vapor density. So what I'll be doing here, I'll be defining 2 terms. One I'll be calling as capital D. One I'll be calling as small d. What is capital D? What is small d? Exactly, day 1. Day 1 was our mole concept. So capital D is what we call as theoretical vapor density. Capital D is what I call as theoretical vapor density, or you can call it as vapor density of the reactant. Vapor density of the reactant at time t is equal to 0. This is my reactant. This is my reactant A. Capital D is vapor density of this reactant. Vapor density of this reactant. And what is vapor density? Vapor density is density of the gas divided by density of hydrogen gas. I hope you know that. Vapor density of the gas is equal to density of the gas divided by density of hydrogen gas. So capital D is nothing. It is what I call as theoretical vapor density, or vapor density of the reactant. Vapor density of the reactant, right? Now, vapor density is equal to molar mass by 2. So if this is vapor density of the reactant at time t is equal to 0, it has to be molar mass of reactant divided by 2. It has to be molar mass of reactant divided by 2, in short. Right? It has to be molar mass of reactant divided by 2. Now, here I'm defining one more term, small d. Small d is something which I call as experimental vapor density. Experimental vapor density, or you can call it as vapor density of the mixture at equilibrium. Vapor density of the gaseous mixture at equilibrium. At equilibrium, we have got a gaseous mixture, and whatever will be the vapor density of that gaseous mixture, that is represented by small d. Right? So small d will be equal to small d. That is the vapor density of the mixture at equilibrium. At equilibrium, you have got a mixture of gas, right? So it has to be molar mass of the mixture divided by 2. But If you remember, molar mass of the mixture is something we call as average molar mass. So average molar mass of the mixture at equilibrium divided by 2. I hope you remember this as well. Something which we have discussed in mole concept. So capital D is equal to molar mass of reactant by 2. Small d is equal to average molar mass of the mixture at equilibrium divided by 2. Okay, perfect. Now guys, tell me one thing. Have you studied this result? Number of moles is equal to given mass by molar mass. Absolutely. Number of moles is equal to given mass by molar mass. Now instead of molar mass, can't we write 2 times vapor density? Absolutely. So can I say number of moles is basically inversely proportional to vapor density? Number of moles is inversely proportional to vapor density. Absolutely. Number of moles is inversely proportional to vapor density. Now, if number of moles is inversely proportional to vapor density, if number of moles is inversely proportional to vapor density, if I write initial moles divided by equilibrium moles, if I write something like this, Ni divided by Neq, Ni divided by Neq, moles is inversely proportional to vapor density. Can I say it will be basically vapor density of the mixture at equilibrium divided by initial vapor density, right? Since moles is inversely proportional to vapor density, so initial moles is inversely proportional to initial vapor density, equilibrium moles is inversely proportional to equilibrium vapor density of the mixture, right? Now, initial moles are how much? A divided by total moles at equilibrium is how much? A plus A alpha multiplied by n minus 1 is equal to vapor density of the mixture at equilibrium. Vapor density of the mixture at equilibrium is small d. Initial vapor density, that means vapor density of the reactant. That means theoretical vapor density. It's capital D. It is capital D. If you just reshuffle it, if you just cross multiple, you will be getting the value of alpha. Alpha will be capital D minus small d divided by small d multiplied by n minus 1. My dear students, this is the result. This is one very, very, very important result which you have to remember. Whenever you will have to calculate alpha, you can use this particular result as well. Capital D is what you call as theoretical vapor density or vapor density of a reactant at time t is equal to 0. Small d is the vapor density of the mixture at equilibrium. Small d, you know, what is N? N means number of moles of product formed from 1 mole of reactant. Number of moles of product formed from 1 mole of reactant. So what is this N? N means the number of moles. The number of moles of product formed. Number of moles of product formed from 1 mole of reactant. The number of moles of product formed from 1 mole of reactant. For example, you have got the reaction like this. PCl5 gas in equilibrium with PCl3 gas plus Cl2 gas. Can you let me know what is the value of N here? 1 mole is giving 1 plus 1, 2 moles. So N value is 2. N value is 2. Tell me this. Let's say 2A gas in equilibrium with 3B gas plus 4C gas. Can you let me know what is the value of N here? 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 See, 2 moles are giving us 7 moles. 2 moles are giving us 437 moles. So 1 mole will give 7 by 2. 7 by 2 is 3.5. N value is 3.5 here. Yeah, N value is 3.5 here. As simple as that. So guys, this is the expression which we have to remember. Alpha is equal to capital D minus small d divided by small d multiplied by n minus 1. Right? And in case of dissociation, sometimes if you get confused, like which one is capital D, which one is small d, do remember, in case of dissociation, capital D will be greater than small d. In case of dissociation, capital D will be greater than small d. Okay. Now here I want to do one more thing. In case of dissociation, I told you. In case of dissociation, I told you exactly how to get the value of alpha. Alpha is nothing. It is capital D minus small d divided by small d multiplied by n minus 1. So you can write it like this. N minus 1 here. So it's alpha multiplied by n minus 1 is equal to, it is going to be capital D divided by small d minus 1. Or you can say capital D by small d is equal to 1 plus n minus 1 into alpha. Correct? Capital D divided by small d is equal to 1 plus n minus 1 into alpha. For example, you have to plot a curve here. Imagine you have to plot a curve here. curve is between capital D divided by small d versus alpha. Capital D versus divided by small d versus alpha. Capital D by small d you are plotting along y-axis. Alpha you are plotting along x-axis. N minus 1 is your m. This term is c. In between sign is plus. Y is equal to mx plus c. Y is equal to mx plus c. Straight line. What about its slope? Slope means m. M value here is n minus 1. What about this intercept? Intercept means c. And c value here is equal to 1. Perfect. But this is valid for dissociation. This is valid for dissociation. Now here we have got case 2. Then let's see what type of questions are asked. Case 2 means association. Case 2 means association. Case 2 means your association. I'm sorry. And alpha here won't be called as degree of dissociation. It will be called as degree of association. Here alpha I'll be calling as degree of association. Try to understand, guys, how exactly I'm going to tackle with this. For example, I'm writing a reaction Na gas in equilibrium with Na gas is in equilibrium with An gas. Let's say this is the reaction, or in simpler words, I'm writing it like this. Na gas in equilibrium with B gas. Assume that N value is greater than 1. Assume that N value is greater than 1. Understand? Here the stoichiometric coefficient is N. Here the stoichiometric coefficient is 1. If N is greater than 1, that means it can be 2, it can be 3, right? So more than 1 particles are associating to give us 1 particle. More than 1 particles are associating to give us 1 particle. So is this a case of association or dissociation? It is absolutely the case of association. Here alpha I'll be calling as degree of association. Here alpha I'll be calling as degree of association, right? Now people, in this particular case, I'm not going to derive the expression here again. In this particular case, if you have to calculate alpha, alpha here is going to be capital D. You can use the same process to derive alpha, but no need of derivation at this point of time. Just remember it directly. It's capital D minus small d divided by small d multiplied by 1 by n minus 1. So just instead of n minus 1, I'm writing 1 by n minus 1, nothing else. Rest everything is same. This is how you calculate degree of association. Capital D, you know, it is the vapor density of the reactant. Small d is the vapor density of the mixture at equilibrium, right? Capital D is equal to molar mass of reactant by 2. Small d is equal to average molar mass of the mixture divided by 2. Correct, people? Is this clear? Is this clear? Let's see what kind of questions can be asked from this approach. Then we can take a break also. After the break, there are just 2 topics left. One is Chatelier and one is reaction quotient. That won't take us more than 1.5 hours after the break. But first, let's try to see what kind of questions are asked here. Okay, let's try to see what kind of questions are asked here. Okay, this is the first question. This is the first question. As far as the question is concerned, first of all, we are given the reaction, and let me write the reaction. Reaction is N2O4 gas. It is in equilibrium with 2 times NO2 gas, right? 2 times NO2 gas. Before solving the question itself, tell me what the value of N. 1 mole gives 2 moles. So N value is 1. Correct? Before looking at the question, what the question says. The vapor density of N2O4 and NO2 mixture at equilibrium. Vapor density of the mixture at equilibrium, that is small d. So small d value is given as 30. If you ask me what will be capital D then, you know, capital D is nothing. It is molar mass of reactant divided by 2. Reactant here is N2O4. Its molar mass is 92 divided by 2. The value is 46. So capital D is 46. Right? Capital D is 46. What do we have to calculate? Calculate the percent dissociation. Percentage of N2O4 dissociated at equilibrium. Right? So guys, for that I'll be calculating alpha. Alpha is capital D minus small d divided by small d multiplied by n minus 1. Capital D is 46, small d is 30, small d is 30, n minus 1. The value comes out to be how much? 0.52 or 0.53, something like that, right? It will be 0.53 almost. If alpha came out to be 0.53, I was supposed to calculate percentage dissociation. Can I say percentage dissociation will be nothing? It will be alpha multiplied by 100. Alpha you got. So I would say at equilibrium, I would say at equilibrium, 53% of N2O4 would have got dissociated. At equilibrium, I would say 53% of N2O4 has got dissociated. Yes? Simple and basic question this was. Simple and basic question this was. Okay, one more question on your screen. Let's exactly see what the question says. In the reaction, the vapor density of the mixture is reduced to half. Half of what? Half of initial vapor density. As per the question, it is mentioned that vapor density of the mixture, which is small d, vapor density of the mixture at equilibrium, which is small d, is reduced to half of its theoretical vapor density, to half of its initial vapor density at equilibrium. If the percentage dissociation is 25, that means alpha has to be 1 by 4, 2500. Okay. Calculate how many moles of B will be formed on starting with 2 moles of A. So you are starting with 2 moles of A. And what do we have to calculate? How number of moles of B formed at equilibrium. Number of moles of B formed at equilibrium. That's something which we need to calculate. Try to understand. Try to understand. So my dear students, as per this particular question, the reaction is like this. A gas in equilibrium with N times B gas. This is your reaction. Perfect. First of all, I don't know its alpha value. What do we have to calculate? We have to calculate the moles of B formed at equilibrium. Moles of B formed at equilibrium. So assume that you have got A moles of reactant. This is 0. Degree of dissociation, for example, alpha. So at equilibrium, I'll be left with A minus A alpha. Now, 1 mole gives N moles. From A alpha, you get Na alpha. Right? So basically, you have to get this value. You have to get the value of this particular term. As per the question, we were supposed to calculate the moles of B at equilibrium. The moles of B in the container at equilibrium, which you got to know, that is nothing, that is Na alpha, right? So N value we can easily calculate somewhere. A value is given, alpha value is given. So this is given, this is given. What do we need? We just need N value. How do we get N value? Right? How do you get the N value from here? How do you get the N value from here? My dear students, this is the case of dissociation, right? It is mentioned that it's 25% being dissociated. So I'll use this alpha expression. Alpha is equal to capital D minus small d divided by small d multiplied by N minus 1. Alpha, as per the question, is given to me as 1 by 4, right? Capital D I'll write as such. Small d is capital D by 2. D minus capital D by 2. Capital D minus capital D by 2 is D by 2. Instead of small d, you can again write capital D by 2. And this is N minus 1, right? So this term cancel. So I got to know 1 by 4 is equal to 1 by N minus 1. Or you can say N value is equal to 5. So you got the N value. You got the N value. So if you got the N value, you're done. You're sorted. Number of moles of B in the container at equilibrium is equal to N value is 5. A means initial moles, that's 2. And alpha is given to us as the equation, that's 1 by 4. So the value comes out to be 2.5. So you got to know that 2.5 moles of B have got formed in the container at equilibrium, which we were supposed to calculate. Is this clear? Is this clear, people? Is this clear, people? Quickly in the chats. Quickly in the chats. Is this clear? Yeah? One similar question. Calculate if the percentage dissociation means you can calculate alpha from here. Right? You can calculate alpha from here. It is 40 divided by 100, 0.4. Right? So alpha is given to me as 0.4 as per the question. Perfect. Calculate the vapor density of the equilibrium mixture. Vapor density of the mixture at equilibrium is small d. Small d we have to calculate. So this is pretty much simple. Just direct expression. Alpha is equal. Since this is the case of dissociation, capital D minus small d divided by small d multiplied by N minus 1. Right? Alpha is 0.4. Perfect. What is capital D? Capital D means molar mass of reactant by 2. What is the molar mass of this particular term? PCl5. Molar mass of PCl5 is nothing. It is 104 point something. Is that? No. What is the molar mass of PCl5? Let me check the solution directly. See, capital D. Capital D is molar mass of reactant divided by 2. Perfect. So it will come out to be 104.25. It is a formula-based question. Capital D is given, right? Small d we have to calculate. N value. 1 mole gives 2 moles. So N is given. Alpha is given. Everything is given, guys. I mean, this is something which you could have easily solved. I was not supposed to solve this question. You could have done it easily because all the parameters are given. It is just one formula, one equation, one unknown. Nothing else. It's a wastage of time. This you could have easily solved on your own. This you could have done easily. Okay? All right. What about this question? What about this question? Capital D by D versus alpha curve is given and its slope is given. And already few minutes back I've told you capital D by D versus alpha slope is nothing, it's n minus 1. So n minus 1 value is 2. So n value will be 3. So you got the n value first of all by just looking at the curve. By just looking at the curve. Now the question is saying for the reaction, the curve between this and this is given. Calculate the percentage dissociation when experimental vapor density becomes equal to half of theoretical vapor density. When small d becomes equal to capital D by 2, at that time we have to calculate alpha. So alpha will be equal to capital D minus small d divided by small d multiplied by n minus 1, right? Alpha we have to calculate. Capital D minus small d is capital D by 2, small d is capital D by 2 multiplied by n minus 1. D minus d by 2 is d by 2, d by 2, d by 2 cancel. Alpha is equal to 1 divided by n minus 1. N is 3, right? 3 minus 1. It is 1 divided by 2, which comes out to be 0.5. If alpha is 0.5, as per the question, percentage dissociation is equal to alpha multiplied by 100. So it has to be 0.5 multiplied by 100. So the value simply comes out to be 50%. I would say 50% of the reaction would be completed, then only your experimental vapor density becomes equal to theoretical vapor density, right? If the value of n is 3. Okay? Is this clear, my dear students? Doing the Chatelier principle, it is mandatory to learn about reaction quotient first. It is mandatory to learn about the topic reaction quotient because without reaction quotient, you cannot learn the Chatelier principle. Okay? So what this reaction quotient exactly is all about? My dear students, try to understand. It's a very simple and basic thing. For example, I have got a reaction like this. N1A aqueous, or let me just keep it like this. N1A gas plus N2B gas, it gives N3C gas plus N4D gas. This is one reaction which I have taken into consideration over here. As you can see, the reaction is reversible, right? The reaction is reversible. First of all, for example, I want to write the equilibrium constant Kc expression for this particular reaction. I can do that. You know it, right? How do you know how to write the Kc expression? Start with the product. It's going to be concentration of C at equilibrium raised power n3, concentration of D at equilibrium raised power n4 divided by concentration of A at equilibrium raised power n1, concentration of B at equilibrium raised power n2. This is how exactly you write the reaction quotient. This is exactly how you write the equilibrium constant. This is the expression of your equilibrium constant. Now, my dear students, in this particular expression, all these concentrations of reactants and products I have taken at equilibrium. This is the concentration of C at equilibrium. This is the concentration of D at equilibrium, A at equilibrium, B at equilibrium. So all these concentrations which I have taken over here in order to write the Kc expression, all these concentrations I have taken when equilibrium was established in the reaction, right? When equilibrium was established in the reaction. Now, people, if I write the similar expression like this, concentration of C raised power n3, concentration of D raised power n4, concentration of A raised power n1, concentration of B raised power n2. So you see, I wrote the similar expression. What is the difference between the expressions? In this particular expression, all the terms, all the concentrations were taken when equilibrium was attained in the reaction. But here, I am taking all the concentrations of reactants and products at any stage apart from equilibrium. What is the difference between the two expressions? Here, all these concentrations, concentration of reactants and products, they were taken once equilibrium was established in the reaction. I'm writing the similar expression, right? But I'm writing the similar expression at any stage apart from equilibrium. Whenever you write the similar expression at any stage apart from equilibrium, that is something which you call as reaction quotient. That's what you call as reaction quotient, right? I hope you got it. Expressions are similar. What is the change? What is the change? In this expression, all the concentration terms are taken at equilibrium. I wrote the similar expression at any stage apart from equilibrium. When you write the similar expression, like the equilibrium constant, but at any stage apart from equilibrium, you call that as the reaction quotient expression. So this is your reaction quotient expression. This is your equilibrium constant expression. Okay. Now, my dear students, if you remember in the beginning, I told you, why do all the reversible reactions want to attain equilibrium as quickly as possible? What is the reason for that? What is the reason for that? Why all the reversible reactions would want to attain equilibrium as quickly as possible? Because equilibrium is considered to be the most stable state of the system, right? Equilibrium is considered to be most stable state of the system. Agreed? That is why every reversible reaction would want to attain equilibrium as quickly as possible. Okay? Now you tell me, if by chance you have a reaction for which QC and KC are equal. Let's say you have a reaction for which QC and KC are equal. First of all, understand how QC and KC will be equal. QC and KC will be equal only if the concentration of C is equal to the concentration of C at equilibrium. If the concentration of D is equal to the concentration of D at equilibrium. If this is equal to this and this is equal to this. So any reaction whose QC will be equal to KC, I'll say that particular reaction is at equilibrium. That is already stable. That is already at its stable state. Any reaction whose QC is equal to KC, we say that reaction is at equilibrium, that is already present at its stable state. Right? The reaction is present at its stable state. At its stable state. Okay? Now, by chance, if QC for a reaction, if I'll be having a reaction whose reaction quotient is not equal to equilibrium constant. Let's say I've got a reaction whose reaction quotient is not equal to equilibrium constant. What does that mean? That means the reaction is not at equilibrium. That means the reaction is not present at its stable state. That means the reaction is not present at its stable state. If QC of the reaction is not equal to its KC, that means the reaction is not present at its stable state. The reaction is not at equilibrium. Okay? The reaction is not at equilibrium at that point of time. But reaction would want to be at equilibrium. So reaction would want its QC to get equal to KC. Reaction would want its QC to get equal to KC. Because when QC gets equal to KC, we say equilibrium is established. Then the system is present at its stable state. Reaction is present at its stable state. If by chance you have got any reaction whose QC is not equal to equilibrium constant, so that means the system is not present at its stable state. But system would be present at its stable state. So system would want its QC to get equal to KEQ. System wants its QC to get equal to its KC. Because if QC gets equal to KC, I will say equilibrium is established, stability is attained, right? Right, people? So tell me one simple thing. Simple thing. If you have got the reaction whose QC is, for example, less than KC. Let's say you have got a reaction whose QC is less than KC. That means system is not present at its stable state. But system would want to attain stability. How system will attain stability? If by chance system would make its QC value equal to KC. If by chance system would want its QC value equal to KC. If by chance system will make its QC equal to KC. How is that possible? See, We have got a reaction whose QC is less than Kc. So what should system do? Can I say system has to increase its QC value? Then only it can get equal to Kc. If QC for a reaction is less than Kc, that means system has to increase its QC value. Then only it can get equal to Kc. Now, how system will increase its QC value? How QC value will get increased? When numerator increases and denominator decreases. Numerator increases means concentration of C and B has to increase. Concentration of A and B has to decrease. Concentration of C and D has to increase. Concentration of A and B has to decrease. When is that possible? When is that possible? When concentration of C and D will increase? When the reaction shifts forward. So in this particular case, when QC is less than Kc, I would say reaction shifts forward. Or I would say forward reaction is favored. I would say forward reaction is favored. Right? Simple. Now by chance, tell me one thing. If QC for a reaction was greater than Kc, if QC was greater than Kc, again, the system is not at stable state. Because which is the stable state? Stable state is the one at which QC is equal to Keq. That is equilibrium state. Right? If by chance you have got a system whose QC is less than Kc, whose QC is greater than Kc, but if every system's QC would want to be equal to Kc, so what this QC has to do? Has the value of QC to be reduced or increased? Can I say if for any reaction QC is greater than Kc, system will try to decrease the value of QC, then only it can become equal to Kc. Now how QC will decrease? How QC will decrease? How QC will decrease? QC will decrease if this term decreases and this term increases. This term decreases, that means concentration of products should decrease. Concentration of reactants should increase. When is that possible? When will the concentration of products decrease and concentration of reactant increase? When backward reaction is favored. Right? So in this particular case, I would say backward reaction is favored. Backward reaction is favored. So my dear students, in short, what you have to remember, if QC is not equal to Kc, but always do remember QC, every system wants its QC to be equal to Kc. Accordingly, whatever questions will come in front of you, you can easily solve them. How exactly? Have a look. First of all, tell me, is this point clear to you? Do remember one simple thing. Every system wants its QC to be equal to Kc. Then only equilibrium will be established. Right? Then only stability will come. Correct? If QC of the reaction is less than Kc, then system has to increase its QC value so that it becomes equal to Kc. If you have got a system whose QC is more than Kc, then QC has to decrease its value. Then only it will get equal to Kc. Accordingly, you can say whether forward reaction is favored or backward reaction is favored. As simple as that. For example, a simple question I'm giving you. A reaction I'm giving, it's Kc I'm giving, and at any time t, I'm giving you the concentrations of each reactant and product. I'm asking you, predict the direction of shift. Predict the direction of shift. So first of all, at any time t, if I calculate QC is going to be concentration of N2 raised power 1 multiplied by concentration of H2 raised power stoichiometric coefficient 3 divided by concentration of NH3 raised power stoichiometric coefficient, that is 2. Right? Perfect. Right, people? Yes? Can you calculate its value? How exactly it's going to be? This is going to be 1 divided by 2. 2s are 4 into 10 raised power minus 2, which will be 10 raised power 2 divided by 4. The value comes out to be 100 by 4. 100 by 4 is 25. So you got the QC value. Compare QC with Kc. Compare QC with Kc. I'll say in this particular case, QC is greater than Kc. In this particular case, QC is greater than Kc. And when QC is greater than Kc, QC will try to decrease its value. Then only it can become equal to Kc. How QC will decrease its value? When backward reaction is favored. So, answer of this particular question, forward or backward? It's absolutely going to be backward. Yes, it's absolutely going to be backward. Similarly, 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 again a reaction, its Kp is given. Its Kp is given. And we are given with the partial pressure of reactant and product at some time t. We have to predict the direction of shift, forward or backward. Again, what I'll be doing? I'll be calculating Qp here. Qp is going to be partial pressure of N2 raised per stoichiometric coefficient, partial pressure of H2 raised per stoichiometric coefficient, partial pressure of NH3, that is 3 raised per stoichiometric coefficient. So it is 2 divided by 3, 3s are 9. Correct? 2 by 9. The value comes out to be 0.2. Perfect? 0.2 approximately. Now compare Qp and Kp. I can categorically say Qp is less than Kp. And if Qp is less than Kp, but what Qp wants? It wants to increase its value so that it becomes equal to Kp. How will it will increase its value? When the forward reaction is favored. Correct? Correct? So one thing you have to remember, when reaction quotient is not equal to equilibrium constant, system will always try to make sure that reaction quotient gets equal to equilibrium constant by anyhow. I hope this point is clear. I hope this point is clear, because when reaction quotient, equilibrium constant are equalized, at that point of time you say equilibrium is established, and once equilibrium is established, we say system is at its maximum stable state. Okay? Perfect. Now guys, it is the time to discuss the Lee-Chatelier principle. It is the time to discuss the Lee-Chatelier principle. What is the Lee-Chatelier principle all about? Try to understand. What is Lee-Chatelier principle all about? Try to understand. This is something important, and here I'm going to make you understand a lot of important things. Maybe you would have studied. See, I'll write the statement. I'll write the statement first. As per Lee-Chatelier principle is concerned, just a second guys. As per Lee-Chatelier principle is concerned, if any change is imposed on the system at equilibrium, if any change is imposed on the system at equilibrium, if any change is imposed on the system at equilibrium, comma, equilibrium shifts in such a direction in which the effect of change is nullified. Effect of change is nullified. What is meant by this particular statement? Try to understand, guys. According to this principle, if any change is imposed on a system at equilibrium, then equilibrium will shift in such a direction in which the effect of change is nullified. What is meant by this? See, guys, for example, you have got a system which is present at equilibrium. Let's say you have got a system which is present at equilibrium. That means system is present at its maximum stable state. If you try to disturb the stability by somehow, equilibrium will try to bring back the stability by doing exactly opposite of what you did to the system. In short, in simple line, I'm telling you. So, for example, you have got the system which is present at equilibrium. That means the system is present at its most stable state, right? System is present at its most stable state. If by chance we try to disturb the system which is at equilibrium, which is at stable state, that means we are trying to change the stability, right? We are trying to alter the stability. Equilibrium will do exactly opposite of what we do to the system, so that the effect of change is nullified. So that stability is restored back. See, if we try to disturb the stability, what equilibrium is going to do? It is going to get the system back to stability. So in short, whatever we do to the system, equilibrium exactly does opposite of what we do. In short, right? So let me write this statement in short. Equilibrium exactly does opposite of what we do to the system. Of exactly what we do to the system. Equilibrium exactly does opposite of what we do to the system. In short. Okay? Now guys, try to understand. Try to understand. One by one, we are going to discuss things. Now, by how many means we can disturb equilibrium? How many means? By how many means? By how many ways we can disturb equilibrium? We can change the concentration of reactants and products, and let's see what happens. Try to understand this carefully. For example, you have got the reaction in which reactants and products, they are at equilibrium. If they are at equilibrium, absolutely, I would say they are present at their maximum stable state. Now, if we disturb this equilibrium by changing the amount of product, by changing the amount of reactant, by changing the amount of product, by changing the amount of reactant, let's see what equilibrium does. In short, one thing you have to remember, equilibrium exactly does opposite of what we do, right? Try to understand. I'm assuming this particular reaction is at equilibrium. If this particular reaction is at equilibrium, I would say its QC will be equal to Kc, which will be equal to concentration of product at equilibrium raised par stoichiometric coefficient divided by concentration of reactant at equilibrium raised par stoichiometric coefficient. Right? If the reaction is at equilibrium, then its QC will be equal to Kc. Correct? Its QC will be equal to Kc. Now you tell me one thing. If by chance I'm trying to increase the amount of reactant, if I increase this term, what will happen to QC? Inversely proportional. If I increase this term, QC will decrease. Initially, QC was equal to Kc. But what I did, I increased the concentration of reactant. QC decreased. QC became less than Kc. So, system would want again its QC to increase its value so that it becomes equal to Kc. I hope you are getting what I said. I'm trying to increase the concentration of reactant. I'm trying to increase the amount of reactant. If I increase this term will decrease. Initially, they were equal. Now QC is decreasing. So, system would again want its QC to increase its value such that QC becomes again equal to Kc. So, what will happen at this particular point of time? I'll say QC will try to increase its value. And how QC will increase its value? When amount of product will increase, amount of reactant will decrease. And how amount of product will increase? When equilibrium shifts forward. Right? Right, people? Now, imagine if I try to decrease the amount of reactant. If amount of reactant is decreased, that means I'm trying to increase QC. Initially, they were equal. Now, I'm increasing this. System would again want its QC to decrease its value. And how system can decrease the QC value? How QC value can decrease? Tell me that. QC value can decrease only if the amount of product will decrease. How amount of product will decrease? When backward reaction favors. So equilibrium shifts backwards. Right? Is it clear? Similarly, guys, if the amount of product is increased, if you increase the amount of product, QC will increase. Initially, they were equal. Now QC has increased. Again, system want its QC to decrease its value so that they become equal. So QC would want to decrease its value. How exactly QC would decrease its value? QC will decrease its value if the amount of product will decrease. How amount of product will decrease? When backward shift occurs. So equilibrium shifts backward. Similarly, if the concentration of product is decreased, that means equilibrium shifts in forward direction. Is that clear? Is that clear, people? Let me know once in the chats. This is the effect of, yes, Abdul. This is the effect of change in the amount of reactant and product when the reaction is at equilibrium. Right? You got to know the direction of shift of equilibrium. I hope this is clear. Let me know once in the chats if this is clear. Let me know once in the chats if this is clear. Right, people? Perfect. All right. So this was effect of change in the amount. Now, my dear students, there is one statement. There is one statement. There is no effect. There is no effect of adding a solid at equilibrium. There is no effect of adding a solid at equilibrium. What it means? See, this is in solid state, this is in solid state. If they are in solid state, if you want to write their QC expression, in the QC expression, will this quantity or this quantity will be there? These two quantities won't be there in the expression of QC. In the expression of QC, these two quantities won't be there because active mass is constant, unity, right? So these two reactants and products, they won't be there in the QC expression. So if you change their amount, increase or decrease their amount, will anything happen to QC? Nothing is going to happen to QC. So if QC does not change, will there be any shift or something? Nothing will happen. So do remember this particular statement. There is no effect of adding a solid, of adding or removing a solid at equilibrium. Perfect? Because by the addition or subtraction of solid at equilibrium, nothing is going to happen because solids, they do not come in the expression of QC. If they do not come, if you increase or decrease their amount, nothing will happen to QC. If QC is not changing, that means no shift will happen. Perfect. I hope this point is clear to you. I hope this point is clear to you. Now, my dear students, there is something called as effect of change in pressure. Effect of change in pressure. First of all, effect of change in pressure. Imagine this particular reaction is taking place in a container, keeping volume and temperature constant. I'm keeping the volume and temperature of the system constant. And when volume and temperature is constant, as per ideal gas equation, PV is equal to nRT, right? If volume temperature is constant, I can say pressure is directly proportional to moles. If you decrease the moles, pressure decreases. If moles are increased, pressure increases. Simple. Now you tell me one thing. You tell me one simple thing. First of all, on the reactant side, how many moles are there? How many gaseous moles are there? 3 plus 1, 4. There are 4 gaseous moles on the reactant side. On the product side, how many gaseous moles are there? 2. Okay. Tell me one thing. When forward reaction happens, what is happening to the total gaseous moles? Can I say when the forward reaction happens, gaseous moles are decreasing? And if gaseous moles are decreasing, pressure of the system decreases. So in the forward direction, is pressure increasing or decreasing? Pressure is decreasing. If I ask you, in the backward direction, does pressure increase or decrease? Pressure increases. In the forward direction, pressure decreases. In the backward reaction, pressure increases. Particularly for this case, for this particular case, right? Now, if you increase the pressure of the system, if, for example, I increase the pressure of the system, if I'm increasing the pressure of the system, equilibrium will try to decrease it. Because whatever we do, equilibrium does opposite of what we do. If I try to increase the pressure of the system, equilibrium will try to decrease it. How equilibrium will try to decrease it? In which direction? Equilibrium will shift. Pressure is decreasing in forward direction. So I will say equilibrium will shift in the forward direction. Right? Understand this again. Understand this again. Understand this particular point again. In the forward direction, pressure is decreasing. In the backward direction, pressure is increasing. Perfect. Over here for this particular reaction. Now, if you try to increase the pressure of the system, equilibrium will try to decrease it. How equilibrium can decrease the pressure? It will make sure that equilibrium shifts forward because here in the forward direction, pressure is decreasing. Perfect. So, On increasing the pressure, equilibrium is shifting forward. If you understand carefully, in the forward direction, are the gaseous moles increasing or decreasing? Gaseous moles are decreasing. So can I say, upon increasing the pressure, equilibrium will shift in such a direction in which the total gaseous moles decreases? Right? That's what we would have written over here. Upon increasing the pressure, reaction will shift in that direction in which the total gaseous moles decreases. Perfect. There will be some reaction in which gaseous moles will decrease in backward direction. Perfect. So this is the point which you have to remember. Right, guys? Is it clear? Is it clear, guys? Let me know once in the chats quickly. So do remember this particular point. Upon increasing the pressure, equilibrium will try to shift in such a direction in which the total gaseous moles decreases. Those gaseous moles can decrease in forward direction, or in some reaction it can happen in backward direction. Accordingly, you can give your answer. Look at this particular reaction. What is delta Ng for this reaction? Delta Ng is 0. Delta Ng for this reaction is 0. So basically, this is 1, 1. So on reactant side, 2 moles. On product side, 2 moles. So are the moles changing? No. Will the pressure be changing? No. Pressure is not changing. So if you try to increase or decrease the pressure, will anything happen? Will anything happen here? Nothing is going to happen here. So for those reactions whose delta Ng is 0, do remember, there will be no shift in those sort of reactions on changing the pressure. If you change the pressure, there will be no shift. Yeah, there will be no shift. Perfect. I hope this is clear to everyone. Right, guys? Perfect. Now moving on to one more important thing. Effect of temperature. This is the most important thing. And try to understand this particular point very carefully, guys, okay? First of all, this is a particular equation, Van 't Hoff's equation. This equation is going to let us know how exactly upon changing the temperature, equilibrium constant is going to change. Now, let's have a look how equilibrium constant will change upon changing the temperature. First of all, imagine that the reaction is A gives B. Perfect. When this reaction was carried out at temperature T1, imagine its equilibrium constant was K1. When you change the temperature of the reaction from T1 to T2, assume its equilibrium constant is K2. When this reaction was carried out at temperature T1, its equilibrium constant was K1. Temperature T2, its equilibrium constant is K2, for example. Okay. Now, first of all, if I assume that particular reaction is endothermic in nature, imagine the reaction is endothermic. If the reaction is endothermic, will its delta H, is it going to be positive or negative? It's going to be positive. Right? So delta H for endothermic reaction is positive. Now, for example, imagine I'm increasing the temperature of this particular reaction. I'm increasing the temperature here. Now you tell me, if I increase the temperature, T2 minus T1 value, will it be positive or negative? If I increase the temperature, T2 minus T1, final temperature minus initial temperature, that will come out to be positive. So first of all, delta H is already positive. T2 minus T1, this is T2 minus T1. T2 minus T1 is also positive. If this is positive, this term is positive. So I would say log of K2 by K1 will be positive. Log of K2 by K1 will be positive. When is that possible? When is log of X positive? Log of X is positive when X is greater than 1. What is X here? It is K2 by K1. So K2 by K1 has to be greater than 1, which is possible only if K2 will be greater than K1. What did you conclude from here? You conclude one simple thing. Upon increasing the temperature, equilibrium constant is increasing. So do remember, in case of endothermic reactions, equilibrium constant is directly proportional to temperature. If you increase the temperature, equilibrium constant will increase. Now here I'm going to tell you one important point. To understand it very carefully because you might do a mistake here. My dear students, you know what is equilibrium constant basically? It is Kf divided by Kb, rate constant of forward divided by rate constant of backward reaction. Perfect. First of all, do remember, upon increasing the temperature, this point take a note of, upon increasing the temperature, rate constant of forward as well as the rate constant of backward increases. This is something which we will study in chemical kinetics, right? When you increase the temperature, upon increasing the temperature, Kf as well as Kb increases. Perfect. Kf as well as Kb increases. Now, people, I am telling you, equilibrium constant of the endothermic reaction, that's directly proportional to temperature. So if you increase the temperature, if you increase the temperature here, upon increasing the temperature, equilibrium constant has to increase. Equilibrium constant has to increase. How will equilibrium constant increase? How will equilibrium constant increase? Does that mean Kf will increase and Kb will decrease? Does that mean Kf will increase and Kb will decrease? That is not the case here. That is not the case here. Because we know when you increase the temperature, Kf as well as Kb both will increase. Now, if Kf is increasing as well as Kb is increasing, then how come Keq will increase? I'll say increase in the value of Kf will be more than that of increase in the value of Kb. I'll say in this particular case, increase in the value of Kf will be more than that of increase in the value of what? Increase in the value of Kf will be more than that of increase in the value of Kb. Right? Do remember this particular statement. Upon increasing the temperature, in case of endothermic reactions, increase in the value of Kf will be more than that of increase in the value of Kb. That is how your Keq increases. That is how your Keq increases. I hope this point is clear to everyone. I hope this particular point is clear to everyone. Now, let me talk about the exothermic reactions. Let me talk about the exothermic reactions. You are going to let me know all the answers now. You are going to let me know all the answers now. See, if I talk about the exothermic reactions, by the way, there's the logic as well. Why Kf increases more, why Kb increases comparatively less, or increase the temperature in endothermic reactions. There's a logic which we shall be discussing in chemical kinetics. Okay? Perfect. Try to understand now. Imagine I have got an exothermic reaction. Imagine the reaction which I have taken over here, it's exothermic. If it is exothermic, its delta H is negative. Its delta H is negative. Its delta H is negative. Understood? For this particular exothermic reaction whose delta H is negative, if you try to increase its temperature, I'll say T2 minus T1. Final temperature minus initial temperature will come out to be positive. Agreed? Right? Imagine this particular reaction is exothermic. So delta H is negative. T2 minus T1. T2 minus T1 is positive. Now positive negative makes the overall term as negative. I would say log of K2 divided by K1 here is going to be negative. When is it possible? It is only possible if K2 by K1 is less than 1, which is telling you K2 is less than K1. Which is telling you K2 is less than K1. Right? What is meant by K2 less than K1? It simply tells you that your equilibrium constant, when you increase the temperature, equilibrium constant decreased. So for exothermic reactions, equilibrium constant is inversely proportional to temperature. For exothermic reactions, equilibrium constant is inversely proportional to temperature. Right? Since you got to know equilibrium constant is inversely proportional to temperature, now you tell me one thing. You know your equilibrium constant. It is basically equal to Kf divided by Kb. Now, for exothermic reactions, if you increase the temperature, equilibrium constant will decrease. Equilibrium constant decrease. What does that mean? Does that mean this term will decrease and this term will increase? No. No. Why is that? Because when you increase the temperature, upon increasing the temperature, rate constant of forward as well as backward reaction increases. But in this particular case, increase in the value of Kb will be more than that of increase in the value of Kf. If increase in the value of Kb is more than that of increase in the value of Kf, eventually your equilibrium constant net, it increases, right? So do remember, increase in the value of Kb here will be more than that of increase in the value of Kf. That is the reason why your equilibrium constant decreases in case of exothermic reactions upon increasing the temperature. Is this point clear? Was it nice? Yeah? Good one? Is it clear? Clear to you guys? Just give me a second. Just give me a second, guys. I hope this particular concept is absolutely clear to all of you. Huh? There are some other things which we need to discuss. Just give me a second before that. Just give me a second before that. Perfect. There are a few graphs which I would want to give you over here, which are very important. But before that, there is one relation which I would want you guys to remember. This is something which we'll basically discuss in the chapter Thermodynamics. Okay? This is something. Yes, I'll discuss the catalyst also. Just wait. There is nothing in catalyst though. Okay? There is one relation which we shall be discussing in the chapter Thermodynamics. Delta G for the reaction is equal to delta G naught for the reaction plus RT ln of QC. Have you studied this particular relation before? Have you come across this particular relation? Delta G for the reaction is equal to delta G naught plus RT ln of QC. Now, at equilibrium, I hope you know, at equilibrium, in the beginning I told you, at equilibrium, delta G for the reaction is 0, right? If delta G is 0, if this term is 0, this will come on this side. It becomes minus delta G naught is equal to RT ln of QC. RT ln of QC. Yes. Even in electrochemistry, I have given you this particular result. Yeah. When I derived the Nernst equation, if you remember. Long back. Anyways, leaving that aside. So I'll say delta G naught for the reaction is equal to, it is minus RT ln of QC. Is this point clear? Is this point clear, guys? Is this point clear to you? Yeah. Now, as per thermodynamics point of view, your delta G is equal to delta H minus T delta S. So delta G naught has to be equal to delta H naught minus T, and this is delta S naught. It is equal to minus RT ln of QC. Ln of QC. First of all, at equilibrium, your delta G is 0. At the same time, QC is equal to KC, right? QC is equal to KC. So, wherever I'm writing QC, I'm supposed to write KC over here. Or you can directly write equilibrium constant KEQ. Perfectly done? Perfectly done till here? Okay. If I multiply throughout by minus sign, it becomes something like this. Minus delta H naught divided by RT plus this is T delta S naught divided by RT is equal to ln of Kc. Is equal to ln of Kc. Is equal to ln of Kc. Right? Is equal to ln of Kc. Now try to understand few important things over. Try to understand few important things over here. My dear students, case number 1. Imagine you have got a reaction whose delta H is, for example, negative, and delta S is, for example, positive. Imagine you have got a reaction whose delta H naught is negative and delta S naught is positive. Now, if delta H naught is negative, negative makes it positive, right? So the equation becomes delta H naught divided by RT, right? Delta S is positive plus T delta S naught divided by RT is equal to ln of Kc. The equation becomes like this. Now, for this particular reaction, if you want to plot a graph between ln of Kc versus C, first of all, this T and T here gets cancelled out, right? When T gets cancelled out, so this is T and T here, right? Is it clear? Can you plot a graph between ln of Kc versus 1 by T in this particular case? What do you think? What do you think will be the nature of this particular curve? Quickly, guys. What do you think will be the nature of this particular curve? What do you think will be the nature of this particular curve? Quickly. What do you think will be the nature of this particular curve? I want to plot a graph between ln Kc versus 1 by T. Ln Kc versus 1 by T. So basically, you can write this particular equation in this format. You can say ln of Kc is equal to. You can write it as delta H naught divided by R multiplied by 1 by T plus delta S naught divided by R. You can write it like this. Now ln Kc you are plotting along y-axis. 1 by T you are plotting along x-axis. This whole term becomes your m. This term becomes your c. In between sign is minus. Y is equal to mx plus c. The graph is like this. What about the slope of this particular graph? Slope is m basically, which is your delta H naught divided by R. Delta H naught divided by R. Right? It is equal delta H naught divided by R. Is it clear? If you ask me what about the intercept? What about the intercept here? Intercept means C value, and C is coming out to be delta S naught by R. Delta S naught divided by R. Can you plot different sort of curves like this based on the sign of delta H and delta S? Right? Can you plot these sort of graphs? You should be easily doing it. Can you plot these sort of graphs, people? I showed you one case in which delta H is negative, delta S is positive. Similarly, there can be another case in which this is positive, this is negative. Both are negative, both are positive. You should be able to make these sort of graphs. You should be able to make these sort of graphs, right? Is this clear? Because from these graphs also questions can come. Questions can come for sure from these type of graphs as well. I hope this particular point is clear to everyone. Okay. Hello, one more case I'll show you. Imagine your delta S is, imagine both are positive. Case 2. Case 2. If delta S naught is positive, as well as delta H naught is positive. Both are positive. Now, if both are positive, what's going to happen? This is positive, even this is positive. Perfect. Positive, negative makes it negative. So, I'll get the equation like this. Ln of Kc. Ln of Kc is equal to. Ln of Kc is equal to. This is going to be delta S naught divided by R. Delta S naught divided by R. And it's going to be delta H naught divided by RT. Right? It's going to be delta H naught divided by RT with the sign minus in the beginning. Okay. So in this particular case, if you want to plot a graph between ln of Kc versus 1 by T. So first of all, 1 by T, you are plotting along, 1 by T, you are plotting along x-axis. So this is x, this is m minus c. So y is equal to minus mx plus c. So the graph is going to be like this. Slope of this particular graph is going to be what? It's going to be minus delta H naught divided by R, right? And its intercept is going to be delta S naught divided by R. So these sort of graphs you should be able to draw. Perfect. This is one more case. Similarly, there can be two more cases, case 3 and case 4. I'm keeping it to you. Perfect. I'm keeping it to you. In the similar way, you can check what will be the nature of the graph. This is your homework and this is your homework. That's all. That's all. Okay. Now, people, now something important which we are going to discuss. What is that? We are discussing Lee-Chatelier principle basically. Now, in the Lee-Chatelier principle, we discussed effect of change in the amount of reactant product, number 1. We discussed the effect of change in temperature, number 2. We discussed the effect of change in pressure, keeping volume temperature constant. Now, effect of inert gas addition at constant pressure. Effect of inert gas addition at constant pressure. What is meant by this? Does it mean we are adding an inert gas? Inert gas, your helium, neon, brom, this xenon, etc., etc. Does it mean that? See, there's a misconception among students whenever you hear this term, effect of inert gas addition, effect of inert gas. They think like we are adding helium, neon, argon, right? It's not that basically. Inert gas basically means, see, this is the reaction, these are your reactants and products. I'm telling you, I'm adding inert gas here. Inert gas is that particular gas which is not going to react with any of these reactants or products. Inert gas here means that particular gas which is not going to react with any of the reactant or product in a particular reaction. Okay? Inert gas here means we are adding such a gas which is neither going to react with any reactant nor with any product. Okay? Now, you tell me one thing. We are doing the inert gas addition at constant pressure. My dear students, imagine this is the reaction which is carried out at constant pressure. Temperature, all the time it's constant only, right? Because majority of the reactions, they are carried out at constant temperature. Perfect. R is already constant. So directly from here we can say volume is directly proportional to moles. Volume is directly proportional to moles. That means if moles are increasing, volume will be increasing. Moles are decreasing, volume will be decreasing. Why am I telling you this? Try to understand. This is, for example, my reaction. If this is my reaction, I'm assuming at equilibrium, this is the concentration of PCl5, this is the concentration of PCl3, this is the concentration of Cl2 at equilibrium. These are the terms which I'm assuming. Now, if the reaction is at equilibrium, can I say its QC is equal to Kc? And how do I write its expression? Concentration of this multiplied by concentration of this, which is B square divided by V square whole divided by concentration of PCl5, which is A by V. So VV cancel. So B square divided by A multiplied by 1 by V. This is how you wrote the expression. Now, my dear students, I'm assuming this particular reaction is carried out at constant pressure and temperature. At constant pressure and temperature. This particular reaction, I'm assuming, is happening at constant pressure and temperature. If this reaction is taking place at constant pressure and temperature, at that point of time, volume is directly proportional to moles. You know it. Now tell me one thing. At constant pressure and temperature, if I'll be adding an inert gas in this container, if I add the inert gas in this container, what will happen to the total moles? Total moles in the container. I'll say total moles in the container will increase. If total moles in the container is increasing, I'll say volume will be increasing. I'll say volume of the system will be increasing. If volume is increasing, volume and QC inversely, if volume is increasing, that means QC will decrease. Initially, QC was equal to Kc. Now QC has decreased. So system would again want the value of QC to be increased, such that it becomes equal again, such that equilibrium comes in the reaction again. So what is going to happen? QC is again going to increase its value. By the addition of inert gas, total moles increased, volume increased, QC decreased. Initially they were equal, now QC decreased. So again QC will bring back its value. Again QC will increase its value. How QC will increase its value? QC will only increase its value if the equilibrium shifts forward. If the equilibrium shifts forward, right? And in the forward direction, are the gaseous moles increasing or decreasing? In the forward direction, gaseous moles are increasing. So do remember, upon the addition of inert gas at constant pressure, equilibrium shifts in such a direction in which the total gaseous moles increases. Right? Reaction shifts towards highest number of gaseous moles upon adding the inert gas at constant pressure. Is this particular statement clear? So do remember, when you add inert gas in a system, right, at constant pressure, equilibrium will shift in such a direction in which total gaseous moles increases. Right? Now, gaseous moles can increase either in forward direction or backward direction, depending on the reaction. Yeah? Perfect. Now, there is one more case. What is that? Effect of inert gas addition at constant volume. Effect of inert gas addition at constant volume. Effect of inert gas addition at constant volume. I'm assuming that this particular reaction, for example, it's carried out at constant volume and temperature. And if volume temperature is constant, as per ideal gas equation, pressure is directly proportional to moles. If moles increase, pressure increases. Right? This is understood. This understood. Now you tell me one simple thing, guys. Try to understand. Imagine these are the moles of reactants and products at equilibrium. And imagine these are the partial pressures. A divided by total moles multiplied by total pressure. B divided by total moles multiplied by total. So these are the partial pressures. These are the partial pressures of reactants and products at equilibrium. Assume that. Okay. Now, if this reaction is at equilibrium, that means its QP will be equal to KP. Its QP will be equal to KP. How do you write the KP expression here? Partial pressure of this multiplied by partial pressure of this. It's going to be B square divided by NT square multiplied by PT square whole divided by partial pressure of PCl5, which is A divided by NT multiplied by PT. So what our terms will get cancelled out? NT cancel. 1 PT, 1 T, 1 PT cancelled. So the final expression will be like this. It will be B square divided by A, B square divided by A, and this is going to be PT divided by NT. Correct? This is going to be your expression. This is going to be your expression. Now guys, try to understand. This particular reaction, it's carried out at constant volume and temperature. And at constant volume and temperature, pressure is directly proportional to moles as per ideal gas equation. Now you need to understand certain things. If you are adding inert gas here, due to the addition of inert gas, you are increasing the total moles. Due to the addition of inert gas in the container, you are increasing the total moles. And at the same time, since you are increasing the total moles, that means total pressure will be also increased. Total pressure will be also increased. So basically, upon the addition of inert gas at constant volume, total moles increases. Total pressure also increases. Total moles increases. Total pressure also increases. Right? What will happen due to that? If denominator as well as numerator both are increasing by same proportion, they'll cancel out. So will QP change? QP won't change. If QP does not change, will there be any shift? There'll be no shift. Right? So effect of inert gas addition at constant volume, there'll be no shift at equilibrium, right? Because the proportion in which moles increase, in the same proportion, pressure also increases, and effect is nullified of moles and pressure, due to which QP does not change. If QP is not changing, there'll be no shift at all. Perfect. Is it done? If this is done, what does the catalyst do? I've already told you. What does the catalyst do? Catalyst, if I talk about the positive catalyst, positive catalyst or a negative catalyst. Positive catalyst or a negative catalyst. What is the positive catalyst? Positive catalyst means the one which accelerates the rates of the reactions. Negative catalyst means the one which deaccelerates the rates of the reactions, right? Okay, you would have studied that. Now, catalyst, be it positive or negative, it does not affect the equilibrium state. It does not. What it does then? A positive catalyst, it just speeds up the forward and backward reaction. Positive catalyst speeds up the forward and backward reaction by equal amounts. A positive catalyst increases the rate of forward and backward reaction by same amount, due to which equilibrium is established in the reaction quickly. Nothing else. Whether the equilibrium comes in the reaction late or equilibrium comes in the reaction early, equilibrium concentrations anyway are going to be same, right? So due to the presence of catalyst, equilibrium concentrations, they don't change. If they do not change, nothing happens to equilibrium constant, right? It is just a positive catalyst. It speeds up the forward as well as backward reaction by same amounts, due to which equilibrium is established in the reaction quickly. But due to that, nothing happens to the equilibrium concentrations. Equilibrium concentrations are still the same, with or without catalyst, right? If equilibrium concentrations are same, that means there is no effect on the equilibrium state. I hope this is clear. Solve this question. Tell me the answer of each. Predict the direction of shift of equilibrium if more H2 is added. If you are adding more H2, in short, if you are adding more H2, equilibrium will try to do opposite of what we do. We are increasing this. Equilibrium will try to decrease this. How equilibrium will try to decrease this? When you will make the reaction to move in the forward direction. So forward shift, right? In short, NH3 is added. If we add NH3, Equilibrium will try to decrease NH3. How? It will make sure the equilibrium shifts backward. Backward reaction is favored here. Right? Now, temperature is increased. First of all, look at this reaction. In this reaction, energy is absorbed over here. If energy is absorbed, it's endothermic. If energy is absorbed, here it is endothermic then. And in endothermic reactions, equilibrium constant is directly proportional to temperature. If you increase the temperature, equilibrium constant increases. If you increase the temperature, equilibrium constant increases. How equilibrium constant increases? When reaction moves forward. Inert gas is added at constant volume. There will be no effect. Inert gas is added at constant pressure. When you add inert gas at constant pressure, reaction moves towards when you add inert gas at constant pressure, reaction moves towards highest or lowest? Highest number of gaseous moles. Highest gaseous moles, see on left side there are 4, on right side it's 2, so it's going to be backward shift, right? It's going to be backward shift. Okay, something which we discussed right now. Towards highest number of moles. Towards highest number of moles. Okay? Perfect. Tell me the answer of this question. Tell me the answer of this question. You've got a reaction at equilibrium, right? Closed container and an inert gas. Inert gas, helium, here you are introducing. Which of the following statement is correct? You are introducing an inert gas. The gas is helium. It is not going to react with this, nor this, nor this, right? Which statement is correct? Which statement is correct? Quickly. Closed container means volume is constant. Closed container means volume is constant. Volume is constant. And all the reactions, right? Here it is carried out at 25 degrees centigrade. So you are adding inert gas at constant volume. If you are adding inert gas at constant volume, will there be any shift? There will be no shift. No change in the concentrations of reactants and products. No shift at all. There won't be any shift. Right? There won't be any shift at all. What do you think about this one? Reaction is given. You have to be very quick, guys. Reaction is given. The equilibrium amount of carbon dioxide can be increased. How can you increase the amount of carbon dioxide? How can you increase the amount of carbon dioxide? If you increase the amount of CO, equilibrium will try to decrease it. How equilibrium will decrease it? It will shift the reaction in the forward direction. In the forward direction, more carbon dioxide can be formed. Is there any option as increasing the amount of carbon monoxide? It is option D. Upon increasing the amount of carbon dioxide, right, reaction will shift forward, due to which more carbon dioxide will get formed. Simple. Yeah? Is it clear, people? Tell me the answer of this question. Tell me the answer of this question. For the reaction 3x plus y gives something, the amount of x3y is affected by. How the amount of x3y can be affected? See, this is the reaction whose delta Ng is non-zero. So if you change the pressure, you can change the effect, right? If you change the pressure, you can. Similarly, depending on the type of the reaction, whether exothermic or endothermic, equilibrium constant accordingly changes. So temperature and pressure both. Temperature and pressure both are going to be the ones which are going to change the amount of x3y. Okay? Now, all right, one more question is there. This is the question whose answer you will let me know in the chats right now. When NaNO3 is heated in a closed vessel, oxygen is liberated and NaNO2 solid is left behind at equilibrium. This I'm keeping as the homework. Do let me know the answer of this particular question in the comment section of the video, right? I would want its answer in the comment section, and I'm directly moving on to something called as simultaneous equilibrium. It is not going to take us more than like 15 to 20 minutes. Okay? In 15 to 20 minutes, we'll end it up. That's great, Teddy. Glad to know that. Glad to know that. God bless you. So let's try to understand this simultaneous equilibrium first of all. Let's see exactly what it's all about. Let's wind it off, then you sleep, guys. I'm not going to give you any sort of break here at this moment because it will break the flow. It is a small topic, 10 to 15 minutes it will take. For example, I've got the reaction like this. AB solid. Imagine it's in equilibrium with A gas plus B gas. Let's say this is the reaction. AB solid is in equilibrium with A gas and B gas. Now tell me whether this AB solid will contribute towards any pressure at equilibrium. It is not going to contribute towards any pressure at equilibrium. Only this and this will contribute towards the pressure at equilibrium. Because this is solid, it's not going to contribute. These two are only going to contribute. Correct? The stoichiometry here is 1:1. The stoichiometry here is 1:1. So let's assume at equilibrium, pressure due to A is x atm and pressure due to B will be also x atm. Right? Perfect. Because stoichiometry is 1:1. If it was 1:2, then this was x, this should have been 2x. Correct? Right, guys? Perfect. Now, the container in which AB solid is in equilibrium with A and B, in the same container, imagine AC solid is also in equilibrium with its components. Imagine in the same container, AC solid is also in equilibrium with its components, right? Now tell me one thing. Will this solid contribute towards any pressure at equilibrium? No, it's a solid. It's not going to contribute. It will settle down at the bottom of the container. This and this will contribute. Let's assume at equilibrium, pressure due to A is Y here. So this will be also Y because it's 1:1 stoichiometry again. Perfect. Now, my dear students, in the same container, do you see there are basically two equilibriums simultaneously? There are two equilibria simultaneously. And both are having one component in common, AA. Whenever you see such kind of the scenario in which in the same reaction vessel, two reactions or more than two. Whenever you see such kind of the scenario in which two or more than two reactions will be in equilibrium with their components. And among those components, minimum one of the component is common. Among those components, minimum one of the component is common. This particular scenario is what you call as simultaneous equilibrium. This particular scenario you call as simultaneous equilibrium. So what is simultaneous equilibrium? It is that sort of equilibrium in which in only one reaction vessel, two or more than two reactions are in equilibrium with their components, right? With minimum one of the component common in both. Okay. Now, understand one thing. Here you have got A, here you have got A. Right? Pressure due to A from the first reaction is X. Pressure due to A from the second reaction is Y. So, what will be the net pressure due to A? What will be the net pressure due to A? You'll write X plus Y. This will be also X plus Y. Net pressure due to A is X plus Y. My dear students, if I ask you, what is Kp for the first reaction? Write the expression for Kp. You'll say partial pressure of this, partial pressure of this. So, it's X plus Y multiplied by X. What about Kp2? What about Kp2? Kp for the second reaction. Kp for the second reaction will be partial pressure of this, partial pressure of this. It's again X plus Y multiplied by Y. Calling this equation 1, calling this equation 2. Now, if you add these two equations, here Kp1 plus Kp2 will be equal to X plus Y ka whole square. From here you can get X plus Y is equal to under root of Kp1 plus Kp2. This is one of the result. This is one of the result. Number one. Number two, if you divide the two equations, you'll get something like this. Kp1 divided by Kp2 is equal to X plus Y cancel. You'll get it as X by Y. So Kp1 divided by Kp2 here is coming out to be X by Y. Kp1 plus Kp2 is coming out to be under root of Kp1 plus Kp2. Perfect. So we got two equations, two unknowns. Solved? Can be solved? In the questions, you will have to use these equations and solve the equations. That's all. I'll show one question that is more than sufficient here. One question that is more than sufficient here. Look at this particular question carefully. Understand the question carefully. I don't know what the question is, first of all. Consider the given simultaneous equilibria. Two reactions are given, their Kp values are given. Calculate the partial pressure of NH3 at equilibrium. Okay. See, similar sort of question this is. You have to be careful with certain things over here. I'm writing the same reactions again. This is NH4 twice. This is sulfur, this is in solid state. It is in equilibrium with 2 times NH3 gas plus H2S gas. Its Kp is given. Solid is not going to contribute. Stoichiometry is 2:1. So at equilibrium, pressure due to NH3 is 2x. This will be x. Now in the same reaction vessel, we have got NH4 whole twice, Se solid, right? It is in equilibrium with 2 times NH3 gas plus H2Se gas, right? This solid is not going to contribute towards any pressure, right? Let's say pressure due to this is 2y, this is going to be y. Both the reactions are in equilibrium and present in the same reaction vessel, and both are having one component in common, that is NH3. So total pressure due to NH3, here is 2x, here is 2y. So it's going to be 2x plus 2y. This is going to be 2y plus 2x. This is the total pressure due to NH3. What am I supposed to calculate? As per the equation, I'm supposed to calculate the partial pressure of NH3 at equilibrium. And as you can see, partial pressure of NH3 at equilibrium is what? Partial pressure of NH3 at equilibrium is nothing. It is 2x plus 2y. So I have to calculate this value. So in order to get this value, I need x and y. Now, how exactly you are going to get x and y? So first of all, if you write the expression of Kp1 expression is going to be x. Kp1 expression is going to be x multiplied by 2x plus 2y ka whole square. This is your Kp1. Similarly, Kp2 is going to be y multiplied by 2x plus 2y ka whole square. Perfect. Now, if I divide these two equations, this term cancel. So I'll get x divided by y is equal to Kp1 by Kp2. Kp1 divided by Kp2, it will come out to be 2, which is telling you that x is equal to 2y. So this is one thing which I got, x is equal to 2y. This is one thing which I got, x is equal to 2y. Perfect, x is equal to 2y. Is it clear till here? Tell me that quickly. Is it clear till here, people? Is that clear till here? So you got x is equal to 2y. Now put this x is equal to 2y in any of these equations. Put it in the first equation. In the first equation, Kp1 is nothing. It is 9 into 10 raised power minus 3 is equal to, instead of x, I'm writing 2y. This is 2 times x. 2 times 2y, which is 4y plus 2y. 4y plus 2y ka square. 4y plus 2y makes it 6y ka square, which comes out to be 6y ka square. 36 y square this is. Or you can say this is 72 y cube. Perfect. So you got 9 into 10 raised power minus 3 is equal to 72 y cube. So this is 1, this is 8, right? So you got to know as your y cube is equal to 10 raised power minus 3 divided by 8. Or you can say y is equal to 10 raised power minus 1 divided by 2. Or you can say it is 0.5 into 10 raised power minus 1. Or you can directly say it is 0.05. But I think we did some mistake somewhere. Just a second, let me check it out. So, is there any sort of mistake, guys, in the calculation? 9198. So this is 8y cube here. That 8 goes to the denominator. Perfect. So y cube is 10 raised power minus 3 divided by 8. Y will be equal to 10 raised power minus 1 divided by 2 to the 4 to the 8 divided by 2, right? So it's going to be 1 by 20. 1 by 20 is 0.05. So y is equal to 0.05. If y is equal to 0.05, that means x is equal to 2y. 2 times this, which comes out to be 0.1 atm. Right? So you got x and y. If you got x and y, so 2 into x, 2 into 0.1 comes out to be 0.2 plus 2 into y. 2 into y, 2 into 0.05 comes out to be 0.1. The value comes out to be 0.3. So 0.3 atm is going to be the partial pressure of NH3 at equilibrium. Is it clear? Is it clear, people? Is it clear to everyone? Is it clear to everyone? Yes? Again, do check the calculation of this question. I'm not sure whether I did the calculation right here at the end or not. Do check it out. But I think it's right only, right? KP1 expression we wrote, KP2 expression we wrote. We divided them. We got the relation between x and y. Now I put this x here. So this is this, x is 2y. This is x is 2y. So it's 4y plus 2y makes it 6y. So 6y square makes it 36y square. So which makes it 72y cube. So 9198 cancel. So taking the root on both the sides. Yeah, it's correct only. It is correct only, guys. It is correct. So these sort of questions are basically asked in your simultaneous equilibrium. Okay. Perfect. And my dear students, with this, we are done with the chapter. Chemical equilibrium is done and dusted. Is done and dusted. In the